since it's live.
Okay. It is.
Oh, how about
Is it actually? Oh my gosh, I see it now too. Yay!
Sweet.
Of course, for once, turning it off and on actually works.
We did that twice. That's the second
Yeah.
time we did. Maybe it was something.
It probably just needed to cool off for a few seconds after the first reset. I don't.
Maybe. And I had deleted that one video, but I don't really think that did it because, yeah. So it's fine.
There we go.
Great. Okay. Awesome.
Sweet.
And it looks good. This is what it looks like. There.
Yep.
Cool.
So, yeah, I mean, you can still record it anyway just in case something crashes.
Oh, yeah.
Especially if that's, I don't know, if it's overheating or something. But you don't have to start that until like
Let's
5.
start, yeah, I was going to say 5 bucks.
Yeah, something like that. If you need any, not that I did anything, but if you need anything, I'll be around out there or whatever. Okay?
Thank you so
Thanks.
much.
Oh, thank you. Hi, Dan.
I can see the beam.
Yes, I don't know what happened, but it worked. So.
Okay, yay.
Yay. You know, it's funny because yesterday I left up the one that we had tested,
Right.
but we did that before and it worked. But what I did was I ended up deleting it just to make sure. I don't think it really think that had anything to do with it, but it didn't hurt obviously. So.
Right, yeah. No, okay, well, I'm glad it worked out.
Yeah, me too. And then they're going to start the recording about 5:09, so we'll have this back up if needed, if something, you know, if the box gets hot or whatever. So,
Right, yep.
awesome. All right, thanks for checking in, Dan.
Sure, no
All
problem.
right, take care. Bye. Okay. So that was very nice. All right.
Cool, yeah.
I'll see you later. Thanks.
No problem. All right.
Hi, Lisa.
Hi, Carol.
How are you doing?
Good. How are you? Good.
Right here.
Oh, yeah.
Yeah.
That was a good time. I'll be in and out.
Yeah. got it done in 3 hours.
Wow.
3 hours, yeah.
On the way home, that thing's coming. Yeah, they just fell. The one that I stole.
Running?
Yes, we are. Yes, we are.
Hi, Gary.
The midterm
feel like this is the first students to have three major assignments between all of them.
Like people were just like standing around.
welcome this morning to the 2021-22 Senior Project Capstone presentations. This is the culmination of a year's work. Students only get 3 credits for it. It's probably considered by many that the first semester worth 1 credit is probably the hardest 1 credit you'll ever work for. And you'll spend more time there than any other time for 1 credit. And then the second semester is 2 credits, and you work even harder than you would for a 3 or 4 credit course. But the ultimate objective is to use all of the educational capabilities that the university offered over 4 years. It is in fact called a capstone course, meaning which is the culminating part. Mother Nature and I have a little difficulty. Mother Nature seems to think that pollen is necessary for the spring, and my sinuses decide that ain't true. Not so much. So every now and then I may sneeze, and I apologize in advance. There's a couple of announcements I'd like to make on the whole process that we're going to go through this morning. The way we do our senior projects, obviously 2 departments, actually 2 departments and 4 of our disciplines work together in some of our senior projects. The electrical engineering teams, the mechanical engineering teams, engineering management, and physics. And what we do is allow some of the students to have multi-discipline on the team. For example, the first couple of presentations you're going to see are electrical engineers only. Then you'll see a presentation that has primarily electrical engineering project, but a dire need for some mechanical engineering to do some packaging and thermal work, and it's necessary. We have a presentation where one of our presenters is both a major in mechanical engineering and electrical engineering. The good news is that person gets twice as many credits, but as he's complained to me a couple of times, he had to work twice as hard. So instead of just 1 credit or 2 credits, he had to work again 2 or 3 times as hard to actually get it to happen. And then we have a mechanical engineering project that needed electrical engineering support, and that will happen near our lunchtime, and I think it's called the Heavy Impact Training System. So it's a good thing. That's how things work together. I have a couple of other announcements I'd like to offer, is that the electrical engineering awards have been announced but not presented, and the Dr. Najib Award for Outstanding Achievement in Electrical Engineering was presented. Matt Costello. Matt, could you stand up? For the second year in a row, that award has been awarded to a student with a perfect 4.0 in electrical engineering. There's some of us instructors probably couldn't do that, so congratulations, man. We also have a dual award this year. The Electrical Engineering Service Award is presented to those students who go above and beyond in helping with our outreach, our tours, our lab instructors, what we call our lab assistants, those folks who have really gone way above and beyond in trying to work with each other and other students in our organizations such as ESAC, the Engineering Council, and then IEEE, which is a professional organization that will run from the students all the way into their professional degree. And the 2 students this year, if these 2 students would stand up, Kyle Rossler and Ian Petrel. Congratulations. Someone who isn't here tonight, this morning rather, that was awarded the Frederick Bellis Award for Outstanding Physics is Siggins, Cornell didn't come from that, but he also received that award. I have one other announcement. Every year, IEEE in the local college area, Lehigh Valley area, offers a paper contest. The Morton Paper Contest. Some of our other members are graduating. Hello, graduating members. How are you? Thank you for joining us. They have participated, and this year we had 2 teams participate. In fact, you're going to hear a couple of the presentations or similar presentations. The 3rd place winner in that contest was our germanium tin group. If that group would stand up and in 2nd place was our team that did the what we call WIDNIC, the wide body charger. Would that team stand up? Ian and your team? I think it's important to note that activities like this dramatically help the students. They do well, they can communicate, and that's an important part of engineering. It's always a joke that engineers tend to look at their feet a lot when they're presenting. And there's a pretty good, funny story that you can tell that when an engineer has become a little more adept at giving presentations, he looks at your shoes and not his. Never supposed to. The engineers understand. You'll see today that many of the engineers are doing very well in their presentation skills. So not only have they done fantastic research, trace studies, design, manufacturing or fabrication and test. And I think you'll see the work that these outstanding students have done. So with that, I'm a couple of minutes behind. So I will go right on to the first group, the deep neural network group. If you'll come forward.
And I'm Charles Reeder.
And our project is about the design of power and energy efficient DNA applications on embedded systems. So first we wanted to provide some background on DNNs. So what does that stand for? It stands for deep neural networks, and they are algorithms that perform machine learning tasks. And the most relevant machine learning task in our project is image classification, meaning we would want to take a picture of a 0 and we would want our network to correctly categorize it as a 0. Now, when you're looking at the overall diagram for a DNN, you're going to have your inputs, which is going to be the pixel values of your input image. Your outputs are going to look something similar to what is in this green box, where it's a list of values. Each value corresponds to a category the input image can belong to, and the category with the highest value is the network's prediction. Now, in this case, you can see the highest numbers for the first category, so the network would predict the first category. Now, how do we know if this prediction is correct or not? Well, in our case, we use what is called a label, and that looks something similar to what's in the red box, where it's just a list of zeros with a single 1 in it, and that 1 corresponds to the correct category. So you can see in our example here, the 1 also corresponds to the first category, so the network would get this example correct. Now, when we first create a DNN, it's not going to be very accurate at all, and the main factor in determining the accuracy of a DNN are the values of what are called weight parameters. And if you look in our diagram in the upper right again, you can see all these are representing the intermediate calculations of the algorithm, and each one of these arrows corresponds to a weight parameter, and that's why we usually represent it as a matrix W. So if you want to increase the accuracy of the DNN, you're going to have to update the values of these weight parameters. And that process is called training. So the first step in training is you want to quantify how long your output is. And we do this by using what's called a loss function, and the loss function we use in our training is called categorical cross-entropy loss. And you can see the formula for it and how it's applied to the example from the previous slide. And the output of your loss function is going to be a value that's simply called a loss. And the goal of training is to minimize this loss value by updating the weight parameters. Now, the algorithm we use to update the weight parameters is called stochastic gradient descent, meaning you're calculating a gradient between your loss and your weight parameter, and then you are multiplying by a coefficient, we call that the learning rate, and then you subtract that product from the original weight value in order to get your new updated weight value. And you can repeat this process and use the new weight parameters to get a lower loss and a higher accuracy until you're satisfied with your accuracy. And we should also note that these gradients are also calculated using an algorithm that in general is called back propagation, meaning that you're calculating the gradients closer to the output before you calculate the gradients closer to the input. So once you've completed training and your model is accurate enough, you can then move on to DNN testing. And then DNN testing is more straightforward and it's less computationally expensive than training. And what you're doing is you're applying an input to the algorithm. You're no longer updating the weight parameters. You're only checking the output for correctness. And this is the process that we focus on in our project and that we actually implement onto our embedded system. And you can see this is an example of what the DNN testing result would look like. So as far as embedded systems go, they are small portable computer systems, and they allow for computation close to the sensor, meaning you don't have to be connected to the internet for them to work. You don't have to send data over long distances, which is good for latency. And really staying off the internet is also good for security purposes. And both embedded systems and DNNs are very popular these days, and the goal with this project is to combine these two technologies. The main problem with combining these two technologies, though, is that DNNs are computationally expensive, even with testing, and embedded systems are resource limited, meaning we're going to have to design our DNNs in a way that is compatible to run on these embedded systems. And the objectives we laid out in order to do that is, first we want to train and develop the DNNs in a desktop environment so we don't have to worry about the limited resources of the embedded systems right away. Once we establish our models, we then want to convert them to make them compatible with the embedded system, and then we want to measure the power consumption, the execution time, the energy consumption, the accuracy of the models while they run on the board, and then we want to identify and profile the trade-offs between these measurements.
For our project requirements, being the first requirement, we have to make sure that we satisfy the energy and execution time constraints when testing the DNN, because it's going to be run on a battery. We don't want to consume too much energy. We have to maintain accuracy between designing the neural network on a general purpose computer and testing it on the embedded system. And for our third requirement, we have to make sure that we don't overflow the memory capacity of the board when running it on the board. For our project constraints, beginning with economic, we only have $500 for any test cables or equipment we may need to continue testing it. For our environmental, we have to make sure we minimize some power consumption so that it doesn't consume too much energy because it's going to be run on a battery. For technical, we don't want to use too much memory because the board only has so much memory available. We also have to make sure we stay above an accuracy minimum. For specifications, key project specifications, beginning with models, we have to make sure that we limit the size of our models by capping out how many nodes it has, how many channels it has. The rest of the model specs are just based off the board specs, just slightly lower, so they stay within the limitations of the board. Power energy specifications, we chose 5 different runtime frequencies because that's just a good sample size. And we try to keep the board between 1 to 2 watt power consumption. We also say that the The max time to process an image is 1 second. So that leads to an average energy of 2 joules per image processed on neural network. And to keep the layers from consuming too much power, we say 2 joules divided by the number of layers in the model, so it isn't consuming too much energy. For ethical standards, we look to the IEEE Code of Ethics, and we have to make sure that we provide background information on neural networks and how they work to our clients. We also have to make sure we improve our knowledge of neural networks as we go out through this project. And we have to make sure that our models and their respective data sets do not violate or harm any individuals in their project.
All right, so for our WBS summary, which is also known as work breakdown summary, we kind of broke down into 2 main sets of tasks. So our first task is our power and energy analysis, and our second set of tasks is our model development. So for power and energy analysis, these are simple things like designing the actual test plan itself, getting the board set up and doing the actual testing, and then going through and analyzing our data. For our model development, that initially started with we were attempting to get our pre-made models onto the board and functioning. We decided to move away from that in the effort to save time as well as make it a little easier to work with. So we moved into working with Python and C, and that also included getting the models themselves to operate on the board. So that means that they're fully functional, they can go through, we can do the testing, they can do the image classification using the boards. So for our project team responsibilities, we've broken down into, for Matthew Costello, he is both the project manager and the lead for the development of the actual code itself. So he was responsible for initially trying to use the DNNs to work on the board, but after we decided to move away from that, he was responsible for actually creating the models in Python itself, and then moving it into C, making sure it worked with it. Garrett Giverson was the lead for embedded implementation, so you can kind of think of that as getting the board set up properly so I can run. So he was working primarily with setting things up such as the memory and clock frequencies, as well as the clock divisor, and making sure that we were within the specs. And then I, Charles Reeder, I was responsible for the power and energy analysis. So I developed the actual test plan. I worked with Matt Costello specifically to get the models onto the board, and then we were using our benchmark software to actually do the testing. So for our project schedule, we kind of follow our WBS. So we have model development and power energy. So for model development, that began actually back in June, where Garrett Giverson was working with Dr. Shaw on working with the pre-made DNNs and attempting to get them on the FPGAs. So we stuck with that for a while, and then somewhere around October of last year, we decided to move away from that. And that's when we moved to the second phase of model development, where that was where Matthew Costello was working more with Python to create our own custom models. And for power and energy, that didn't really begin until last October as well, because we didn't have the DNN model set up yet, so obviously we can't do any power and energy measurements. So that began, once we decided to move away from the pre-made model, we began to get at least some rudimentary data that we can start taking. And then we really got the models finished up over winter break, so then we can begin to evolve the power. So for our deliverables, we kind of have 2 main things. So our first thing is obviously the models themselves, right? So you can think of these as the AI that actually classifies the image for you. But these are what you put on the board themselves. They take the image, analyze it, and give you your classification result in that set. The second thing is all of our information as well as data and anything that we learn. So obviously you're going to get a presentation as well as all of our figures, so what our actual measurements and our tables and everything, as well as some important information in the report on how it actually functions, what it's doing, different functions that we personally use, some more of the background information that might not be otherwise available.
So now we're going to talk about the design and some test results we had for our models. So last semester in December, we presented these models in this table where we had 3 CFAR 10 and 3 MNIST models. And just as a reminder, the MNIST models test on images of handwritten digits, black and white handwritten digits, and then CFAR 10 trains and test on images of like everyday objects, so like cats, dogs, birds, stuff like that. And our biggest issue we said last semester was that our CFAR 10 model accuracy was way too low. So a major goal this semester was to increase that accuracy. And in order to increase that accuracy, we had to look into different layer operations, which is like, this is the type of intermediate calculation that's going on in the DNA. So last semester we used what's called a linear layer operation, which is basically just a matrix multiplication with those weight parameters. And obviously that did not give us good results, so we looked into another layer operation called a convolutional layer operation. And you still use a weight matrix, and it's going to be slightly smaller, and you call it a kernel or a filter, and you can see it in the diagram here. And what you do is you overlap this kernel on your input values, you call it an input channel, and then on the corresponding overlapping values, you perform a sum of product operation, and that sum is going to go to your output channel. And you slide this kernel across the input channel, and every time you move it, you do that sum of product, and every time that sum goes to your output channel. That's how the operation works. So using this convolutional layer in our CFAR10 models, we were able to get significant increase in accuracy, around 27%, which is very significant for DNA testing. And we should also note that we still use the linear layers in the CFAR10 models. It's just that we start off by using the convolutional layers, and then we end the model by using those linear operations. So the final model is going to look something similar to this diagram, where the first few steps are going to be convolutional operations, and then at the end it switches to a fully connected, but you can also call that a linear operation. And another thing we should know, in between these convolutional operations, we use what's called a max pooling operation. And that max pooling operation is used to basically reduce the dimensions of these channels, so you can see how the squares get smaller. Those squares are the channels. And the max pooling reduces the size and the number of computations you have to do in the intermediate of the DNA output.
So for our testing plan, we kind of broke into 3 primary phases. So phase 1 was the actual programming of the board. That was where me and Matt took the models that we were going to run, put them on the board, and then we also worked with Garrett, and Garrett was primarily responsible for helping us get the actual board set up right. So that was the board parameters, different things, clock, memory frequency. The second stage was actually running the models themselves. So that was when we actually took the DNNs, fed them the data sets, and had them go through and actually do the image classification. Then we took those results out, and then we did our analysis. That was our third phase. So we used the software called BenchView, and we were primarily concerned with voltage, current, and time, and we would go back through and use those to find our things such as power, energy, those various things. So as you can see here, so here are some of our endless model results. You can see on the graph there that there's the 5 kind of broken up layers. So what each of those actually are, those are the intermediate calculations between the weights. So as Matt earlier explained, you can see that there was the round weights, right? And then there was also the lines connecting everything. So with all those different lines are actually the intermediate calculations that we actually do ourselves, right? That's where the model is actually effectively working, right? So, and another thing that's important to know is with the endless model, Matt also said, the data is much simpler, right? They're handwritten digits, so they're a much lower variety, essentially, of what the computer is looking at, which is explains our much higher accuracy, as well as why it's much faster at doing the execution. Now we'll go into our CFAR10 model result. So you can see here, these are the more complex images. These are real live images, right? So things like cats, dogs, vehicles. So they're much more complex than just numbers. So we saw a very large dip in accuracy, as well as a massive increase in execution time when we tried to move to this. So same thing here, and you can also see that the blocks of calculations shrink as time goes on. That's related to those with max pooling, as well as just by the way the operations work. As we go on, we actually have less and less numbers, so that's why it almost seems like it's not that the model is speeding up by any means, there's just actually less calculations that we're doing.
So now we're going to talk about the conclusions you want to keep in mind when deciding which one of our DNNs you would want to run on a embedded system. And the first conclusion is that increasing the number of computations is going to increase the execution time. Charles was just talking about that. And here we have 2 tables from 2 different MNIST models that we tested, and they both have a different number of layers. So this bottom one has more layers than the top one. And you can see that there's 2 ways to increase the number of computations. You can either increase the number of computations between the layer operations, or you can just simply increase the number of layers in your DNA. So if you're looking at this bottom table, you can see that the more computations you have, the longer it takes to run. And when you're comparing between these 2 tables, you can see the overall execution time to do all of these layers is around 15, 16 seconds. And when compared to the smaller model with fewer layers, you can see it only takes half a second to run overall. So when you have more layers, it's going to be a longer execution time. So when you have a longer execution time, you would expect an increase in accuracy because you're running a larger model with more computations, you would expect better accuracy. So that's actually something we do by design. And here's a plot of the MNIST and CFAR10 models that we had from last semester, and this shows that as we run larger models and they take longer to run, you're going to get an increase in accuracy. Now, there's an obvious trend of diminishing returns here, so if you keep making the DNA larger, larger, and larger, you're going to get massive increases in execution time and only slight increases in accuracy. So you can only go so far by increasing the number of layers.
So knowing that fact that we can't just continue to make the models themselves bigger to actually kind of essentially solve our problem, right? So what we did is we kind of moved to an alternate strategy, which is where we began examining various different types of layers, right? So as you can see here, these first 3 results were actually when we were doing the CFAR10 models solely with those dense linear layers, right? So those are kind of like the most basic DNN layers we could use. And you can see there, we couldn't get above really 45 to 50% accuracy, and the time was quickly becoming extremely high. So we decided to look at using convolutional layers, and as you can see for that last one there, that's where we actually introduced the use of convolutional layers, and you can see the very obvious massive spike in our accuracy, and there's really a very negligible increase in that execution time, which means we were getting far better accuracy with a similar computational load, which meant that overall the model was effectively just better.
Lastly, we concluded that decreasing the clock frequency does decrease power consumption, but leads to an overall increase in energy. We have 2 tables here, one where the clock is run at a higher frequency and one where the clock is run at a lower frequency. And as you can see, the average energy consumption is decreased, but you'll notice that the image time is increased, and that turns out to be the dominant trend, leading to an average increase in energy consumption. So we suggest to just run the clock at a higher frequency. And now we're going to talk about costs and what we learned. For costs, we plan to spend only $50 on test cables for testing the board. However, we ended up spending 5 times as much because we wanted a spare board and a spare micro SD card. Thankfully, the test cables were less, so we ended up spending 5 times less with respect to the test cables. For risks and opportunities, we get significant accuracy degradation when going from designing the DNN on a general purpose computer and testing it on the embedded system. We could also use pre-made models, but a lot of the time they were incompatible with the embedded system. Opportunities, we could increase the accuracy of our models by either packing more layers into the model or using various types of layers. Some lessons we learned, the pre-made code for DNNs on embedded systems was hard to come by, and whenever you did find it, it was most likely incompatible with your board. So some advice we suggest, looking into PyTorch and C++, so that way you don't have to design your model in Python and move it to C just to run on the board. And we also suggest to look into utilizing the FPGA fabric that's inherent to the processor. What the FPGA fabric will allow us to do is to parallelize the multiply and accumulate calculations, which is the majority of the computations in the model.
Are there any questions?
Faculty, any questions?
So when you were measuring your time that you computed and that, did you do a comparison between because you said you tested things out using a computer, using a PC versus the FPGA board. Did you do a comparison in those times?
Yeah, so it's going to be, the execution times is, we do have some data for that. It's not in this presentation, but we provide a report as well. So that would be part of it, where the execution time on the board is significantly slower because also on a desktop you can enable multi-core operations, which increases the execution time a lot. And the embedded system we use has dual cores, but I think we're only running a single core program, so it's going to be much slower on board, and we do have comparisons of that in our report.
When you switched over to the convolution-based model, did you notice a change in times?
Yeah, so the convolution, so it's not so much different layer types take longer, it's more about the number of computations. So the convolutional layer that we implemented was going to have more computations than the linear layers we were using before. So it's going to take slightly longer, and as we saw here, it does take slightly longer once you're using the convolutional layers, but it's more so about the number of computations. So it's slightly more computations, but a lot larger increase in accuracy.
Okay, so basically you were doing a trade study between speed and accuracy in that, at that point.
Yeah, and that's what we're always trying to optimize.
Yeah.
Okay.
Two simple questions. Number one, how do you define accuracy?
So these data sets here, they come with a training set and a testing set. So you do the DNN training on the training set, and then when you do the testing, it has specific images that you're meant to test on. Because you don't want to test on images you trained on, because that eliminates any sort of bias it may develop. So it's doing a 10,000 images for both data sets, and it's just a percentage of the accuracy. Did it get it right? Did it get it wrong? What percentage of the 10,000 for each data set?
When you see right, I mean, like you can identify if it's a horse, you can identify it's a horse.
Yeah, so it would be like, it would say, okay, there's 10 categories in CFAR 10, and it's like dog, and it would be like dog, bird, cat, and then what it does is it uses a label. So say that if there was only 4, in our case there's 10, but say if there was 4, if this was dog, cat, bird, and truck, and it wanted to say it was a dog, it would have the highest value for a dog. So by having the highest value for that category, that's its prediction. And
so give us one quick application of your work.
so for applying this work, we would want to apply this technology of image classification. So if you have, like for IMNIS, it was used for like checks and stuff. So if someone wrote out a check and you wanted a computer to register what the person wrote out on the check, you would need to classify these numbers. So the computer would know, okay, this person wrote a 7, a 0, and 8.
One slightly more complex, if I could just figure this out. So, you know, real time, this is definitely not a real time application, right? Because
Not in its
so
current state.
what's the difference between your work and the actually real time, for example, face recognition of those technologies?
So the difference with us is that we're putting this on an embedded system which has limited resources. So like the image recognition would require a much more powerful processor and implementation. So we were trying to get this to work on an embedded system. And like I said, with the embedded system, it doesn't have to work on the internet. So we were thinking somewhere where, you know, there's no internet, there's limited resources, there's no wall power, so it would be battery operated. So the resources are very limited. So we made sure that the scope of what we were actually training our models on was more limited. We just wanted to focus on getting this technology onto an embedded system.
Something like a handheld scanner or reader, that's...
Yeah, or something like that. Like if someone was working somewhere and they needed to scan a label with a barcode and there's numbers on it, you just do maybe image recognition there. It's not a barcode reader, but
You showed training on what would be handwritten numerals. So they got another thing where you showed images of like a cat and other things like that. So can you also do the same thing with faces and stuff like that?
yeah, and that's a big thing with faces. So the reason we didn't use faces because of the ethics actually. So we didn't want to be using data sets that just has like people's faces on there because we were worried about like any privacy issues and stuff like that. And we didn't want to get into that.
No, I understand that, but I'm just saying, it is another thing that it can be used.
That is a big application of it. Yes.
I'm going to put a stop. If you want to talk to these gentlemen later, please do so. Thank you very much. Isn't it too bad that they're not excited about their work? What's also interesting as an instructor to watch the senior class work together is that when we do our practice presentations every week, just to do a status, all the project teams start asking each other about what's happening. And it's a very, it's a neat concept. So thank you, gentlemen. Okay, pardon me. I'm also going to make the announcement. The teams do give your presentation. Try not to wander past that little line and stay back here so that we can see you as we stream. next presentation is the germanium tin-based team that actually was making, designed, and made an infrared photodetector, something that was very difficult to do. And this was the basis for the Morton paper that the team won third prize.
Well, good morning, everyone. I would like to thank you for all coming out today to join us for our senior project presentation. For a quick introduction, my name is Kyle Rossler. I'm the project manager for the germanium tin-based infrared photodetector. I'm joined along here today with my group members, Penny Carpenter, Rachel Menescus, and Andrew Paul. I would also like to say that we have our fabricated devices out in front of us. If you'd like to see them afterwards, please do come to us and we'll show you. So, without hesitation, I would like to talk about the problem that we are tackling for our project. As of right now, the current market for infrared photodetectors is dominated by group 3-5 alloys. These alloys include indium phosphide and gallium arsenide. Now, when we refer to these alloys, we refer to where these elements are found on a periodic table. For instance, gallium is found in group 3, and arsenic is found in group 5, hence gallium arsenide being a group 3-5 alloy. Now, these alloys have a plethora of applications. However, these are currently not compatible with the current silicon CMOS technology, such as microchips that can be found in your PCs. And this incompatibility brings up the cost for fabrication, and therefore increasing the market value for these infrared detectors. Now, this leads me into the objective of our project. What we wanted to do for our objective for the project is to explore an alternative for this problem. Specifically, we wanted to look into a group 4 alloy called germanium tin. Now, this novel material has gone through vigorous research and studies, and based on the studies, germanium tin is operational in the near to short infrared wavelength, can be silicon CMOS compatibility due to it being a group 4 alloy, and it has a high photo gain. I'll talk more on photo gain later. Now, stepping back for a second, I want to talk about what's our motivation for doing infrared photodetectors. Well, infrared photodetectors are used in our daily lives, and we might not even realize it. We use them to take physical inputs from the real world and commute it, or to put it into the digital world and use that as information. For instance, let's say you want to watch some television. Take the TV remote, you press the power button, and the TV turns on. What you just did was press a physical object, the TV remote sends an IR signal to the television, with the television then sends the IR signal, therefore causing the digital output of the TV turning on. You can think of it as this laser pointer right now. Every time I change the slide, it receives the IR signal, turning the next slide. Some other applications than just televisions and laser pointers is LiDAR. LiDAR shows a huge promise for the autonomous vehicle. The process of sending light being reflected by, let's say, oncoming traffic or walking pedestrians, and using that information to get an understanding for the environment around it. Another application is optical fire. Quantum computing has seen a huge surge in popularity from countries all over through its promise in quantum computing. Now, quantum computers use optic fiber communication, which is the process of sending light to send and receive information, and we can detect that information using IR photoconductors. Some other applications can include cameras to take pictures with your friends and family to make memories, and thermal imaging, which can be used for security reasons to set any outsiders from trying to break into your home at night. Now, going into some of the requirements and specifications, obviously, as I stated before, we want our infrared photodetector to be operational in the near to short infrared wavelength. That would be from 1.2 to 1.55 micrometers. And ideally, we wanted our detector to conduct a maximum photocurrent. Now, when it is exposed to IR radiation, it conducts a higher photocurrent, and photocurrent is dependent on a thing called photo gain. Now, photo gain is the multiplication factor that goes into what photocurrent is, and a parameter that it depends on is the excess amount of electron-hole pairs from excitation. Now, if we wanted to increase our photo gain, a parameter that we looked into is the electrodes. Now, for our electrodes, we have decided to design a finger-like pattern. These fingers are interweaving with one another to stack on top of each other. And in order to increase our testing pool, we have designed multiple patterns of electrodes, which are being 50, 75, 100, and 200 micrometers. The distances I have just listed are the widths of each finger and the distance between each finger as well. And the electrodes need a home. The electrodes will sit on top of our devices, which is called the mesa. For our mesa, we have defined our mesa to be 1.6 to 1.8 millimeters. And with our project being mainly electrical engineering, all of our standards were going to be electrical. We have chosen our standards and our code of ethics from IEEE. Our standards pertain to measuring and characterizing our devices as well as safety. Safety is a huge factor that we have to look into when working with IR radiation. IR radiation is harmful to the human eyes, which can cause permanent blindness. So while working with IR radiation, we made sure to take safety seriously.
So some constraints for our project include manufacturability, sustainability, and ethics. For manufacturability, we want to make sure that if there are any successors to our project, that all the processes we do have a strong repeatability to it. This is something that's crucial for industry. For sustainability, we simply want to minimize the amount of material we're wasting by maximizing the amount of devices per wafer. For ethics, we of course want to make the devices safe for all kinds of consumer usage, as well as making it harmless during any of the fabrication processes. Here's the list of deliverables for our project. These can include the simulations that were done in the first semester for both silicon and germanium tin, as well as the masks that were designed and fabricated. We want to fabricate operational silicon and germanium tin devices utilizing the microfabrication lab that we have here on campus, as well as developing a robust apparatus that is going to be able to characterize and measure the devices and their photocurrent. For the test plan for characterization, we use the Pasco interface as well as a 2-pin probe to complete our circuit. For our light source, we used an infrared flashlight that operates at 940 nanometers. This flashlight also has the ability to vary its light intensity. So the goal for this is to measure the difference in current for the devices when the flashlight is on versus when it is off. The success for this would be that the germanium tin devices have an overall higher photo gain compared to that of the silicon devices, and a failure would be that the measurements we do are overall inconclusive and don't really have any kind of correlation to them. Some risks that we had to take into account when we were doing the testing is any damage that could occur to the devices and or the equipment that we used, as well as any safety precautions that we need to take into account when working with IR. Our WBS summary highlights things such as the devices and their photocurrent, simulations and measurements, as well as the overall fabrication process. These things can be looked into further detail in our project schedule, which the project schedule, as derived from our Gantt chart, starts with research so that we can gain a solid foundation for our project. We can then move into our trait study that we did, which is the simulations for. Once this design is done, we then send it out to a manufacturer so that once we receive those masks back, we can start the fabrication process. Fabrication for our project took a majority of the time just due to some issues that came up and the time it took to troubleshoot these issues. Once these issues were resolved and we could then move on into the final steps of testing and measurements. Here is the OBS summary. Throughout the entire school year, each member was hands-on for the whole project. However, this OBS just gives more specific responsibilities to each member of the group in case issues were to arise and clarification was needed. In the green squares, simply show what task was given to which member of the group. For our cost, the initial cost estimate was sitting around $700. However, due to mechanical restrictions that we had in the microfabrication lab, we ended up having to outsource the metal deposition process to Penn State University. This ended up bumping our final cost estimate, or our final cost, up to around $1,730.
So last semester we spent majority of the time running simulations
dimensions for our germanium, tin, and our silicone. So when we were done with fabrication, we would have a baseline of where each device was going to sit in its respective wavelengths. We tested different things such as concentration, depth, electrode placement, and wavelength. And what we found that germanium tin was able to absorb a broader spectrum of light compared to silicone. So for our design summary, we started fabrication at the beginning of the semester. We were actually able to fabricate a fully functional germanium tin wafer as well as a silicone wafer. And for our specific process, we started out with 2 rounds of photolithography. The first one to put our mesa down, the second one to put our electrodes down. We ran a dry edge on our silicone wafers, and we decided that after that we wanted to do a wet edge on our germanium tin wafers. As Kane said, we ended up sending our wafers out to Penn State to complete the metal deposition process. And once we got those back, we performed the liftoff process in our fabrication lab. A few highlights from our fabrication process. So instead of in class when we cleaned our wafers using BOP and SE1, we decided to use an ultrasonic vibration technology to provide a faster clean and allow us to get into the process a little more quickly. The second picture was our results after our dry etching of the silicone wafer. We just wanted to point out the defined edge of our mesa. The third picture was our ice bath for our wet etching process. We ran that at 4 degrees Celsius for 20 minutes, and it had a 5 to 1 to 1 ratio of DI water, hydrogen peroxide, and hydrochloric acid. This had an etching rate of 50 nanometers per minute. The fourth photo was our finished result of our silicone prior to sending it out for metal deposition. This specific picture shows our 75 micrometer electrode. And the final picture, so we ended up having to switch our photoresist from a positive to a negative. So that required us to test different development times in order to find the perfect spot of how long we needed to develop our wafers. We did run into a few problems with fabrication. To start, our metal deposition machine in the fab went down, so as we said, we had to outsource it to Penn State. We also ran into a few issues with our photolithography process where we were using an auto aligner compared to doing it by hand like we did in class. What happened was it provided an inconsistent light source, so we actually, when we were putting our electrode mask down, we had to switch back and do it by hand. We also found out that we were using an expired photoresist, so that, as I said, that required us to switch back to a negative photoresist instead. And then lastly, when we were etching our wafers using the plasma machine, we found that we etched them for too long, and we actually burnt our photoresist onto our wafers. To note, the right picture shows us we actually did attempt to do our own metal deposition process before figuring out we had to send them out. What we found was the gold that we were using wasn't easily spreadable and ended up just leaving a puddle right in the middle of the wafer, which is why we decided to send them out. And these are a few pictures from our fabrication process. On the left, that's our CAD render of our mask. On the right, you can see our final design for one device. As you can see, they're pretty similar, which is obviously the goal we are going for. And along the bottom, there's the 50, 75, 100, and 200 micrometer electrodes. What we found that when we did the germanium tin, our 50 and 75 micrometer electrodes, were not as clean and clear cut on the germanium tin wafers compared to our silicone wafers.
So above me are 2 different pictures. On the left, we have a circuit diagram of our schematic, and then on the right is a real-life picture of what we have of our testing apparatus. You can notice that the voltage source and the ammeter are run through our Pasco interface, as well as this separate circuit is very simply the IR flashlight that was mentioned before, which is here fixed above in the picture is shown as our silicon wafer. We have our two pin probe onto our wafer on our microscope. So above me are some of the testing results for the silicon wafer. Notice for our 200 micrometer, we actually have an increase in current when it's exposed to infrared, and then somewhat strangely, for our 75 micrometer silicon, we actually have a decrease in current through our system when we're exposing our devices to infrared light. We had, similar to the 75 micrometer, we had similar results for our germanium tin across all of the electrode sizes that we were able to test. Again, this is not what we were expecting, but we believe that we were able to figure out what was going on. So what we were expecting was the simple case of ohmic contact. Ohmic contact is when there is no barrier between the conduction band of our semiconductor and the metal on the electrode. This allows for electrons to flow very easily from, as I said, our semiconductor to our metal electrodes. However, what we did see was what we call a Schottky contact. So notice that there's this potential barrier here. This potential barrier makes it difficult for electrons to travel from the conduction band of our photoconductive material onto the electrodes. So this Schottky contact, as I said before, it has this energy barrier. So because of this energy barrier, what happens is there's a collection of electrons at the electrode, and while opposites attract, like things repel. So because there's this buildup of electrons at the electrode, these built-up electrons will actually repel the newly generated electrons or holes, respectively to each side. So in general, we want the transit time of our electrons to be greater than our extraction time. To define those for you, the transit time is the time that it takes for an electron to travel from one electrode to the other, while extraction time is the time that, well, once at the electrode, how long is it going to take for the electron to then tunnel through the electrode to the rest of the circuit. The reason that we want the transit time to be greater than the extraction time is that by the time we have our electrode travel, or our electron travel from one electrode to the other, we want to, that's the transit time, we want that, by the time that happens, we want there to be no buildup at the electrode. Silicon has a higher transit time as compared to germanium tin, so that's why when we looked at the 200 micrometer finger width, we were able to see a positive gain in current. There's an increase in current because there was less carrier repulsion occurring. Silicon has higher both due to its carrier mobility as well as the larger electrode distances where we were able to see a positive increase. Two things that we didn't test throughout our testing process were temperature and dopant concentration. While, because they were not tested, we were not certain. If we were to decrease the temperature, we hypothesized we may have been able to see better results such that decrease in temperature decreased the electron mobility, which would then decrease the chances of carrier repulsion happening. So, in summary, some of the lessons that we learned throughout this project are the importance of trade studies. We did lots of simulations at the beginning of the fall semester to understand difference, variation of electrode placement, variation of wavelength, etc. We also expect the unexpected. We can look at that in two different ways. Expect issues to arise and make sure that you have time allocated to troubleshoot those. As also, don't be surprised if you see something that you weren't quite expected to see. In our situation, that being the carrier repulsion rate, we were expecting to see an increase, but most of our testing showed otherwise. And then, of course, germanium tin is a viable infrared photodetector. What we could have done differently, we could have made the mask larger to account for undercutting. We could have better documented our process just to help specifically with our presentation part and the administrative side. Improve budgeting and to stay on top of the schedule to make sure that when those issues do happen, it doesn't totally derail the project. And then if there was any team that would like to follow on our project in the coming years, you can vary the germanium tin composition. Depending on the composition of germanium tin affects its band gap properties, or you can explore another alloy entirely. You can explore different wavelengths, or we can measure under different environments, as I mentioned, the temperature. Above me is a list of courses that we used. This is a capstone project, so of course there's lots. I would like to highlight EE271. That's our semiconductor devices course to give us a strong foundation of a lot of the theory that we're learning about. Of course, EE381, our microfabrication lab. We spent many hours downstairs in SLC 10 and 22 actually fabricating these devices, so that gave us a great understanding of general concept that we need to step through, as well as Physics 203, in which we explored the photoelectric effect, and we had, again, more principles and understanding of what's going on. We would like to acknowledge Professor Taylor, Dr. Dew is our advisor, Mrs. Vicki Stapleton, the office assistant, helped us with the paperwork, Mr. Mike also helped us through the fabrication process, and of course our EE classmates and family to brainstorm ideas and support us. Thank you for your time. Are there any questions?
Ian,
For your fabrication process, why did you put it in the ice bath?
ice bath, so that has to do with wet etch. So for the wet etch, we use a 5:1:1, which is DI water, hydrogen peroxide, and hydrochloric acid. The wet etch was used for germanium tin because if we were to use with a dry etch, that would potentially damage our actual devices.
Back to any questions?
One comment first. Excellent use of the word clever. Very good. You had made a comment at the end about temperature.
Yes.
Okay, and do you think temperature was part of the reason why you were the results that you received what you got?
Yes, so when we made our measurements, we did a room temperature. If we were to have a cooler environment, this would have changed the carrier mobility, hence slowing down the rate at which they travel across for the transit time and the extraction time. If we were to increase that transit time, then we could have seen different results of a positive photogain rather than a negative or a loss of current.
Have you done any research into how a near IR detector device is used in real-world application today?
I have. So, for instance, quantum computing uses optic fiber communication, which is the process of splitting photons, entangling them, and measuring, which is quantum cryptography.
So if you were to go look at a near IR camera, what's inside a near IR camera is a Peltier device. It takes that detector and cools it down, so you get better performance on it. So I think if somebody does future work on it, something that they definitely need to look into to get better results. But I think very good job. Thank you.
Could you go back to your 2 plots?
Absolutely. These two.
So what's the main advantage of your design compared to traditional silicon-based device?
Could you repeat the question?
What's your main advantage of this device compared to traditional silicon-based?
So the reason why we use germanium tin is that it can actually, it has a better responsivity to infrared range. So we originally intended to use a laser diode in our testing that would operate at approximately 1.5 micrometer wavelength. However, that laser diode that we received was inoperable, so we had to use a shorter wavelength infrared flashlight, which was at 940 nanometers. At 940 nanometers, both silicon and germanium tin are responsive to that wavelength. However, if we were to just increase to slightly longer wavelength IR waves, silicon is not responsive to that, whereas germanium tin is.
Okay, so based on that, from those 2 plots, could you tell me, like you actually see the advantage, is there any information here to show you that, or prove that, like in those 2 plots?
In these 2 plots, not necessarily. We do have in our appendix, we have this intensity absorption versus wavelength, where, as I said again, we were tested. So we originally wanted to test here with our laser diode. Our laser diode, as I said before, is inoperable. So when we were looking for alternative light sources, we found an IR flashlight, but it was only at approximately here in wavelength. So that's why we were still able to see results from our silicon that were.
So for those 2 plots, I really like those 2 plots. That's why I keep asking this question.
Of course.
So what advantage could you see from the second one versus the first one?
So the first one I have to do with the electrode placement. 200 micrometers might have been a sweet spot for getting the transit time, iterative time for the electron hole pair to be extracted by the electrode. And for the 75, the distance might have been too small, giving a negative photo loss, you could say.
Could you see that from your second plot?
Yes, so if you were to look here, we actually had a difference of 7 milliamps. So when the IR was on, we actually had an increase in photo current. When it was off, we actually had a decrease. That's a whole wave function. So if we looked up to 75 and we have the photo IR flashlight on, we actually have a decrease in photo current.
Thank you.
Yes, Dr. Sweeney.
You tell me what was the relationship between this voltage and the number of the fingers? Those fingers that the particle was the
You said the relationship between those fingers and the voltage?
Yes, that voltage and the number of the fingers in the photodetector.
So when we are applying different biasing to our circuit, we notice a pretty similar relationship across the board. So when we applied 1 volt for our power supply, we saw a very small potential difference across the photodetector. So over when we did different power supplies for like 0.5, 0.75 volts, we noticed a pretty consistent line of potential drops. So we have a linear relationship, I would say, for when we apply our power data.
That was why we made our mass like the 50, 75, 100, and 200. So when we went to test the different voltages, at each point we were able to see the difference, like with comparison to comparing the width to the voltage.
Great. I'm going to try to call time. We're a little behind. Thank you very much. Our schedule calls for a brief break, and then we'll do an introduction to the combined electrical engineering, mechanical engineering presentation. So let's go ahead and take about 4 minutes and so, 10 after. Please come back in. Thank you. This is the one that came in. This came in at 2:30. I'm glad to see you. Oh, you. I like to bring it at least Again, welcome back. Welcome to the mechanical engineering group who have come in. We finished our electrical engineering section, our pure electrical engineering section. I would like to welcome all of the visitors, graduates of Wilkes University engineering programs. Thank you for coming. We appreciate that. Thank you for family and other industry visitors for coming. I think it's these are great events for all of our engineering students to be able to present what they've done and spend an entire year doing. So, Dr. Bednarz, the mechanical engineering group.
Okay, yeah, well, welcome to our mechanical engineering students, guests, and our faculty. So, as Professor Taylor said, we're moving into the joint MEEE portion. So you see the groups coming up this morning, right before lunch. And here's our time interval. So what I'm going to do is I'm going to set the timer for the first two groups, the joint MEEE groups, for 18 minutes for presentation time, and then you have 2 more minutes just to wrap it up, and then we'll have 5 minutes for questions to try to keep us on schedule. And then moving on to all subsequent ME teams, I'm going to set the timer for 13 minutes initially, and then you'll have 2 more minutes to wrap it up, so 15 minutes total. And then 5 minutes for questions. So I'm going to do my best to keep us on schedule. We got a lot of groups to get through, a lot of great groups, and hopefully we're out here by 3:45. That's my goal. And for any faculty, if you haven't already done a grade rubric for my son Eddie, you can pass them out. So it's a very simple rubric: just presentation organization, presentation execution, amount of work done, design completion, prototype and testing. So 20 points. Up to 20 points for each category, 0 worst, 20 best, to your best discretion. So for the 392 groups, you should see completed prototype and testing. They should have their product completely finished, so evaluate them all the way up to this last column. The last 2 groups of the day are going to be ME 391 groups, where they still have 1 more semester to go. Their goal for this semester was to complete the design, and then come fall, we're going to finish the prototype and testing. So you don't have to evaluate them there. They'll be graded out of 80 points, these last 2 groups, and the first 11 groups will be out of 100 points. So that's just the grade. So here's our schedule. So I think we're ready to go. So, okay, so we're going to pick it up with wireless deep body implant charger.
Well, good morning, everybody. My name is Ian Petro, and I am the team leader for the wireless deep body implant charger. I'm joined up here with my EE colleagues, CJ Lee, Gabriel Crowley, as well as our mechanical and biomedical engineer, Nicholas Surgeon. So for our presentation, we have a lot of points that we're going to be covering. Firstly, we're going to be talking about our problem statement, the documentation of our project, our antenna simulations, our fabrications, and the measurements we perform. We're going to be looking at our rectifying circuit, the thermal analysis, the case design, our project conclusion, and some concluding remarks. So as it stands right now on the market, there's a lot of different types of implantable devices, but they all share a common flaw, and that's that they have a finite battery lifespan. For pacemakers specifically, they have a lifespan of between 5 to 7 years, or 5 to 10 years with advents in technology. So whenever the pacemaker battery expires, so might the patient. So an expensive and potentially dangerous surgery is required to replace that battery. So the objective of our project was to design a system capable of wirelessly recharging a battery while it's still implanted inside the bone. Because as we can see, these replacement surgeries can come with a lot of complications between the wound not closing all the way or the medical professionals creating some type of issue with the actual pacemaker leads. Because 1 out of every 100 replacement surgeries results in a lead failure, so they have to go back in and fix the mistake that they did.
So as some of you may already know, our project is a continuation started by a group last year. So although we're taking our second
project. We didn't take too much from the prior group, or we wanted to start fresh. We did, although, examine all their results and learn from their mistakes, so we knew the best way to go about our project moving forward. Two of our biggest takeaways were to not try and 3D print our mask, or wouldn't get the right precision and resolution given the small size of the antenna that we're working with, as well as we just made sure to very carefully think about what components we will need. They happen to purchase a few components incorrectly that would not have worked come time to do your full system fabrication and testing. So taking a look at the current slide, you see some project requirements listed. In order for our project to work, it must be able to transmit and receive power to wirelessly charge a battery as done by the process shown in the signal flow graph on the bottom. Being a medical device, there are a lot of things to take into account, and our whole process must be overall medically safe. A wide range of safety standards for reference to help us address these worries. Taking a look at the signal flow graph on the bottom, I'm going to give you a quick idea of how our project works if you don't already know. The signal generator will power our transmitter antenna. During the charging process, the transmitter antenna will be placed on the surface of the skin. It will pass a signal that can go through skin, muscle, and fat until it reaches an implant receiver antenna. That receiver antenna will receive the signal and pass it on to our rectifier circuit. The rectifier circuit converts the radio frequency, or RF signal, to a DC voltage suitable for charging our pacemaker battery. As I previously stated, there are a lot of things taken into account considering this is a medical device. One health and safety constraint we have is during the charging process, our transmitter antenna cannot exceed 110 degrees Fahrenheit or else it can burn the skin. We reference the National Institute of Standards and Technology to determine the temperature suitable for our charging process. So also, our components will be subjected to a lot of movement inside the human body, as well as we don't want them to cause discomfort to the person, the patron of our product, and those things tie to sustainability concerns. So, taking a look at the standards we referenced when conducting our research, the IEEE 95.1 code sets standards for human exposure to radio frequency electromagnetic fields in the 3 kilohertz to 300 gigahertz range. The second line of standards are all specific to medical applications. They govern test procedures as well as quality and risk management for medical devices. It's also very important, you can't forget the IEEE Code of Ethics. For most of us here know, you must hold paramount the safety, health, and welfare of the public. Now jumping into our project itself. Our rectifier circuit is comprised of capacitors, inductors, and diodes. Our transmitter antenna was designed to operate at a bandwidth of about 1 to 1.3 gigahertz based on our simulations. We have a 1 watt power limitation from our phase dividers, so our transmit power must now be less than 1 watt. During our last presentation, we stated concerns for our receiver antenna. Our old design was very small, and since then we have concluded that we cannot fabricate such an antenna in-house, so we redesigned our receiver, upscaling it while still keeping its size comparable to that of the pacemaker. Our old design was 7 millimeters in diameter, and now our new design is 4 centimeters, making it much easier for us to fabricate. The output voltage from our system must amount to be at least 3 volts so that we have a voltage suitable for charging the battery. Here you can see a summarization of our work breakdown structure. Our main components of work are research and design, fabrication, testing, and documentation. We'll take a little quicker, deeper look at research and design. Our various components are our 2 antenna, the rectifier circuit, and the capsule that must encase our implanted components and keep them safe inside the human body. Here's our responsibility matrix, and it shows our different tasks and the team members responsible for carrying out each part. Looking at our costs, we got all of our chemicals for free from the Wilkes University Chemistry Department, as well as our antenna substrates for free from Rogers Corporation. The rest of our components, like our phase divider, SMA connectors, we got from a variety of different sources, but in the end, our cost to date came out to be less than our fall estimate and well below our budget. For our project schedule in fall 2021, we started with the design and simulation of both our transmitter antenna and our rectifier circuit. Once we completed our transmitter antenna, we had the specs needed to go forward with designing our receiver antenna. Jumping forward to January 2022, we were able to complete our receiver antenna design and begin fabrication of our transmitter antenna and our rectifier circuit prototype.
From that point forward, everything is all fabrication and testing for us, so we fabricated all of our components individually, and then did individual testing to prove their proper functionality. After that, we were able to put everything together into a full human body model system test.
So, to simplify our simulations so that they can go from about 10-minute, or to go from about 3-hour runtime to 10-minute runtime, we simplified the model of our human body. In our simulation software, there's a library of body material that we were able to define for each brick. So for our simulations, we defined a layer of skin, fat, and then the large brick is of muscle. So the brick itself is defined from 0 to about 20 centimeters, or roughly about the entire width of the body. But the pacemaker itself won't lie any shallower than about 1 to 2 centimeters. So it can be seen, it'll be right about here. So we're getting our ample amount of voltage and our ample amount of current. The graph to your left shows the electric field, and the graph to the right shows the magnetic field. On the left, it supplies voltage, and on the right, it supplies our current. On this slide, you can see our far field simulation results. On the right, you can see our receiving antenna, specifically designed to have a circular polarization. So if our alignment is slightly off, we should still be able to receive more power than with any other form of polarization. And so going through the fabrication process was a very extentful trial and error. We went through many different processes until we found the correct recipe to get the result that we wanted. So going through the fabrication process, we start off by separating our substrate board, and we have to drill alignment holes so that we can align the mask to the front, to the back, so that there is very little difference. We take our photoresist material, which you can kind of think about like an ice cream sandwich. There's a protective layer on the top, protective layer on the bottom, and then the material in the middle is going to be a light-sensitive film, which we're able to use to transfer an image. It's a very similar process to how they do microfabrication for semiconductors. So we take our resist, we cut it into the correct size, and then to get proper adhesion of the resist onto the board, we run it through a laminator. Then we repeat steps 3 and 4 for the back side. So we have resist on the front and on the back. Then going into steps 5 and 6, we align our mask and then put it underneath a light which transfers our image from the mask to the light-sensitive film, and we can see that our pattern transfers very well. And then the asterisk signifies one more step that didn't need to be photographed. It was a post-exposure bake to really solidify the film onto the boards to make sure nothing washes off in the development step. Going into the development step, we use sodium carbonate, to remove the remaining film that we do not want. Then we put it into a ferric chloride bath to remove the copper that we do not want. Then we put it into a bath of acetone to strip away the remaining resist. Went down to the machine shop, we used the belt sander and the drill press to remove the remaining material around the edges and to drill a hole for a port, and we can see our final recipe up on the screen. So comparing our results from our simulation to our fabrication, we were able to get very good results between the two, from our receiving antenna to our transmission antenna. And the silver box, as CJ stated, is our phase divider. It is a necessary component of our transmission antenna to be able to split the phase 180 degrees to be able to send power into the body.
So once we had these two antennas fabricated, we right away wanted to get into testing. So we took the closest thing to our original model that we had, which was our partner Ian Petro. We quickly realized that that wasn't going to be the best idea for our future testing. This was just an initial test to see if these antennas were anything close to what we were wanting. They worked out well, but we quickly switched to our new human body model. So this consists of putting our transmitter up to a bag of water. That bag of water represents the human skin and fat. It has very close permittivity to that of 80, while our skin and fat is about 78. And then it went through a minced beef creation that we made to our receiver antenna. That minced beef represents the muscle inside the human body that the signal has to go through. These gave promising results. From our simulation, we knew we should have a value below -10 dBm, as is required by the IEEE standards for this type of model. Our model using Ian had almost the same thing, just slightly more resonance and slightly less bandwidth, while our model using the bag of water for our S11 had a much larger bandwidth with less resonance. But this bandwidth actually helps because since we have a larger realm to work with, we can then get it to work with our receiver much easier. Looking at our receiver, we saw 3 similar results amongst all of them. Our simulation had the largest bandwidth with plenty of resonance below -10 dBm. Our human body model, Ian, had a skinnier bandwidth but more resonance, so we would have no problem there. And then we actually got our best resonance in our actual minced beef model. Overlaying these two from our human body model, we were able to see that there is plenty of room to work with our receiver. Bandwidth lies completely within our transmitter bandwidth. That means they will be able to communicate together without any real issue. We saw the same thing with our water and beef model. Our bandwidth for the transmitter gave us plenty of room to work with, and our receiver lay completely within that, so there should be no problem with the two communicating between each other. These two antennas then feed into our rectifier. So our rectifier consists of 2 main components. First, a matching circuit, which will allow maximum power transfer from our antenna into our next part of our circuit, which is our voltage doubler. This voltage doubler has to take the RF energy that we have coming in from our receiver antenna and convert it into a usable DC voltage that we can use to charge our pacemaker. So once we had that design made, we started laying out our PCB. We used the KeyCAD software to create that design that you can see in the top corner. This was then printed using the Volterra 1 and SLC 193. This was just to verify that we could print and fabricate a circuit that small in-house. You can see the total circuit size is only roughly the size of a thumbnail. We looked at some of the kinks in that first design and created the next one in the top corner, and then went and sent it out to PCBWay for a proper circuit to be made. That design in the bottom corner is the final circuit next to the quarter, where we sent it out to PCBWay, had them print out our layouts, and then use the Volterra 1 to use reflow to attach the components to it. You can see it's only the size of a quarter. The results of this was our first real disappointment of this report. You can see in the gray, that is our expected voltage out based on our RF energy in. We're expecting around 3 dBm. We'll get to about 3.5 volts, which is plenty of voltage to charge our battery. When we actually tested this of our physical fabrication, though, we only got about 1 volt out at this same dBm. We did also test this at 1.47, as that was another potentially resonant frequency early on, and we saw more similar results between simulation and simulation and fabrication, but they were not good enough still to be used. So looking at this plot shows the connection between our receiver and transmitter antenna. So for our transmitter power in and our receiver power out on the y-axis, you can see we need about, with our current circuit design, we're going to need about 35 dBm into the circuit in order to get a voltage high enough to be able to charge our batteries. The issue with this, first off, is that in-house here at Wilkes, we don't have anything that can create a source this high at our frequency. So for one, we were never able to actually test something that high to get that high of a voltage. If we had our circuit working to our original specifications, we would have only needed about 28 dBm, which is about 3/4 of a watt. This meets our original requirements for our transmitter. Still would not have been able to be done in-house, as we could only reach a max of 18 dBm in-house, but it verifies that if our circuit was working up to the specifications, then we would have been able to charge the battery with proper input.
The thermal analysis took place by using 5 K-type thermocouples placed throughout our apparatus. Our T1, which is not pictured, is attached to our rectifier circuit. Our T2 is attached to the receiver antenna. T3 and T4 attached to the meat, and T5 is attached to the transmitter antenna. The apparatus did have to go through a little bit of a change because water and plastic, although match the dielectric properties of skin and fat, they are incomparable to that for thermal properties. Unfortunately, the testing was unsuccessful. As previously stated, the generator can only produce around 16 to 18 dBm when we were hoping for around 28 dBm. With this little bit of power entering the actual transmitter, we found that there was nothing more than 3 degrees Celsius increase in the actual apparatus. Simulations did occur using our lifelike box as previously stated, and we found that the greatest temperature was at the corner of the transmitter of 37.88 degrees Celsius. The graph to the right shows the temperature across the muscle going deeper into the actual muscle box, and it's to show that after about 40 millimeters that the temperature does return back to the normal body state of 98.6 degrees Fahrenheit. The specific absorption rate is the amount of RF energy that is absorbed into the body per kilogram. Our transmitter maximum SAR is 7.54 watts per kilogram, and it is within the FCC regulations that state for a controlled exposure partial body is 8.0 watts per kilogram. The way that the simulation calculates this is the integral of the electrical conductivity multiplied by the electric field squared over the actual density of the material being tested. The original capsule design was more matched towards our 7mm diameter receiver antenna. Now that our receiver antenna is nearly 40 millimeters in diameter, we thought it was a better use of the space to stack the receiver on top of the rectifier circuit. So as seen, the rectifier circuit is going to be placed upside down and attached to the actual support of the internal casing. This allows for the components in the rectifier circuit to be safe from any wear and tear against the internal casing. The receiver antenna is then placed on top of the support where it is open to the RF waves that the transmitter will emit. The two grounds are then connected through a drilled hole in the actual support, and the two wires shown will act as leads that connect the rectifier circuit to the pacemaker battery. So the transmitter and receiver were both successful in the fabrication and testing processes. However, the rectifier circuit was optimized but was unsuccessful in the fabrication process. Some challenges and setbacks that we did face were the reparameterizations of the transmitter and receiver antenna. We also wished to fabricate a smaller receiver antenna, as well as the multiple redesigns of the actual rectifier circuit, not being able to purchase any medical grade polyurethane, and as well as a pacemaker for any interference testing. Over the past year, we found that each part was actually very easily manufacturable within the cost-effective method, and that this is imperative for reduction in medical procedures. We also found that there's still some room for improvement, including a higher efficiency transmitter, a smaller receiver antenna, as well as any other adaptations for other implantable devices other than a pacemaker. Some relevant courses are stated above, 3 of which include the electromagnetism classes, our microfabrication classes, and heat transfer. And some of our publications include the 2022 IEEE paper contest, which we placed 2nd place, our engineering in medicine and biology conference paper, and a journal publication. And we would lastly like to thank the engineering department here for the past 4 years of experience, as well as the names listed above: Dr. Spoonie, Dr. Carey, Professor Taylor, Nikki Stapleton, Dr. Moo, Professor Greiner, Dr. Gamari, Dr. Bednars, and Lisa Colbetti for working closely with us this past year during our senior projects. And thank everyone for coming. If there are any questions, we'll gladly take them now.
Faculty questions?
I saw your plots for S11 and S22. Did you do an S22 or S1?
So for the simulation, we had a difficult time getting the simulation to run for an appropriate 2-1 because for the transmission antenna, it requires a 2-port excitation, but whenever you import a 3rd one in, it's difficult to get the appropriate coupling between the simulation. Our measurements we did, however, I don't think I threw it between the serialized.
If you did an S21, then we would have been able to see the loss of the body tissue.
Yes.
You would have had a better idea of how much your receiver antenna was getting from your transmitter.
Yeah, whenever we measured it at our most resonant frequency, we were getting around -20 dBm, where standard's around -15.
So you're getting what, -20 dBm of loss, dB of loss. Okay, so was that, and you said you were expecting -15?
Yeah, well, -15 is standard, is it not?
Okay.
Yes.
Well, first of all, I have to commend you for, regardless of whatever you had in terms of the outcome, for being so systematic in your methodical in your project. Just you checked every step that I had to kind of take for a project. So great work. In case it is successful, because I think it's ongoing, is what I hope people probably next year somebody can kind of make it more together. Does it need a special type of battery, or it can be used with the current implanted batteries in market?
So current pacemaker batteries are lithium primary batteries, meaning they're single-use, not rechargeable. That's the main problem that we wanted to address with our project. All right, 1 second. There's. So we decided that we were going to use lithium-ion batteries because obviously they are rechargeable. They can be recharged up to 500 times and still maintain up to 80% capacity.
So for those who have currently some batteries, there should be some surgery anyway to put a new battery in, and then from that point on.
Yeah, regardless, we replace the battery and then we would be putting our antenna and full system in at the same time.
And just a suggestion for future for those who are going to put in your report, you're using ground meat. If you make a burger versus steak, burger, you just need maybe 2 minutes per side. Steak takes longer. And I think real flesh is closer to it. It's not ground, right? It's not ground. So I believe we need something more realistic for future experiences.
Thank you. So there are maybe like 2 losses here. One is the theoretical communication, one is your rectifier. I mean, based on your presentation, it looks like you think the main loss is in the rectifier? But
Yes.
So did you ever try to compare the power input and output of the rectifier and see actually how much you lost there, or how much power you're using in the rectifier? Because I don't try that idea.
Yeah, so you can see, like in the gray there, that was our original simulation. So you can't exactly directly compare what's going into RF energy while coming out. We want a DC voltage. So we know what our expected is, which is 3 dBm in should be getting us 3.5 volts out, no problem. While when we actually measured that, that's what's in the yellow. We were only getting around 1 volt, really just under 1 volt out. So that was our comparison was between our RF energy in to our DC voltage out.
So you believe there's enough power goes into the rectifier?
Yeah, with more power in, so that's also what we have with this slide. That's showing what the transmitter and receiver is coming out. So on the left there, those equations, that's top right, I'm sorry. That equation is what actually shows if we had 35 dBm going into our transmission antenna, our receiver antenna will receive enough for us to be able to charge it. Our issue with that is that's higher than our specs. Our phase divider for our transmitter can't hold more than 1 watt. However, if our circuit was working up to specs, we would only need about 3/4 of a watt coming into our transmission antenna in order to get a high enough.
So the main reason is because the rectifier is not efficient enough?
Correct.
And another solution that we could have is improving the gain of the receiving implant.
But there's a limit with what we can do.
Okay. Thank you for your question. Thanks.
Slideshow we put together just showcasing everything we've gone through this semester. as you can see in that quick little video, we've gone through a lot this semester, and if we compare last semester, this is our final render of our design compared to the actual product that we have produced. And so to quickly recap exactly why we're doing what we're doing, around 30 million people around the world are in need of a prosthetic, and 3D printing is a perfect manufacturing method for this because of how customizable it is for the user. And so we set out to build a large form factor FDM or fused deposition modeling 3D printer to be used for rapid investment casting and printing of non-structural prosthetic components. It is because of these industries that we wanted to reach a build volume of 610 by 610 by 914 millimeters. When compared to some commercially available printers, such as this Modix Big 60 here, our printer is actually larger in size.
So WAM's objective is to design and develop a large format 3D printer for the investment casting, silicone molding, and silicone molding prosthetics industries. Basically what this means is with our printer, you can print in one day your model, go straight to casting like you can see here, and dip it right into your solution, burn it out, and you can go right to cast. Or you can do something like over here with silicone molding.
So getting into some of the specifics of our project, we required that it run on a 120-volt AC 20-amp circuit, and based on NEC standards, we wanted to make sure we didn't load to any more than 80% of this circuit. We wanted our heated bed to be partitioned into individual pads, each of which can be controlled manually, and we also needed our printer to run on Marlin, which is an open source firmware that we will discuss later on. As for some specifics, we specified that our each pad will draw no more than 200 watts at any given time, and we don't want our stepper motors to draw any more than 90% of their current limit.
So some of the key constraints and standards we have, obviously safety. We don't want anyone to get hurt while using our printer. Manufacturability, how easy is it to make? Can we get parts? Sustainability, if it were to break, could you just 3D print a part? Could you buy it easily? Is it accessible? Economically, we want it to be available to most consumers. We also have some of our standards here. We have the NECE standards for electrical connections. We have ISO and OSHA standards for safety and health, our ASTM standards for our materials, and then lastly we have ANSI, ASME, and IEEE standards for drawings. One of the ones we want to point out is our ASME standard, B18.3-1998. That's the first time that FDM was defined in a standard. So ethical considerations. Obviously we're going to look at our ASME, NSP, and IEEE. One of the very important ones that we saw was through IEEE down here, which was to give and accept honest criticism to your teammates, to other teams, and anyone that would come in contact with.
On the left-hand portion of the screen here, we have the bridged version of our work breakdown structure. And this is a bridge version, so we just have the main points highlighted here. We have our design, our manufacture, install, the programming portion, and then also our test plan execution. And within that is all the different tasks that we have to complete in order to have a successful project, as well as all the submittals for that project. Along with that, we have an organizational breakdown structure, essentially what part of the project is each of us responsible for. Based on those two, on the right-hand side of the screen here, we have what we call our organizational breakdown structure, work breakdown structure matrix. Between the two, that tells us what each of us is responsible for task-based to complete the project.
So moving on to the schedule, according to this, we reached these bottom two portions here, testing and troubleshooting, about 2 months earlier than we expected, which was good because these portions actually took a bit longer than we anticipated, so it was nice to have that 2-month buffer. Additionally, because of this 2-month lead time or buffer, we were able to make some out-of-scope improvements because we actually finished our project in late March, early April.
So when it comes to our budget, we're a unique group. We have a mechanical budget and an electrical budget. Some of the things that we want to point out is that we applied for an extension through the mechanical engineering department. We also did a fundraiser. We raised about $145. We estimated that it would be about $1046. After all of our extensions and fundraising, it came out to be $1307. We also did some work for Dr. Moo on the project just to make things a bit easier for him, anything that he wanted. That brought us up to $1616, and we used the AM lab fees and stuff for that. So drawing packages. For this, we had to do a drawing package. Our current drawing package is 77 pages, 55 of which are our own personal parts. If you look here, we have an assembly drawing. In our top right, we have one of our complex, unique parts. And then in the bottom right, we have a cable drawing.
In addition to that, we have here for you the entire electrical schematic, which takes you basically from the wall to the point of extrusion. Here we come in at 120 volts AC on our 20 amp dedicated circuit. It's modulated through the power supply to 24 volts DC. It goes through a DC to DC converter and modulates it to 12 volts DC, and those are distributed by bus bars individually. Here we have two overlays showing you what's going on underneath our heated bed. We have 6 individual heating partitions, as well as the thermistors that read temperature from them. Each of those partitions are controlled by its own thermostatic control module. And then to the right of the diagram here, we have the print dynamics section of the schematic, which basically controls everything about the point of extrusion. Its position based on the gantry, as well as the flow dynamics coming out of the nozzle.
So at the beginning of the semester here, unfortunately due to COVID, we were limited and couldn't be on campus. So we got permission from the department and retrieved all of our supplies and materials from the laboratory that we were working in, and we took them to Cody's apartment. Here we started assembling, we started printing more parts for the printer and putting it all together, which led us into realizing that some of the parts actually had some problems. So one of those issues here is primarily our bearings. This is the Achilles heel of the project and has been an issue since the very beginning. What the problem was is our extruded aluminum has a slot, and we were utilizing those slots with these roller bearings to actually ride in them so that it would guide the movement. What happened was these came as 10 millimeters instead of the 11 millimeters wide that we spec'd out. They had a 2-month lead time to arrive, so unfortunately we could afford neither the time nor the money to replace them, as closer replacements were too expensive and to replace these would take too long.
So once we did have all of our parts, we began testing. On the mechanical side of things, we had all of our manufactured parts, any things that we designed and printed, and all of our source parts, any parts that we bought. We tested all of these according to our testing plan document, WD58. For printed parts, we tested our gussets, clamps, any bracketry, and for source parts, this included things such as all of our stepper motors, our hot end, our fans, etc. And the results of these tests are also recorded in this testing plan document. And aside from the bearings, as Stevie had mentioned, all other parts had passed.
Additionally, we wanted to do some electrical testing according to that same test document. We wanted to do a systematic sort of verification, basically starting with individual components, verifying how they operate, integrating them into systems, verifying that operation, and then further the system as a whole. One of the big challenges that we faced was shorting in our thermostatic control modules. It's a little bit difficult to see here, but in that red circle, there's a burn mark on one of our ICs. The difficulty we were having is that there is improper insulation of the factory manufactured thermistor housings, as well as the insulating tape that we used to try to remedy this had a breakdown, which caused shorting through the pads into the thermostatic control modules. It took us a couple tries in order to figure out what exactly was happening, and some faculty assistance as well, but finally we were able to remedy the problem and move forward. Additionally, we had an arduous task of mechanical and electrical integration. As you can imagine, because everything is hardwired and we have a 3-axis moving gantry, we had to make sure that all the wires were able to reach the points that we needed them to. In that process, we implemented a technique called twisted shielding pairs in order to reduce the amount of noise and transient voltage swing that we had across the printer.
And so another big portion of this project was the firmware being how the mechanical and electrical parts communicate with each other. For this, we used Marlin. This is because it's open source, meaning we can download it and modify it as we please for free. And also because it's what nearly all FDM 3D printers in the world utilize. It's basically just a C-based code that we just modify the base parameters to fit our printer-specific needs. This includes things such as modifying the bed size to be our physical dimensions, enabling auto bed leveling, implementing an LCD screen, changing the steps per millimeter of our steppers based on the gear ratios of our printer, and many other factors.
Here you can see a schematic of exactly how we wanted to lay out the heating pads, and this is a top-down view. Essentially, in our 3x2 foot print area, we had 11 by 11 heating elements. And you could essentially turn on and off and modulate these heating elements as you need. If you only need to print on 2/3 of the bed, as they consume almost 200 watts apiece, you can turn off 2 of those heating partitions in order to save some energy. Before we moved into manufacturing, we wanted to isolate a cost-effective and manufacturing effective technique that we could use to furnish this entire bed. We looked at PCB heaters, we looked at silicone-coated nichrome, and all of those options were near $1,000 for entire furnishing, which is obviously over our budget. We settled on the conductive paint field in order to heat our bed. I'll show you here in this cross-sectional view how we decided to do it. We started with our aluminum sheet substrate on which we were going to print. That was the structural substrate. And then we coated it with a high-heat insulative enamel. It's kind of similar to what you would coat your cast iron grill with outside. On top of that, you place your 2 copper leads on the edges of the square, and then you connect the 2 with a coat of conductive paint. Once you apply a voltage to these copper leads, the conductive paint will heat up based on its intrinsic resistance. I'll walk you through that process a little bit more based on our first prototype manufacturing. We started with that aluminum plate coated in the enamel, applied the copper taping to it, and then we masked it off so that you only cover a portion of the copper tape. You begin to apply your first layer of paint. We wanted to make sure that we did this in as even and consistent way as possible because we did not have the capabilities of applying this in an aerosol form. Once you apply that first layer, you allow it to cure, which takes almost 24 hours, and then you measure its resistance. If the resistance is not low enough to meet the power specifications that you put forward, you apply subsequent coats until you achieve the resistance you need. If it's too low, you sand it in order to get higher resistance. Once we did that, we wanted to take a little bit of time to characterize the devices themselves. Basically, when we apply a particular amount of power to them, how they react, how do they heat up. When we did this, we could modify the intrinsic resistance once we made the first prototype, because we only had one. So we did this by modifying the voltage instead to change the amount of power going through them. Through this process, we were able to identify a range of power densities and, moreover, resistances that we could manufacture to. Basically, based on our specification, here is a range of resistances that you can measure and call acceptable.
So when it comes to our sheet, we had a working model and we decided to go forward with it. So we started out, we took our sheet and we located all of our holes onto it, drilled them through, and then went through and we did our coating, we sanded the sheet. This basically promotes adhesion between your stove enamel and the aluminum. After that was done and it was painted, we brought it to masking and we laid down our copper traces. Now something that's important about our paint is it's a carcinogenic when it's in liquid form. Basically this means you have to wear proper PPE, and we had to do it in a fume hood. So because on campus we couldn't find a big enough fume hood, we could only do half at a time. So we'd paint it, let it cure, it takes 24 hours, and then come back and do the other side. This took a process, we had to micro-adjust our resistances. After that, we were able to solder on all of our wires and place all our thermocouples.
Once we did that, we got the bed into the installed state. We wanted to do a little testing in that state because it's most important to us. As you can see here, we did meet our temperature specification on one of our pads. We did not meet our wattage specification, but what was most important to us was the temperature. Because of this, it's a proof of concept. We did not go back and rectify this because it would have taken us considerably longer in terms of printer testing to have testing without the bed installed. One of the things that we learned about this is that it was a process that was much better suited to industrial materials. We didn't quite have the techniques or the material in order to get good layer thickness on the conductive paint. Additionally, the insulator was scratched on pad number 2 during the installation process, and we realized though it had good electrical insulating properties, it was not necessarily durable for the application that we needed it for. Another one of the challenges we faced was grid integration. Wherever we went, based on the fact that the printer was spec'd to consume almost 1,800 watts, we had to remain under that 80% loading condition, and so we had to have our own 20 amp dedicated circuit with a NEMA 5-20P receptacle installed. We had that receptacle and that line verified both in our testing facility in SLC 377 as well as SLC 169, which is the final resting place of the printer in the additive manufacturing lab.
Here you can see our operational flow diagram, and this basically dictates the process in which you take an idea and you realize it through 3D printing. The very first thing you do is generate that CAD file using your software. You put that into a Cura with the profile that we've generated for our printer, and you slice it. You take that sliced file and you put it onto an SD card and insert that into the motherboard on the printer. Here, the next step you're going to do is turn on the heated bed partitions that you need, because you want to get those to steady state temperature before you bed level. And this is due to the coefficient of thermal expansion of the aluminum bed, changing the topography of the bed just slightly enough that if you're bed leveling before you do that, you could probably get some pretty bad results. So once that's done, you're going to bed level, and then you're going to print it. Just like any other 3D printer, it's going to go through the process of homing, leveling, printing, just the works, and then you're going to remove that print. So the very first thing that we had ever printed, it's pretty rudimentary as you can tell, but it was a great, it was a huge success for us. We were so excited to actually be able to make something after months of work and time put into this. So here on the right-hand side, you can see a little bit of a timeline of the first couple prints that we did and some of the issues in terms of quality that they had, which Cody will talk about.
So some of our quality issues were that we had layer inconsistencies. This would be because either we would over-extrude or under-extrude. We then came upon layer shifting. This means that basically when the print over-extrude, as the head moves, it gets caught on that over-extrusion. This makes it lose steps and it loses its location. This causes the whole print to shift over.
To remedy those issues, we actually had to make a couple of hardware changes in terms of belt tensioning. We realized that our belts physically could not be tensioned tight enough by the method that we were currently using, so we changed that up. Then we went through and we actually got a solid print. Here you can see this is our first print that we considered our baseline. From there, we just worked to improve upon that and considered that to be, our standard. So on the right-hand side here, you can actually see what we've produced after all that calibration. And in terms of calibration, I mean software settings such as your printing parameters like flow rate, temperatures, fan speeds, acceleration, stuff like that. Here you can see a little bit better the kind of improvement that we've actually made. On the left here, you can see something that has significant over-extrusion and undercooling, inconsistent layer lines. And just to put into perspective, this is what we can produce now. We're extremely satisfied with this result, especially considering that that is this large. In terms of you being able to see how consistent it looks on such a large screen, I think that's a pretty good result. Here you can see we have some large prints. We decided to start off with some generally normal sized prints. This is something that most 3D printers can do. It's a vase. Then we decided to scale that up quite a bit. We produced this one, and we weren't satisfied with that, so we actually made something that was previously impossible to make in the additive manufacturing lab here at Wilkes University. This is larger than any of our 3D printers can currently produce. And as was previously mentioned by Dayton and Cody, we did do some out-of-scope improvements as per Dr. Moo's request. The first thing that we did was make aluminum sleeves for our bearings. This replaced the plastic ones because they did wear out eventually. Second thing that we did was install linear bearings and smooth rods to allow for more consistent travel on those Y members, preventing the cantilevering motion that was causing binding in our rods. And finally, we installed an LCD touchscreen, allowing to remove the computer out of the equation because computers can crash. This has a very simple code on it, so it's very less likely to crash and allows for more successful prints.
So our final results, we were able to deliver our FDM printer. As you can see, we have some pretty big prints here that we're satisfied with. We also, calibration-wise, when you look at one of our calibration cubes, it's pretty spot on to what it's supposed to be.
So to summarize everything, we were able to deliver the scoped out project that we had set out for. However, it did come with some complications, as all projects do. We learned very quickly that not all parts ordered will come as you expect, and that not everything is going to go smoothly the first time. It really pays off to take time to do an in-depth trade study while you're designing to make sure you're going to get the best bang for your buck. Additionally, we learned that tight tolerancing is not cheap, and while 3D printing is fantastic for rapid prototyping and getting your any bracketry, in our case, that we were printing very quickly, some bracketry just needed to be a little bit more precise, and stuff like that is more suited for industrial methods. However, at the end of the day, I think we can all look back and smile and say that we have completed this project with to the best of our ability, and we made something we can be proud of. So as we finish up here, I'd just like to take a quick moment to thank everyone here on this list, whether it's the mechanical faculty, electrical faculty, facilities, any consultants we had. Everyone provided a tremendous help in getting us where we are today.
We'd also like to take some time to thank our donors. As you heard, we did some fundraising, so we have Main Street Snack Attack, Diamond's Farm, the Hall Art, and Franklin's Pizzeria.
And as you can see, our printer isn't in here with us. This is because it is in its final home in the additive manufacturing lab. We do have a break coming up in a little bit, so if anyone would like to go and see the printer, we have it set up and we'd be more than happy to take you. So are there any questions?
Justin, nice job cleaning up the electrical wiring. Question for you is so you mentioned that you switched over to shielded twisted pair to clean out the noise. So what did shielded twisted pair do? What's the property of shielded twisted pair that causes it to work better than the street wiring? Why is that?
So it's reducing the impedance between the two nodes that you have, the supply node coming from the bus, and then your point of switching, and then that reduces the transient swing that you're going to see when you have signals coming on and off.
And so did that then eliminate by doing that eliminated that spiking that you were seeing, turning things on and off?
Yeah, one of the biggest ones we saw is when you turned on another thermostatic control module, you would see the LEDs flash different thermostatic control module. Because of that, we saw a reduction in that, and in most cases, there was none at all.
The other thing you talked about is you used an insulated tape.
Yes.
What was that tape that you were using that had the breakdown?
It was a Teflon.
The Teflon tape. And so you switched to what?
We actually just switched to a heat shrink. Yeah, it fit right over the insulating case for the thermistor, and we assumed that it was used to insulate the wires themselves. So that would work.
So great job. How many, for the big model, how many of those heating platforms do you use for that?
This, we used 4 of them, yeah. So, because of the one pad that had failed is in the middle, so we used an L shape to put it closer towards that corner there.
So thermally, they are very consistent. Not much of a kind.
Yeah, so really all that matters is, so you saw the steady state temperatures that each could achieve. As long as you're below that for all of them, like, the lowest one is the highest point realistically, all of them will heat to the same because the thermostatic control modules modulate that temperature.
Unrelated question. How many hours per week each of you put into this project on average? Support of everybody else.
Yeah, I'd say that we put in way more hours than we should have, but we were probably in there between 20 to 25 hours every single week since the beginning of the semester, just to get us to this point.
Each of you.
Yeah, per person.
In perspective, this takes 28 hours to print.
Very good job. Okay, so just one thing I want to comment on is how you guys deal with the party economics. So that's something we actually, to be honest, that you have a very little exposure to needed curriculum, but you guys have done a wonderful job to deal with that, because that just tells you why you're engineers, because you can adapt and learn new things very quickly. Even if the things you don't technically learn in the curriculum, but you can still learn them by yourself very quickly. So that's what education is about. Good job. Okay.
Last question. Is there any IP involved in this property that makes it different from what else in the market?
The biggest difference that we had developed was the 3-axis gantry. And I know that's something that we haven't mentioned because that was a big talking point last semester. But our 3-axis gantry is pretty unconventional, and really the biggest advantage of it is it eliminates the inertial limits of producing something large. So you may have a weight limit of a different printer because the motors cannot overcome moving that inertia because the bed has to. For us, we move the head in all 3 directions, which means that you don't have that kind of issue. So that's the biggest difference. We're not necessarily sure. We didn't really research patentable technology here.
The other big part was Justin's contribution with the partition heating bed. As far as we could tell, no other printer has individual heating zones that you can turn on and off to reduce power consumption, as well as no other heated bed, as we could tell, make use of conductive paint as its heating property.
Thank you very much.
Good morning, everyone. My name is Seth Hatchett. I'm with the Heavy Impact Training System Group. I'm joined by my colleagues, John Pezzolani, Corey Schluger, and Emily Loftus. So the problem statement for our project was that conventional boxing training aids don't offer a lot of feedback to the user, which means they're not able to target their training to get a progressive overload and eventually get better at what they're trying to do. So we solved this by creating a punching bag with force resistive sensor in it that will actually give the user feedback on how hard they're striking. So if we get that force readout, we'll be able to calculate stress, strain, deflection, as well as pressure. So what we really focused on for our project was force as well as the impulse of each strike that goes into that force resistive sensor. So additionally with that, we have an array of sensors, which we'll talk about in a little bit. We're able to pinpoint which sensor is being struck, so that also will help the user improve their accuracy as they're learning to fight, do any kind of martial arts or anything like that. So finally, like I said, the system will provide feedback so the user will know exactly how hard they're striking, and that will allow them to improve over time or track if they're not improving and figure out what they need to do to continue to improve. So our target customers, anyone involved in martial arts knows that it's very crucial to continue training over time. So we're targeting people like that, anyone that enjoys fighting, training like that. And we're also targeting any kind of law enforcement or military applications, because it's very crucial that people in those fields know how hard they're striking, because you don't want to cause excessive force doing any kind of combatant in situations like that.
So in order to achieve our goals in this project, we have requirements in both the mechanical and electrical spheres. Mechanically, our project is built to be beat up, so we need to make sure we can withstand that. In our research, we figured that there was about 800 pounds force of maximum force from a professional boxer, so that's where we set our threshold. So it needs to be durable enough to withstand that, and it's not just once. It needs to be rigid enough and durable enough to withstand that several times. Further on that, that impact is going to be in isolated target locations, so the impacts are repetitive to the same area. So storage-wise, electrically, we have two fronts. The information that we're telling the system and the output of the sensor. So we need to input a biomedical matrix that's telling the system where those points of damage or bone fracture are, as well as the sensor needs to report the data that it's reading to the storage. For computation, which manifests itself in calculation and manipulation of the data it's receiving to output to the user in a way that is readable. And then lastly, the sensor requirements for the sensor itself. It needs to, like the mechanical system, it also needs to withstand that force of punch, and it needs to have a flat configuration so that we're eliminating shear. Because when the sensor bends, it does read a little bit of ambient force. The sensing area needs to be large enough so that it is able to capture the point of largest force of that punch. So the sensors we found are 2x2. And lastly, that sensor needs to be able to communicate electrically to the rest of our circuitry. So some of our specifications for realizing these requirements, you can see on the bag there is a skin-like material. And what you can't see is that there is a metal plate inside. So the plate on the inside is protecting the surface, making sure that we're keeping that as flat as possible. So there is a minute radius, and that leads into why the interface, we made a low-level filter. So we're cutting out that small noise of the small reading just from it being a tad bit bent. Further than that, our power source comes from the USB cable that runs from our Arduino microcontroller, as well as a 9-volt battery. The output of the sensor is along a linear trend line from 0.5 to 5 volts, and from there, that's where we're computing our values off of for the output of force. On that, the sensor needs to be able to sample at a quick enough rate that we're able to capture the force of a punch in less than a quarter of a second. So here you can see how our system flows, along with some pictures of what's going on. Not sure how to use the laser function, but up there you can see the cylinder is the bag itself, the squares are that sensor you can see. So what happens is you hit the bag, the sensors are recording the values of your force. That's being input to our microcontroller, manipulated, and output back to the user as value of force. Here's our SolidWorks design. It's basically the same thing you see there, just with the transparency put on that skin-like material so we can see the configuration of the sensors behind the skin-like material.
Okay, so having established some of our constraints and objectives, we move on to design our circuit and select our sensors. So we have our circuit here. You can see in the bottom left are 4 sensors, which are simply connected in parallel. The rest of the circuit is basically just an amplifier, and this outputs between 0.5 volt and 5 volts to the Arduino microcontroller, which then processes that information. All right, so we had a choice of several different sensor technologies for our project, and we ended up using force sensing resistors for this project. Some of the reasons that drew us to force sensing resistors was the cost, the durability, and the flexibility. And we specifically went with a brand that offered some more non-traditional advantages to our sensors. So force sensing resistors are usually pretty cheap and basic. However, with the TechScan brand, they offer a range of up to 10,000 pounds of force that they can detect, and very good low power consumption. They do have, enough disadvantages in comparison with other sensor technologies, but their form factor and cost made it an attractive option for our project. So there is a little bit of repeatability variation from sensor to sensor, manufacturer to manufacturer, batch to batch, because they do have different characteristics between sensors. So we want to try to minimize the variability in the circuit as much as possible. Try to use sensors from the same batch, the same manufacturer, same geometry, et cetera, et cetera. All right, so a little bit of a background on the force sensing resistors. So we have a little diagram of a shunt mode force sensing resistor here. You have a layer of printed semiconductor material and a layer of interdigitating electrode and a spacer in between, which means that this sensor is basically just an open circuit when you don't activate it, which is great because it has basically no for making the amplifier. And it also means that when you have these sensors in parallel, they do not interfere with one another. So some of the basic features, I guess, of the sensor are that it acts as an open circuit when you don't interact with the sensor. When a force is applied, the resistance drops in relation to, it's inversely proportional relationship between force and resistance, which means force and conductance is a proportional relationship, right? We then translate that to force and voltage, and with the TechScan sensors, which is the brand that we ended up using, we have a very, very good linearity from the bottom 0.5 volt all the way up to our 5 volt or our 800-pound limit that we decided to use for our sensors. Traditionally, force sensing resistors are used for more qualitative applications, such as detecting a rate of change of an applied force or exceeding a threshold. Sometimes they can be used in scroll pads for electronics. However, we try to eliminate as much of the variability as possible so that we can increase accuracy, increase precision, and use these for this specific application as protecting the force. Because they do have pretty good resolution. Here's another explorative view of what a force sensing resistor looks like. This is you cannot really tell from the enlarged view, but this is a through mode sensor that we use. So this is more like the sensor that we use. We ended up using several 3x3-inch sensors from TechScan, and they look pretty much exactly like this. So you have the basic layout of it. There's a top substrate, there's a laser, and a bottom substrate. So basically, it is a mechanical element, which means there is some rise time and some settling time. That element has to get crushed, it has to be compressed and activated. It's not instant. It doesn't have the same response time as other sensors. It's maybe an accelerometer or a load cell. So like I said, it has its advantages and disadvantages. So there are a couple important guidelines that we follow in integrating these sensors in our application. Some of these guidelines come from Interlink Electronics, which is the company that created and patented the force sensing resistor in 1977. So they understand them pretty well. So some of these that we follow are, number one is know your sensor. Basically means where does error get introduced in your sensor and in your circuit? What is the variability? What is the drift, the linearity, things like that? Try to eliminate that as much as possible. Number two is we choose the sensor that fits the best geometry for our application. That means having a large enough geometry that encompasses the entire scope of the force, so we don't have a half-hit register. Number three is set up a repeatable and reproducible mechanical actuation system, because unfortunately these sensors are very sensitive to force distribution. Again, that means we don't want to have crazy variation in registering half a hit. We want to make sure that our force registers on our entire force registers on the sensor. And we want to increase cycle consistency. So we want to try and hit the same area basically, so that we have a better read. Number four is we use optimal electronic interface. So what that means is, when I showed that the circuit earlier, we have one amplifier. A lot of times with the force sensing resistor, you would use a voltage divider circuit or current to voltage converter circuit, and you would have several circuits per force sensing resistor. For us, we have one circuit, one amplifier for all four resistors. Similar characteristics for four resistors that come from the same batch, so we try to reduce errors as much as possible. Number 5 and 6 basically relate to calibration. Develop a nominal voltage curve and error spread. So we have our sensor. We adjust the sensor gain via potentiometer in our circuit, and it increases as much as we need. And then we create a calibration curve with several points. So we load the sensor, say at least 5 points, 20, 40, 60, 80, and 100% of the target load that we're going to do. Create a line of best fit. And from that slope and intercept, we have our calibration. So we have that advantage is that you're able to calibrate the sensor by yourself, and it doesn't have to be manufacturer calibrated. And then refine the system to reduce any kind of user errors where they might be introduced. Here is a little snippet of a spec sheet from Interlink Electronics, the company that patented the force sensing resistor. So this gives you an idea of how much error can be introduced in a circuit with force sensing resistors. We try to minimize that as much as possible. We obtain pretty good results from our testing of both our static and dynamic testing. Again, they have very good resolution, better than 0.5% at full scale. However, there are a lot of opportunities for errors to be introduced. So we try to simplify the circuit. And here's a snippet of our code. So two things that I wanted to show here is that we have two variables that are sensors and circuit output. We have force and we have impulse as a unit of Newton seconds. So we have code for impulse. And if you look here, we have the result of our calibration. This is the line of best fit, the slope, and the y-intercept. This is what enables our sensor to output the accurate force in the video later on.
So going into testing, our original static testing was we were going to put the weight on top of the sensor. We had to concentrate on this little plate, that way all of the weight was going directly onto the sensor. You can see our first test at 300 pounds went really well. We had 0.719% error. Unfortunately, it went downhill from there. We were not able to replicate it because we had a balancing issue. So because we were trying to put all the weight on this little piece, it kept on tipping over and we weren't able to get accurate readings. So from there, we went into the lab and got the Intron machine. We had Mr. Adams make these little plastic plates for us that concentrated it, and we were able to control how much we were compressing down, and that's how we did the rest of our static testing. So this is the overall static test curve. You can see this down here is where we actually make contact, and this is the max loads that we have. So our runs are at 1400, 1442, 1444, and 1452. Those were our max loads for the 4 runs that we did for static testing. And then these, I'm going to circle through. These are the actual data test results. So because the Intron machine went down and compressed, stayed there for a moment in time, then came back up, we did a 5-point average just to try to get the best numbers that we could. So you can see these are what we loaded it at, these are our results, and we see our percent errors, we came as close to about 1%, but everything was really well with the static testing. So once we had the static testing down, we moved on to dynamic testing using a drop test. So we used 2 different weights, 100 and 150 kilogram force. That's what the weight was in at the labs. And then we only did at 1 meter at height because when we went higher than that, we weren't able to drop it directly onto the weight or onto the sensor. So with that, we just stuck at the 1 height but changed the weights. And we used the following 2 equations to calculate our force in newtons. And then you can see our sensor readings again. And then these are the data results again. So you can see our 292 corresponded with a 307, what we calculated that. And then this is the actual working prototype. You can see it's coming out about 600 newtons of force.
Okay, so this is our work breakdown structure, how the actual project got done. We broke it down into 4 major components: the mechanical, electrical, testing, and lastly the management stuff. That's all. So those are the 4 sections that we broke it down into. This is our Gantt chart, our schedule of how that all works. So this is the research and management portion, a lot of paperwork, the actual mechanical and electrical design. You can see what we were doing, who was responsible for it, and then the days that we started and completed those steps. Then the electrical and mechanical assembly, it all actually coming together, and then our testing and report for the completion of the project. So this was the budget. As you can see, we spent in total about $350. So we had about $550 remaining in our budget, so we came in well under budget for this project. This is our kind of what ifs. So if we had more time, more money, more knowledge, what we would have done to improve the project overall. So if we had more time, we would have liked to include a better output to the user about what the force that you're striking the bag with would be able to do to a human analog, as well as a little bit better pinpointing of the strikes. And lastly, right now, as you saw, we have the computer outputting the results. We would have liked to have a little LCD screen attached right next to the bag to give the user a better idea. If we had more money, we'd like to see better sensors, as well as an actual human analog, a silhouette type thing, to show or give the user a better idea of where they're going to be striking in the body. And then more knowledge, better user interface, just giving the user better results overall.
Some of the lessons that we learned from this are, on the technical side, basically we found out right away that with the lamination of the sensor becomes damaged if you apply shear force. So it has to be, static testing has to be done very carefully, which we were able to do with the Intron machine, which was done basically perfectly perpendicular. On the other hand, some of the things that we could have done better is basically implement the accelerometer and use force sensing resistors on the cheaper scale to find pinpoint location of the hits. And from executive side, basically a lot of our issues would have been solved if we had met more frequently.
All right, so in conclusion, our project effectively illustrates exactly what the user is doing when they're practicing to strike the punching bag. It gives them useful outputs on how hard they're striking, so that's their force, as well as the impulse, which is force involving a unit of time. So that's the useful input, useful output that the user gets out of our project. These are the references that we use from the force sensors. I want to offer a special thanks to everyone in the mechanical department and the electrical department for helping us put our project together. Does anyone have any questions?
Forrest, could you go back to the schematic? Yes, sir. Right there. Yes. So your sensors are in the lower left-hand top corner.
from the sensor side of the circuit there. The circuit illustration.
Okay, so you don't have a biasing circuit defined on your sensors. Do you remember how you did it?
With the biasing sensor we used basically was, a lot of the circuiting is normally done with a voltage divider or a op amp and a current to voltage converter. We basically used one of the PET-scan boards, which are they are compatible like in a plug-and-play setup with the sensors. So our circuit was not custom built. Our amplifier was not custom built.
That's a missing point on this right there. Okay, thank you.
Would you go to your dynamic test? So those were the like later when you do the impact test.
The drop testing?
Yeah.
Yes.
Like the number, that's okay. Basically, it's just a quick comment. So your static test and the impact test, actually, that wasn't the thing that was most interesting. So I'm so glad you guys actually did that. And maybe I mentioned this last time, but that, and those results are really great. So they really, I mean, yes, we have lots of time constraints and budget constraints which are making this model actually feasible, but this is the foundation of everything you do. So this, I'm glad you guys actually focus on this part of the course. Very good job.
Thank you. Thank you.
Good morning, everybody. We are Water Current Energy Generation. I'm Ryan Lasher.
I'm Chase Olson.
And I'm engaged Pedro actually cannot be here today. He's playing his last baseball game of his college career. Our advisors are Dr. Bresci and Dr. Mill. So before we dive into everything that we've accomplished this semester, we wanted to give a little recap, just briefly. Our project statement was to design an adjustable and portable system to generate electricity from water current. The project goal was to ultimately charge a 12-volt battery using a car alternator and a series of pulleys while making the frame adjustable. And last semester, we completed our CAD models from schedule, WBS, simulations, testing, and specs requirements. If you look up to your right, the picture up there, that was what we turned in last semester before we went on break. One of the major changes that we have between that model and this model are the paddles. These are buckets that we use, and after talking with Mitch downstairs, we actually switched to using metal fan guns. So this is a list of our requirements for our project. I want to point out that all of them have been completed except for the two red bullets in the bottom left. The reason for that we did not use a tensioner, is because we actually ended up using polyurethane belts, which had 10% of a stretch that would have its own tension on our pipes. And we actually did not develop a cover for the alternator to keep it at a direct precipitation. When we were doing our alternator testing, it was actually pouring, and we really did not see an impact on how our alternator performed.
To go to our frame, we cut the aluminum square tubing, the two 6-foot arms, and 5 2-foot cross members. Before we welded the frame, we decided to drill out the holes where the fill blocks would be, because we figured it would be easier. So to do that, we measured where the holes would be by hand and using the mill to make sure we double check our measurements. When we drilled those holes, we allowed some tolerance so we could slide the pillow blocks to the outer part of the frame to provide more tension in the belts. And then lastly, to finalize our frame, we welded on each side of the cross members along the main arms. After cutting our aluminum base to the proper size, we drilled holes in each corner so it could be staked to the ground. After discussing with Mitch, we decided instead of buying short channel floor mounts made of steel to connect the arms to the base, we would instead use aluminum square tubing to make the floor mounts ourselves so they could be welded to the base plate. We also welded 2 corner brackets to hold the battery in place and stop it from sliding. To secure the trailer jacks to the frame supports, we use the existing bracket that was previously made for them and drilled new holes in it. The jacks could then be secured to the frame using U-bolts, which also allowed us to move them along the arms as well as remove them for transportation. We modified the feet of the jacks so they could swivel to match the terrain that they would be sitting on. To build our water wheel, we reamed the center of the bike rim so it would fit the shaft we're using for the pulley system. Additionally, we drilled 2 holes in the bike rim to secure it to the shaft. The second hole was used so we could flip the water wheel around to account for the different directions of water flow. Initially, we were going to use 5-gallon buckets to make the paddles for the water wheel, but instead we used recycled fan blades and bent them to add curvature. And we secured those fan blades to the bike rim using U-bolts, and we evenly spaced them around the water wheel to create the most efficiency possible. For our pulley system, we used 2 polyurethane belts and 1 V-belt. The reason we had 1 V-belt on the first gear ratio is because when we initially used a polyurethane belt, there was some slippage because of the size difference in the pulleys. So we used the V-belt to provide more surface contact, which provided more friction, allowing it to spin more efficiently. Additionally, we discussed different combinations of gear ratios to use, but we decided to stick with our original plan because all the other combinations that we could come up with would make the alternator spin slower. We initially wanted to use the 2 holes on the bottom of the alternator to secure it to the frame. However, they were not symmetric, so we discussed numerous solutions, one being to make a bracket that you would secure to the frame and then secure the alternator to. However, instead of that, we decided to use one of the holes and use a bolt through it to secure it to the frame, and the weight of the alternator would be supported by the cross member. 12-volt battery used in the system would be able to store DC power, but we also added an inverter into the system that would allow for any AC appliances to be plugged into it if they needed to be used. For our work breakdown structure, we have completed all the mechanical, electrical, and testing aspects of our project. We've also updated and finalized all the documentation we needed to complete. Besides the final report, which is shown in red in the bottom right-hand corner, which will be completed next week. Shown on this slide is our schedule. Since we decided to order materials at the end of last semester, we were able to construct our sub-assemblies, test them, and finalize our prototype that we're showing you today ahead of schedule. This is our finalized budget. We spent around $170. We were able to save a lot of money by using donated parts from prior senior projects. We also wanted to leave a lot of remaining budget in case we ran into problems during testing.
So next we're going to talk about our cost analysis of our system versus any type of conventional gas power generator. I did a little bit of research online and we found the Champion Power Equipment 3550 watt weekend portable generator. The reason why we picked this generator to put against ours is our inverter has a continuous output of 1500 watts, whereas this generator is able to put out 3550 watts, but at a 50% load using 4.7 gallons for a total of 14 hours. We did a little bit of research online and found that the nominal annual interest rate was 12%, using this both systems for 26 times a year at gas at $4.28 a gallon for 2 years. You can see that our system is actually about $50 cheaper. Yes, you might say that gas generator is going to be more efficient and it's going to be more conventional to bring around. You're going to be able to use our system at night in any type of stream, and our system puts less emissions out into the environment, which is more eco-friendly.
So next we focus on our sub-assembly testing. The picture in the top left corner is when we did our pulley testing. And before we actually put these on our frame, we wanted to make sure that that they would work. So what we did was we got some plywood, and we didn't want to drill into our frame, so we drilled into these wooden blocks to make sure that our system would actually function properly. The picture in the top right corner is our frame when it was welded. We wanted to make sure that the weld was whole, so what we did was we went through and pulled up on all of the cross members, and we actually bent one of the front ones. So we had to re-weld that just to make sure that it would work whenever we went in the field for testing. The picture in the bottom right corner is the bolt that connects these shafts to the wheel. Jason pointing to it right there. That is a 1/4 bolt. We initially did not plan for it to bend when we were in the field testing. So what we did was we upped the size by one size of the bolt to keep it from bending in the future. This is our alternator testing. The graph on the left is when we tested the alternator at the beginning of the semester. And what this did was it set a goal that we wanted to hit, or have our alternator hit at least 1025 in the field. The picture on the right is from when our most recent testing was. So although it does not spin perfectly center, that's why the RPMs fluctuate. That's because we have not been able, as of today, to perfectly get the paddle centered around all the 8 different paddles centered around the light rim. We were working on that up until this week when we did our last testing.
So next here you actually see the 2 areas that we tested at. We call it Hillside Farms, and they were gracious enough to allow us to come and test. You can see on the left side, that is going to be a wider area of the stream that allows us to have a lower flow of water, that allows us to see if our system will work in a lower flow. And then on the right side, you can actually see our system a little bit set up in the bottleneck. We use the bottleneck to test because that was going to increase our flow of water, similar to how we did fluids. When you have a decrease in area, you're going to have an increase in velocity. That was probably going to be our 2 best situations to have. And then here we're going to show you 2 videos of our prototype testing. One of our biggest concerns when we were actually making our system is the first time we went to go turn this, our first thought was it's pretty tough to turn. So we were concerned about this moving correctly in the water. The left video is going to show you it moving. Now that video is personally my favorite because you can see the water moving slowly, and each subsequent pulley you can see moving faster. That was a very big success for us in our opinion. We got to see it move, and we didn't have to jolt it or give it any type of kickstart going. The second video, which is going to be on the right, that's going to show our testing that we did in the field of deflection of our paddles. Our biggest concern was if this stopped moving, were our paddles going to deflect and were they going to break? So we ended up having Gage and Ryan hold onto our shafts and stop our wheel from moving to simulate if our system seized up or if a pulley stopped moving to see if we had any type of catastrophic failure. As you can see, we didn't have any notable deflection, and we were very God, I'm just going to smile. I can't figure out the word. So you'll see here on this slide, we actually put our system in the back of Gage's Jeep. Gage has a mid-sized SUV, and you can see that it fits pretty well in the back of this car, and it gives you room that if you want to take this camping and use it, you have the room to bring the extra equipment, tents, sleeping bags, anything of that type of equipment. Next, we did some efficiency calculations. On the top left, you can see the measured shaft RPMs. We saw for our wheel that we actually had 17.7 RPMs of our measured RPMs. With a wheel diameter of 34 inches and a rudimentary calculation of 5 feet per second of our water flow when we went out to test and got these measurements, we saw a theoretical wheel RPM that was supposed to be 106.8 RPMs. You can see there's just a tad bit of difference between those 2 numbers. So we saw a water-to-wheel force efficiency of about 16.6%. Additionally, you'll see on the right side, we have theoretical versus measured pulley ratios. The first ratio is from the first shaft to the second shaft, second shaft to third, and third one to the alternator.
You can see that there was some decrease in our pulley ratio. We expected some type of slippage, some type of loss due to friction and tension. That's specifically shown in the first one. That's a very significant loss. We used a V-belt there, which increased the friction and the amount of tension and didn't have as much elastic properties. Additionally, we would like to point that we actually had a veer ratio of about 100. I know last semester we said we had 192. We actually checked our 1-inch pulleys this year, and instead of them being 1 inch, they were actually about 1.38. So that kind of helped us keep the amount of torque we had down. And we saw that our overall pulley efficiency was about 66.8%. So just to conclude our system, we were able to charge a 12-volt battery successfully, and we were able to plug my computer, my AirPods, and my iPhone into the inverter while our system was running, and we didn't see any type of significant loss of voltage within our battery. Some improvements we would like to do. We would like to create a cover. Like Ryan said earlier, we did test this in the rain, and our alternator was fine in the rain. We did not bring out the battery and inverter because we did want to put a cover eventually on that, just because those are electrical parts, and water and electric don't really mix too well. Additionally, we would like to do some stress analysis on our bolt. Like Ryan showed earlier in the picture, we showed that there was some type of deflection and bendage in our bolt. If we would have had more time, we would have been able to sort that out, and it would have been much easier to get the paddles on and off. And then lastly, we would like to optimize our paddle shape. We were not able to optimize that just because of the time constraints we had and the amount of time it would have taken to do so. So if we had more time, we would have been able to look at different shapes, test them, and actually optimize them for the real world. Lastly, it's not shown up here, but we'd like to say some ideas that we actually learned. I know me personally, I'm able to build systems in SolidWorks. I'm able to build systems theoretically. My old boss will tell you that personally. I am very bad at practically making them. So this semester showed us how to practically build something from our design phase to our actual model like you see here.
So this time I'd like to acknowledge Mr. Mitch Adams. He was a huge part of making our project. And he actually simplified our initial designs. He proposed using stuff that was already downstairs in the senior projects room instead of ordering and waiting around for it to arrive so we could immediately start testing, which saved us a lot of time trying to accommodate for the 3 of our schedules our senior year. Hillside Farms allowed us to test at their farm. They took great interest in what we were trying to do and what our projects stood for. And then last, we'd like to acknowledge Lisa for helping us order all the materials, our advisors, and Dr. Bennett for some projects. Does anybody have any questions?
We did not specifically look at that, just because when we did our real-world testing, we didn't see any significant voltage drop. Our plan, if we were to actually market this and put this out into the real world, we would send it out with 2 or 3 batteries so that while one's charging, or 2 of them are charging, you can have the other one working with the inverter. We saw that as a possible idea.
What we also did was we took our alternator to AutoZone and we hooked it up to test it. And we found out that the alternator can put out a maximum of 135 amps. But the problem is the alternator is only going to supply whatever current is needed to power the system. That's why whenever you hook lights and everything up to a car, when you measure the current, it rises whenever you turn the lights on and the stereo is.
But you realize that for this project, that's pretty much one of the most important things, right?
We were able to charge the battery and power the inverter off of that. And the inverter has a 1500 watts.
But like I said, I mean, that's for this extensive amount of work. I mean, at the end of the day, you want to know how much power goes into that battery. Right?
I would like to know how long it would take to charge a battery every month.
So, can you go back to the alternator testing slide? So you can see here, we used the 1,025 RPMs. So it took us, you can see, probably about 0.2 volts in 5 minutes. So we said
We're confident that this will charge in about an hour and a half total. We didn't have the time to go out and get it from lowest charge to full charge, and your battery has to have some type of charge in it to help excite the alternator to charge the battery itself. So we weren't able to go out, and we didn't have the means to get another alternator. We didn't have enough time just to do that. So we were able to bring this out, and from what would say probably about 9 volts, we were able to get it up to 12 in probably about 45 minutes at top end.
Okay, thank you guys. Okay, everybody, so we made it to lunchtime. So we're 15 minutes behind schedule, so we're going to reconvene back here at 12:30. And a reminder to all the teams, please stick to the time line because we still have 9 more teams to get to this afternoon, and we need to be out here by 3:45. So please stick to the time.
PE faculty, we have your ratings, please.
Dr. Zoo.
Oh boy.
You got this, Tundra. It should just pop out. If you press it.
Let's take
The other one's not in that one, right?
This is
Oh, that's the other one. Okay, okay. Cool.
So I put the one that was used in there for this.
Okay, perfect.
work environment. Don't be scared to ask a question while you're there. Steer clear of more crazy than he is. He's the most. Although on a serious note, his dad is incredible.
Hey, David, you want to take a picture?
What?
Want to take a picture for us?
Okay.
Yeah, unfortunately. Unfortunately. That's good. No, you didn't. What are your favorite ones? You know that's becoming like second nature. I used to never be good at presentation.
Okay. Yes, sir. You're welcome. Glad to do it. Well, what do you think? Hey, take more than one.
Yeah, why not? Maybe it could be for dinner time. Which is weird. I'm not sure why I was reporting it. Well, because the house was at level, and all of the engineering directors reported to this one thing. And that's what all the behind that wall. Yeah. That might change. Maybe it might.
People didn't know what to do. I know. Well, Frank has tractors to play with. What's that? Frank has tractors to play with. That's what he does. He flies tractors and he's got that property. Did they bring anybody new? No.
I'll get it from you. I'll get it from you Monday or Tuesday. Yeah. All right. I'm going to be taking the team out the chart routine out for a drink. Okay. Will do. Thank you, sir. Have a good one.
Yeah.
mother gave you a talking to. I'm so sorry. You know how it is with God, right? You know. I said, why did you cry? What did you say? What did you do? I don't know if I can show my face there again. I was so upset. You know, but anyway. I know. But I got a job in the depot. Yeah. I got a job in the depot. And then I got another job on Transpower Technologies in New Jersey. And I don't want to take that one with them because it's a small company. And I've heard mixed things about them. But the advantage is they do a subject that they specialize in. And when I went there, they gave me a test. They said, solve this BJT, solve this op-in. You know, and I did it easily right there on the spot. You know, solve the ripple voltage of the amplifier. And I would like to do hardware design, and I lose out on the demo. So I want to drive it. So, how long you drive is the demo? 15 minutes. Maybe less. Yeah. Yeah. Which is that's why yeah. It's hard to find there. Yeah. That's what Dr. Curie just told me. He just told me.
It's kind of a few.
Yeah. And you know, it's hard enough to find a job in hardware design. You know, and then if you only have 6 months experience, 1 year, it's still hard. You know, because there's not a lot of entry level positions either. Yeah. I'm definitely staying. I've been studying something since I graduated. And one of the things I have learned about electronics, she's coming to big trouble.
I just want to say
Thank you, Trevor.
I really appreciate it.
Yeah, what's up?
I wouldn't have got a job.
Very, very rainy day.
Hey, I had a question for you about your project. So you were talking about how you were having
what we did was the power plant is
okay.
So it's like we go in,
right.
That's the reason I
So in the realm of electronics, to swoop you use a capacitor. I never I'm not a mechanical, I'm not just a mechanical engineer. The equivalent of that would be like you add extra weight to it so that you would keep the momentum and actually help smooth out, but you wouldn't want to include that extra weight.
Yeah, essentially.
Okay. I was brainstorming when we were listening. I just wanted to check. We can do so many things differently.
What are we on now?
You're going to go.
I think it's like what? Thank
No,
you.
actually.
Thank you. Thank you.
Anyways, yeah, you guys were like,
Make an extra lunch.
Oh, I wanted to roast you for mispronouncing my name.
Oh, did I do that?
You mispronounced my name and our work project twice.
The name was funny. It was like the name was funny.
Yeah, you called me Evan Petro.
I thought it was Ian, but that's okay.
It is for you. I think
I thought I said Ian, but that's all right. That's all right. No.
I'm just going to go put this in my car, and then I'm going to look for you.
I'm part where
I didn't mean to. I know better.
I'm part of the main.
No, it's okay. I just thought it was kind of funny because then you made me stand up, and I was like,
I'll just text you. I'm going to put this.
I swear I said Ian because I'm reading it. That's why I do it. I read it.
You said Kyle, you tripped over Rossler, and then flowed into the
Oh,
yeah.
But it doesn't matter. I knew I was behind schedule, and I was trying to make up. I shouldn't have.
No, it's all right.
Great job. Great job. Great job.
I know I made a few mistakes.
I was impressed. You answered the questions correctly.
They need metallization.
The what?
Metallization. They need the system to metallize.
Believe me, I know. Believe me, I know. No, you did okay. I noted what's up. I noted. I'll go over everybody's, my review of everybody's presentation. All you have to do is come see me and I'll give it to you. Okay? No, I deal with voice, loudness, articulation, speed, hand gestures, how you answer questions, that kind of thing. So everything was fine. I think you guys have been practicing. I've been harassing you all semester. So, that's not a big Take an extra lunch. And I do know what the hell your name is.
Yeah, I would hope so.
If I said that, I swear I'm reading it. Oh, well.
Even still, it's Petro.
Yeah.
No, it's my name's not Petro.
Is it really?
The issue is
Petro?
really Petro, yeah.
I didn't know that.
Yeah, so the issue is up at the Avoca exit, there's a gas station. It's called Petros.
Yeah, the Petro station.
However, people in New Zealand, people in Lackawanna County call it Petro. We call it Petro. That's why you must be from the Petro fuel dynasty.
I wish. My parents wanted to name me Liam, but they chose against it. Whenever they do last name, first name on the sheet, it wouldn't have gone over very well.
I know a lady.
That means you're going to have to get started here.
Yep, I think I have all of my stuff. I'm going to tuck away some boxes for lunch and we're walking down.
All right, walk down, so I'll be out here whenever you're ready.
Yeah, and you do not need to buy anything for this. We're all just going to have a good time.
I'm buying the first round.
You don't have to. You just got to show us how to do their tequila shots.
That's exactly why I'm buying you the first round.
Expensive now.
I'm not gonna have you buy the first round on the tequila that you're supposed to.
So, what are shots?
I don't believe in shots.
You believe in classic.
I believe you drink it. Tequila is not a shot with lime and salt.
You need to show the video of Sarah from Kyle's birthday party.
See you Monday or Tuesday.
Thank you.
I was telling him, I said, I think we have...
Good luck.
Do you want to start in there or like?
schedule for this afternoon. We have 4 teams presenting, then a quick break, then 3 more wrapping up for 392, and then 1 more quick break, and then 2 391 teams. So I do kindly ask all the teams stick to the time limit. I'm going to set my timer for 13 minutes, and then when you hear the beep, 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 beep go off, that means you have 2 more minutes to absolutely wrap it up. So you have to stay under the 15 minutes, please, because we have a whole bunch of teams to get through. Okay, guys, just also real quick, I want to take a moment to thank our Zebra communication students that are filming, Christopher Gawani and Maddie Kinnard, so if we could please give them a round of applause. They're handling the live streaming, and it'll be posted to YouTube later on, and also to thank our colleagues in the communications department, Dan Mattern, Rod Dennis, Kaylin Churcher, for all their support, as well as the students from last year's event in December, Sarah Ross and Jake Mascalek, who I think have trained and kind of helped pass the bar. So yeah, thank you to all our Zebra students. I want to take a quick minute then. Okay, everybody, so we're going to pick right back up with rainwater power generation. And, okay, thank you guys.
Hello everybody, thank you for taking the time out of your days to come and watch all the presentations. We are the Rainwater Power Generation Group. I'm Kevin Schofield, joined by Bioreactor, Archie Plant, Alex Myers, and Ethan Weaver. So to begin, we're just going to go over a little bit of table of contents, stuff that we're going to go over. We're going to do a little bit of a recap of the fall, where we got to from where we were then. We'll show our SolidWorks design from there, then we'll go into our mechanical and electrical requirements, show our Gantt chart, and then our updated budget. From there, we'll show our final SolidWorks design, and then we'll go into like pictures and videos of our testing setup from everything that we've done to test where we are now, and then we'll show videos of more real-life simulations and the charging of our portable chargers that we will be sending over to Dr. Bangladesh. Then, obviously with some projects, we'll hit some bumps in the road from time to time, but we'll show what we faced, how we overcame them, some risks and concerns, and then we'll wrap it all up in the conclusion.
So to recap, last semester, we chose this project to provide assistance to a school in Bangladesh by providing electricity or power through a renewable source. We wanted to charge iPads and iPhones to help the education of those students. And then since Bangladesh has a long wet season, we were looking to use that rainwater to help provide the power. And since the community already has solar panels installed and in use, we figured this would be a good backup to provide electricity. And then at the end of last semester, we created a testing mechanism that would simulate the head that would provide the power. So this is our final design from last semester. As you can see, it's built as a standalone structure. It utilized a turb system to collect the rainwater. However, we realized that it didn't collect enough water, and we wanted to utilize the roofs that they had in the building to provide more volume of water. And we also realized in order to reach the needed head, it would be an unstable system, so we decided to go in a different direction.
So here are the mechanical and electrical requirements for our project. On the mechanical side is the system of the structure and the turbine. In the system of the structure, we decided we're going to use PVC piping. It has to be 96 inches because that's how tall the building is. And we have to make sure that we enclose the electrical components of our design so they don't get any water damage and get destroyed. And then last of it, we have to make sure that we use a gutter system that's going to be installed over there to make sure that we can use that gutter system to make the flow into the approximate tank. And then on the turbine side of the mechanical requirements, we need to make sure the turbine spins in one direction and also go through the right speed so we can make sure that we have the most efficient power and the most efficient maximum efficiency. And then on on top of that, we need to make sure that the head and pressure of the system is evenly throughout the entire thing. On the electrical side of things, we have power generation, transfer DC to the portable chargers, and the charge capacity. The main goal of this is we have to make sure that we don't charge iPhones and iPads over there. We need to make sure that the electricity that is generated is enclosed and cannot have water damage. And then we have to also make sure that we have a voltage regulator inside our circuit to make sure that we have the same, most consistent voltage and it doesn't fluctuate at all, so it messes up the current and the power that is generated. So this Gantt chart shows the schedule from the fall semester all the way up into this presentation and on. So in this Gantt chart, in the fall semester, we hit the two major milestones, and then going into the spring semester, we also hit the two major milestones, and we are almost ready to ship it over to Dr. Bangladesh soon to make sure that they can get the device and get it up and working so they can get electricity in. We have all of our milestones throughout the entire year that we had planned. So this is our budget. This is everything that we bought throughout the whole semester. We have a we spent very limited money, $236.98, because we were making sure we had extra money in case anything went wrong in these final 2 weeks or anything that we had to ship over there. We could have some of the shipping costs covered for it, and we also didn't have to make the collection tank, so they can load it over there and they can make it over there. So that made the cost total spent this entire year very low because we didn't have to buy anything like metal-wise or anything like that.
After some thinking, we realized this was going to be our final source design. As you can see, we are using the 3 turbines down below, connected with the piping to the collection tank. The height of the building that we assumed to was 10 feet tall. With that height, we should be able to generate enough power to charge the battery. The collection tank will be connected to the wall with some self-products underneath it. We are going to use 2, each one on one side of the collection tank. And down below, we didn't really need to put the piping into the wall, but we realized that just to make sure that we didn't get any movement, we were just going to use clamps connected to the piping to make sure that it didn't move. So this is our first prototype. All the testing was done in the lab, so we will use a constant flow. With this constant flow, we were able to test all 3 turbines separately and collectively. After the testing, we realized that we needed way more head in order to get power needed to charge the battery. This was because our turbines needed more pressure, and the only way to increase the pressure was to increase the head. So after we were done with this testing, we moved on to the next.
So at some point we did have to take our testing outside, mainly just to increase the head that we could actually attain. We could get roughly 5 feet in the lab, and we realized quickly that it would have to be in the range of 10 to 12 feet to see any significant power generation. So we used fire escape just to be able to have enough clearance to work with. This was a 10-foot head, and we used 1 piping system. So the biggest flaw here was that the bucket that we used could only be filled up once and let it drain. We had no way to get a constant flow of water in so we could prolong a test. So we were kind of limited in how quickly we could record data. So that was one of the downside. But what we did notice here was that the RPM of the turbine could be simulated in the lab as long as we know that the voltage output was the same. And that was how we were able to take our testing results from outside and replicate it in the lab using the benches. So this was some of the data from our trials at 10 feet. So we got 64 milliamps for our voltage of 23.9 volts and a power output of 1.529 watts. This was, again, only done with 1 piping system and 1 turbine. So continuing, when we took it into the lab, we were able to replicate our outdoor results by just finalizing that our output voltage would still be 23.9 volts, even with pressure added from the bench. 3 turbines could then be utilized because we had 3 hydraulic benches at our disposal. And then the power generated did charge a portable charger that could be used for iPhones, iPads, or any device with a USB charger input. A full charge takes approximately 5 hours, and this is something that we're going to further explore over the next week before shipping over.
This is our final electric circuit. As you can see on the left, you have the 3 turbines connected in parallel. We realized after testing that in order to get the most power out of the system, we needed to put all the 3 turbines in parallel. With this, not only we avoid any problems that we could have if one of the turbines stopped working, but we can also get a higher current. With this system, we get the average voltage, which is around 24 volts, and the current will be multiplied by 3, which is what we wanted because our current was really low and we needed a higher current in order to charge the battery. Then next we have a capacitor connected also in parallel. This capacitor makes the voltage stay more steady, so we can get a more steady voltage into the battery. And after that, we have the key part of the system, which is the voltage regulator. This voltage regulator takes the voltage that we put in, and it gives us a 5 voltage 1 amp output voltage, which is the amount needed in order to charge our water.
So as you can see here is a video of the outdoors testing setup. This is more to simulate what it would look like when it's attached to the building over in Bangladesh. And like I just said before, the data we got here we used to calculate the RPM and voltage. We can mimic that in the indoor lab, which we'll show next, and which we use to actually physically charge the portable charger that we will be sending over to Bangladesh. So here is a video of the lab setup. As you see, we're plugging in the portable charger there. There's the circuit and you get 3 different turbines connected to 3 different hydraulic benches that mimic the same situation that we showed outside, but for a longer period of time. So this video is a time lapse over a course of about 15 minutes showing that we were able to get the portable charger to charge.
So we do have a few ethical considerations that we have to take into account. So firstly, a structure that will be created that will withstand all the elements. This may include wind, sea, and storms, as well as the weight of the water handling tank being suspended on the side of the building. Additionally, we're going to have to implement, in the instruction manual, we will send over how to input a mesh grate, just so that way no leaves or anything block up the pipes or the turbines themselves. Additionally, with it being a humid environment, we had to avoid water pooling at the bottom of the tank just for mosquito concerns, especially considering this is going to be in use at the school. However, with our bulkhead fitting that we used, this really wasn't a concern at all, and we believe that that will be replicated in Bangladesh in the final system. Additionally, for the same concerns, water runoff out of the system needs to be taken away from the buildings or anywhere where the students may do any of their work in the day. This can just be done with a flexible PVC pipe that's cheap and easily accessible.
So with any engineering design process, challenges are faced. Our first one was communication with the community in Bangladesh. Obviously, since we are on different sides of the globe, sometimes it proved a real challenge to get a hold of them and get the information we needed in order to complete this project. The second one was the redesign. At the beginning, we were trying to power a really large power bank and producing enough current to charge that. So we ended up switching it to portable chargers. Then we had difficulty finding an acceptable outdoor testing area. It was really hard to find an area where we were able to set up our system to have the 10 feet of pipe length that we needed. And then lastly, developing the circuit to get the proper current input into that portable charger.
So emerging concerns of this project was the lack of a gutter system that is over in Dhaka, Bangladesh. They will have to create a gutter system so we can make our system work. The shipping cost of Dhaka, Bangladesh, it's very expensive to ship overseas nowadays, so we're going to try and have our leftover budget help with the shipping costs. And we're going to ship limited parts over there, only the more important ones. The water runoff, like Archie was talking about, we have to make sure that it goes from the water turbines through them into a river stream outside of the school district. And then the keeping of the debris from the collection tank and the gutter system, we need to make sure that it can't damage any of the water turbines or anything like that, so it can be working 24 hours every single day that it's raining and it has enough water to work.
So in conclusion, we hit every point that we wanted to hit within this our end goal of actually making a system that will be used over there in Dr. Bangladesh. So we'll be shipping it out within the next couple of weeks before graduation. Like Alex said before, we'll be sending over the turbine and a couple of other pieces that aren't that heavy that'll reduce shipping costs. Because they're able to get the PVC pipes and they have the welder accessible, they'll be able to make the collecting tank that we recommend for them. Additionally, we'll be sending an instruction manual to show them how to assemble our structure and like what order it should be assembled in. And then finally, we're going to be working on enclosing the electrical component and putting it in a more stable circuit board where it'll be soldered and be permanent for them so that it'll be waterproof.
We'd like to give a special thank you to Dr. Zhu, Dr. Frederickson, Dr. Bednarz, Mr. Adams, and Mr. Coloviti for all their help over the past 9 months and completion of this project. Are there any questions?
Could you go back to your slides that you mentioned that it takes 5 hours to charge it, right? Could you tell me like how did you come up with that number? Right there.
Yeah. So through our testing, we have we usually hit around the 45 to 47% mark, roughly in about the same time, like 45 minutes. And then we timed out the rest throughout the past couple of days of what we could obtain, and we were able to get upwards of 70% in about 2 hours. So that's something that we will test further this week. We say approximately because we believe it may start to slow at the end. But as of right now, kind of the way it was from 45 to 70 was pretty consistent in the timing between each percentage.
Okay, so this number is a big question mark.
And that's something that we're going to explore that before we ship it. Probably not next week, but the week after.
But like, same as the previous project, you know, so how many watts do you think is going into the battery? How many watts when you're charging?
That the battery is rated for, that we are rated.
It was like it was over 4 watts.
Do you mean what the battery was rated for, or what we
No,
were inputting?
how many watts?
Oh,
How goes into the battery?
1.6.
How many?
1.6.
1.6 watts.
Yeah.
Okay, that sounds about right. Thank you.
Yeah.
So would this charge one iPhone or one iPad?
So, basing off the numbers that we found on the older iPads that they have at the school, that as far as we know, because communication got a little dodgy at the end, one full charge will do 1.2 charges of an iPad, and about 1.8 of an iPhone.
So you need a lot of these. If you were to charge all the iPhones for school, you'd have to go.
So the other thing that's important to remember here is that this is a unit that's going to supplement the use of solar panels already, which goes into their larger power bank. And the iPads in the school are mainly used for communication needs between the rest of the world. That's how we kind of stumbled across the project with Dr. Frederickson. So how heavily they're used in one day in school may depend from day to day. However, they have our system along with the solar panels that are already there. We're kind of aiming for that 4-month rainy season where it can rain for days on end, and that's where this will really put to use.
So then maybe they'd be able to charge one iPad or something like that.
Yeah, and our idea is to send over multiple portable charges, so one can be charging while they use the other.
Thank you, guys.
are the autonomous launch shields. My name is Ezra Jack. I'm here with David Flaherty, Joe Lilly, and John Implant. You may ask why. Well, at the beginning of the year, we were the last guys. We got put in a group together. And we had no idea what we were going to do. So we got an idea from a friend that Dr. Fetcher had a project that he needed done because he's been doing studies in Alaska for 30 years. His next study, he wants to see what sunlight does to tussock cotton grass. So we talked to him, thought it was a great idea, and we designed a product that is going to be used in Alaska this summer from July to August. It will be running for 30 days, and it's going to happen for the next 3 years.
So let's talk a little bit about our project and what it is. This is our device, and it's set on an autonomous timer. So we set the time, it'll close on demand and open on demand. This is just so Dr. Fetcher can study the phenology of Tundra cotton grass and see how it may differ from lower and higher latitudes of grasses.
So here was our original design for the Tundra shield. It was a 12-foot tall pole with a linear actuator that would bring down an umbrella over the Tundra pine. And early on, we decided that this design was never going to work because, for a lot of reasons, but mainly that's how it's going to work in Alaska. That's just a little demonstration there. But it's this design was becoming a lot more complicated than we anticipated, and we weren't confident that when we deployed it in Alaska, it was gonna perform how we expected. So early on, we scrapped that design and had to start from scratch, and that's always a little nerve-wracking when you have to get rid of a design that you worked really hard on and start from scratch. But at the end of the day, it worked out for us because our current design is much more reliable and robust than the umbrella could have ever been.
So then we moved on to this design. At first we used 12-volt DC motors. These motors worked pretty well. They opened the shader efficiently. The problem was that the internal gears were plastic. So we ran into gears fracturing and snapping when the shader would over-rotate just a little bit. Also, the stock that the company we ordered from was very low, and we were unsure if we could order 24 motors to produce all 12 shaders. So as you can see, this is our completed project. Right here we only have 10 shaders. We do have 12 made. As of May 10th, they will be packaged up in a giant crate, and we will be shipping them to Alaska for Mr. Fetcher, or Dr. Fetcher, to be using them in his experiment. So when we first got them, he had some concerns. It needed to be at least, it had to cover a 48-inch diameter circle. It had to allow less than 1 micromole of light through the material, so that way it doesn't affect the experiment at all. They had to be easily transportable, so we had to make it light to transport it, because I believe he has to travel about 500 yards to where the actual experiment is going to be taking place. And then also we need 12 units.
So over winter break, Ezra and I were here for wrestling, so we got to work on a couple of prototypes. And visually, the prototype is very different than what we have now. You can see that the cover itself is a different material. In the video here, it's made out of cotton, which is much lighter material. And once we switched to this fabric, we wanted to ensure that we still had torque to be able to open the cover. Also, if you look at the video whenever it's closed, the front end lets in a lot of light. So Jonah had to do a little sewing on the front to have a little drape come over for the shield. But on the right, you can see one of our later prototypes where we add the proper material and the servos are strong enough to be able to open it. And more than anything, we just want to check the concept and the mechanisms and make sure that they're able to withstand plenty of trials. So we ended up running our servos and our components for a couple hours of iterations, which is more than anything the shaders ever going to see in the field.
So understanding the mechanical elements of our shader, basically there's 4 total poles. The first pole is connected to a servo, which isn't in the video, but this is going to be the pole that's applying all the force to pull the other 3 open. And then the back 3 poles are assembled to our project because it allows for the poles to be opened uniformly and at the same position and equally apart every time. Because if the shader were to open and the poles were to be misaligned or something like that, the cover would collapse onto the plants and cause a critical error in opening and closing of the mechanism. So it also allows it to close down as flat as possible when the shader is not covering up the plants. And then here's just a completed, here's just like a complete mechanical assembly of what it looks like down here. So the three connectors at the bottom, they're held together by an aluminum rod, which is powder pinned on either side to prevent it from any slippage and keep it secure so they can last the entire time of an elastic.
Some of the biggest obstacles that we had throughout our design process, the timing was probably the biggest that we had, because in order for it to be autonomous, it has to operate when we want it to. The accuracy of timing with the Arduino is inaccurate by a little bit, but over time that small error accumulates into something large. So we ended up implementing a real-time clock module that operates on its own separate battery, and that keeps track of the real time, so that in events, say, where we lost power to the device, the clock will still be keeping track of time. We could replace the battery, and when the shader needed to close or open again, it would do so successfully. Our 3D printed parts at first were not strong enough using standard PLA. We had a few breakages, as you can see, even with some of our later parts. We replaced that filament with Mark IV Onyx, which is carbon fiber infused filament, and we also adjusted some of the print settings to add some more density to our parts and allow them to be a bit more robust. Our power source was not supposed to be an issue, but it became one. We were originally going to use smaller batteries to power each individual shader, and we ran some tests and we were able to get about 140 cycles running back and forth every couple seconds before the battery dipped to a voltage level that was not enough for our mechanism to perform properly. But we did not take into consideration the idle current of the servos holding their positions over the course of the day, and it ended up being that we could only run the system for about 2.5 days at a time using the smaller batteries. So we decided to use a larger 12-volt battery and a solar panel that would be constantly charging the battery to provide power at all times. And a very basic wiring diagram so you can understand the mechanism. Obviously, the sun provides power to the solar panel charges the battery. The battery will then put voltage through a voltage regulator, which allows us to step down whatever voltage we're taking in to whatever we want to put out. We were putting out roughly like 6 to 6.8 volts, which is what we need for the servos to run properly. The clock would be keeping track of time data on its own, and then the Arduino would constantly be reading that time data and comparing it to set variables that we have in our code to determine whether or not it should be in the open and closed state. And the servos are getting positional data by the Arduino when it should be open and closed. This is all of our code. Actually, it is very simple. You see the creation of the two servo objects, the real-time clock. There are a lot of comments because our code does need to be user-friendly for the team that is going to be up in Alaska running the experiment. There really shouldn't be too many issues with it. It is really just a plug-and-play, set it up once and run it, and it should not cause any issues for our customer.
All right, so outdoor testing for our team was essential. We wanted to make sure that the Tundra shield is able to withstand the Alaskan summer environment. Turns out Alaska Tundra in the summer is very similar to Wilkes in the spring, with rainfall and wind gusts and the sorts. But a couple of things we want to look at for outdoor testing was the clock modules. So as John said earlier, we do have a clock that runs on its own, an internal clock. We want to make sure that over an extended period of time, of a month, that the clock module doesn't run behind or ahead too much. And the clock module will stay within, we found it stays within a couple seconds even by towards the end of the month. Some of the other things we're looking at is the batteries. We ended up going through a bunch of different batteries. We started with a LiPo battery, but it didn't have the amp hours that we needed, so we needed a battery that we could recharge, and we ended up going with a battery that we could charge using a solar panel. And even though it's been overcast the last couple of days, we still maintain a charge on our battery, and just because this just pulls just enough that you need something to charge it, but at the same time it's not pulling a ton. To look at some of the physical components, just make sure that the servos are able to perform in, outside and be able to do what they're supposed to. In the cloth, we want to make sure it doesn't tear under wind conditions, and just observe the overall strength, where we might encounter errors, breaks, and how we can improve them later. So on the left, you're able to see our Tundra shield under wind gusts of up to 30 miles per hour, which is about the most I've experienced on the Tundra. And on the right, we have a heavy Wilkes bear spring downpour, and all the electronics inside were safe and dry. On the left here, it just shows our solar panel setup, and this is able to charge the battery enough even on overcast days that the battery doesn't die. And on the right is it opening under high wind conditions, and the shader had no problem whatsoever.
So after we were confident in the test results that we were getting from our prototype, and we were confident in our design, we were able to start the mass production of all 12 of the shaders. This led to a few problems, being that we could only produce the shaders as fast as we got pieces to. So things like 3D printing delays and shipping delays really set us back in the production process. So to assemble all 12 was a long, drawn-out process over a few months, but at the end of the day, we were able to get them all assembled, all 12, and we're going to make the May 10th deadline to successfully ship them all up to Alaska for next spring.
So here's our base cutout assembly, and that's our backyard. And we got a router table, and we cut out a template first, and then since we needed 12 of them, we wanted like an efficient way of doing it. So Ezra had the idea of we should cut a template, we should just clamp it on, screw it on, and then trace out all of our bases. So doing that, we were able to cut down our time on making bases too. Towards the end, Ezra and I were making a base in 10 minutes. And we also had to waterproof them because they will be exposed to outside. So we ended up sealing all of them, and yeah, that's our base production.
So the polyester covers was my job in the manufacturing process because I'm the only one on the team that knows how to use a sewing machine. So essentially, to make one of the covers, you have to make a template, like a leaf-shaped template, and then you're going to take this template and cut it out with the fabric, and then when you have 4 of the leaf-shaped pieces of fabric, you sew them all together, and then you're going to sew on some of these Velcro connectors, and these Velcro connectors are made it so we were able to connect the fabric to the poles, so that when the poles are moving, the fabric can move uniformly together with the poles when it's opening and closing.
So on to the 3D printing parts. Throughout this process, I worked with Dr. Moog mostly to get everything 3D printed. We happened to use the Mark IV printer, which is an amazing printer. The only problem is we printed so much that belts started to loosen and it needed some adjustment because parts were coming out not correct. But once we got the parts all printed up, which I think we had roughly 150 printed parts, we had to post-process them. So there's a lot of structures within the parts we had to take out so that way it can support the printing process.
For our electronic components, the top picture you see is actually our own creative little electronics module. It contains the RTC clock module, which you can see at the very top. A little PCB breadboard, which allowed us to solder components together so we weren't just loosely sticking wires into the Arduino. The Arduino itself, and at the bottom of that is the voltage regulator that we're using to control my power. It's all wired together. There's only one power source needed. At the bottom you can see that there was, in fact, a lot of them that had to be done, and this involved a lot of calibration of servos, wiring, soldering, screwing everything together, and making sure that it fit in the boxes.
Our budget. So to make one shader, it costs roughly $521. This does include some bulk material. So if you cut down the bulk material, the price of the units would be a lot cheaper, considering all 12 shaders cost roughly $3,800. We did get lucky, and this project was funded by the National Science Foundation, so it was able to cover all of our expenses. And as you can see, most of our products we either order through Lowe's or Amazon. And we just wanted to give a thank you to Dr. Fetcher, Dr. Zoo, Dr. Wu, Lisa, Mitch Adams, and Joe Shaver.
Well, thanks. We thank you, and as I thank you, and hopefully you transform it.
I just want to say something. Very proud of you, what you guys have accomplished. And it's just on that everybody knows this idea is inspired by babies' car safety. So I mean, car seat open close. So that's where it came from. So engineers into your life, that's where you get inspiration. You see that very much like how the baby car seat open close.
You're viewing this to verify just how dark it gets under the shade, and I don't know if it matters according to Dr. Fletcher or what the experiment requires, but do you have any measures on that?
Yeah, Dr. Fetcher actually has a meter that can read it. And we close the shade over the meter and it read 0 micromoles. Like,
awesome.
Is there a concern about the temperature, what it's below the sunlight on it?
This project, it'll be closed over the plants at roughly around midnight in Alaska. So it's pretty cool.
Thank you, guys.
So this is our prototype. We'll start by working through the name. So self-sufficient. It means that we're having it be able to run off of solar power. It can go into a wall outlet as there is a plug for it in the inverter, but we wanted it to be able to work on its own. It's a atmospheric water harvester because it is condensing that water that is in the air and converting it back into water in a receptacle.
So why? Well, when a natural disaster strikes, it can throw a lot of debris into the air and it can cause damage to our water infrastructure. And it also can often cause damage to our electrical grid. There are ways to take water out of the atmosphere, but a lot of them are very expensive and are reliant on our power grid, which can get damaged. Any sort of like large-scale water harvesting operation that exists currently is very expensive. It's very large and it has those issues. So we wanted basically that was a little bit smaller, a little bit more compact, something that we could deliver somewhere that experiences a natural disaster and provide water for people. So some of our mechanical requirements, first we need to make sure we have a good solar panel support. We wanted to make sure everything could stand up. We wanted to have our solar panel be able to fold out and fold back in so that it can be collapsed for easier storage and fold out so we can get a right angle on the sun. And we also wanted to have our air cooling system. It needs to be able to draw as much air through the system as possible. The more air we can get through the system, the more throughput we have, the more water vapor we can have access to the system, and the more water we can condense. It needs to be able to condense the water, of course, and it needs to be able to redirect any water that it condenses into a receptacle that can be removed and put back in. Some of our electrical requirements. First, we have our control unit. We wanted to make sure our control unit didn't take too much power or anything. We wanted as much power for our system to be going into our cooling as possible. And we also have our solar panel requirements. We wanted to make sure our solar panels could charge our batteries and power our system. We needed to make sure our batteries had enough capacity to. Now, the one we have here is just a proof of concept. Making something that's fully up to spec would be extremely expensive, many thousands of dollars. So this is just a proof of concept showing that it could be done. But a full-fledged system would be able to. Some of our ethical considerations that we have when creating this is, first of all, intellectual property concerns. So our cooling coil design that we have comes from GE, and we would either have to do licensing for that, or we would have to create our own. We wanted to create our own initially, but the reason that we didn't was because it's not safe for us to do so. We're working with pressurized refrigerant, and none of us are, qualified to do that. So we had to avoid that. There's testing protocols that have to be followed. Generally, systems like this are tested at 60 degrees Fahrenheit at 60% relative humidity. Ours wasn't tested perfectly at that because we didn't have a way to perfectly match those conditions. We did the best that we could, but an actual system would have to be tested in an enclosed environment that would have those conditions. And lastly, of course, safety to the consumer. We don't want anybody to get hurt. We want to make sure our water that we generated would be any way accessing the electronics. And there is the concern about the potability of the water. We don't want people drinking water that's unsafe if they're going to drink the water from the system. So this is our work breakdown structure. Very simply, we have our mechanical, electrical, testing, and documentation or management things that we did. You can see how we broke it down. And this is the schedule. There were some setbacks when we were building the thing, but we generally tried to stick as close to the schedule as we could and do as much work as we could. So this is what we've generally followed. Here's our budget. You can see we spent a total of about $258 on ours. We wanted to keep the cost down in case anything broke or anything. And if we compare that to how much it would have cost to build it fully, it would have cost us around $2,000 if we weren't able to source any of our parts for free. We were able to keep our costs so low because we've got a lot of our parts for free, and we're able to really just keep the cost down because of how we were able to access things.
So we had some constraints on the project. One of them is that we did want to limit the amount of money that we are going to spend. Most of the components for our project are relatively expensive. The solar panels, the batteries, the cooling coils. If we wanted to get a full version that works completely, those would be way out of our budget. And if we got ones that kind of worked, we would still be out of our budget. And we wanted to keep some budget around in case of failure of some of these systems. For example, our cooling coils are about 9 years old, so old things break. So we wanted to make sure that we had money in our system for that. And we used that pre-made system because of those safety concerns we mentioned earlier. It's full of refrigerant 410A. It is pressurized. That is not something that we are capable of doing ourselves.
Yeah, so you can see that we have our prototype that looks slightly different from our initial design. So our initial design, as you can see, had 2 solar panels, and they're supported by longer legs, and we also had the design for a open top. We opted to kind of change that and go with a more closed system, considering most of the components just run. There's really no need for maintenance or anything like that. It's still also easily accessible with a screwdriver or like an impact. The solar panels weigh quite a bit. We would ideally use lighter solar panels, but with the system that we had, the 2 solar panels, getting them to mesh together and sit in a really safe and consistent position, while also working with our brackets and then also being able to lift them up and down. We had the 2 solar panels because we were trying to maximize the amount of solar array that we can have. Since this is a proof of concept, we were able to drop it down to 1 solar panel and still have current and be able to charge batteries at least slightly. So then, yeah. So the actual structure is built from 80-20 channel. We went with this because it's a really strong, consistent material that's easily able to construct simplistic frames. We designed and created all of the brackets and 3D printed them on our own 3D printer. So all the brackets in the corners, and we had brackets designed to actually slide and collapse our solar panels. On the legs, you can see in the corners we have brackets that we designed and created so that we have pivot points for our legs attached to the solar panels. All of that was created in-house and designed. We did run into some breakage issues where we had to design and kind of beef up the actual components so that we could withstand like the weight of the panels and everything themselves. So then the actual electrical components, so we have obviously our solar panels. We have our solar panels running into a charge controller. So when you run a solar system, you can't really have you can't just have your solar panels going directly into your system because they don't offer a consistent current because obviously you're relying on the sun. If you have cloud cover, you have current droppage. So then we need something that's an intermediary in between our battery and the actual system. Since our pre-built system was designed to run off a 120 volt outlet, we do have a power inverter to convert the DC power from the battery into AC. And then our actual cooling coil system, we have a condenser that pumps compressed refrigerant continuously through a pipe system. So the system has a bunch of fins and is cooled down to about 40-ish degrees Fahrenheit so that you can collect water vapor from the air and have it collect on the coils, and then just with gravity it drops into the receptacle below. We have a fan that just draws air through so you can get as much of the outside air in through your system and try and maximize that. We have a filter in front to block out any particulates, potentially bugs, whatever, from getting into the system.
So for testing, at every point in the process, we kept testing all of the components individually so that we knew at any point if we had to replace any of our parts. So when we tested our solar panels, we got a current of about 2.8 amps coming out pretty consistently. It has a maximum of, not pretty consistently, it has a maximum of 3.5 amps, and it was a relatively sunny day, but not super sunny. So that showed us that the solar panels were in fact working, and as well as they were bringing a 12 voltage to the battery. However, we ran into an issue at some point where our battery it looked like it was charging because it was getting those 12 volts, but it was a dead battery, so it was not charging. So later in the process, when we started to try and use this just off of battery, we got delayed because our battery did not work. Due to adverse weather conditions, it's northeastern Pennsylvania, it's what it is. We opted to test inside at first. We made our custom greenhouse pretty much in Edison's bathroom. We pretty much, our classmates told us it would be a great idea if we were to run a shower to improve the humidity in the bathroom, but we were running this for long amounts of time, so running a shower for that long wasn't a great idea, so we instead filled a tub with water and let that slowly humidify the air. So in our indoor tests, there was a relative humidity of around 50% each time we started it, and we got around 2.1 milliliters per minute of water, which isn't a lot, but originally when we were in a lab here that was at about 35% humidity, we were only getting around 1 milliliter a minute, so the change in that's likely due to the humidity that we were working with. So for some potential improvements, to get this system running a bit longer, because off of the battery, the singular battery itself, it would not run for very long. We would like to get some high-end deep cycle batteries so that they could get recharged constantly and they would work, the device would be able to work for that longer 8-hour period of time. A better solar panel would allow the batteries to charge at a reasonable time because with the solar panels we have, it would take much longer to power the batteries than it would take to be able to run it. We would think about adding food-safe coating to the coils so that it makes the water more potable. Right now, it is not drinkable water. We do not want people drinking anything that comes out of this. There are other concerns to the potability as well, other than just the food-safe coating on there, so that was a little bit outside of our scope of working with. We would think to add additional cooling systems, being able to design our own cooling coil system would be a big plus in being able to make our system work better. As
as well as adding a larger fan so that more air would be able to get through the system. We initially set to have a larger fan, but we wanted to leave a lot of room in our system to add those extra batteries that we would want to add, so we didn't have enough space in this current design to add a bigger fan. So in conclusion, our objective for this project was to create a water harvesting solution for disaster relief areas. To do this, we designed and constructed a system that would collect water by condensing vapor in the atmosphere and have it not rely solely on a power grid. We faced a lot of challenges and setbacks, but we did learn a lot from this experience, and our prototype is a proof of concept, but it does work. It doesn't work right now because sometime in the last week or so, our actual cooling coils broke. So the pipe on it is broken, so we can't actually turn it on to show you guys, but given more time and resources, we can prove to make this successful. So we'd like to acknowledge a few people: Dr. Karishi, Dr. Bednarz, Lisa Colovetti, Jim Lennox, Mitch Adams, and the entirety of our senior projects team class. Do you have any questions?
How much water you think you would get? Even okay, so let's say if the battery, the solar is able to sustain and run the battery for 24 hours continuously. Let's just say that ideal scenario. What's the ideal situation you think the best can get out of the system? Like how much water you can actually generate?
So the system that we have is a 70 pint system, so that would be kind of our ideal number. That's 70 pints over 24 hours. So ideally, we would be able to get 70 pints out. This is why we kind of have it a little bit larger, so we can have a system out here where we can see we have more space for water. We took the system and kind of took the auto shut off system out, and we wanted it to ideally run and hopefully get like 70-ish pints. I mean,
how much liter is that?
Because
right now, like the one you had was about 2.4 liters per day, based on my quick calculation here. So how I want to get like what's the percentage you think?
I don't think I have the numbers. I don't have the numbers for that off the top of my head. But yeah, we were kind of struggling where this is an old system and we know we weren't getting like the ideal numbers. Yeah. I think a liter is 2 pints. A liter is 2 pints.
But you know where I'm heading, right? I want to get a sense of like, okay, that's 100% idea, that's 100% of that. You get 10%, 20%, whatever. I want to get a general sense of how much you're getting. That's all we need is figure. See, that's the thing you should put in your presentation because that's help us to understand actually. And there's one matrix, that would be the simple, most important matrix for the system.
Yeah, pretty sure, guys. I'm glad you were able to get results kind of watching you come for the last 2 semesters. I think one of my original questions, even back last semester, again this semester, how does this compare to like a normal household unit that I may have in my basement? You know, like what would be the typical production from that as opposed to what you were doing?
So we didn't, like the numbers that we got were not really ideal. I think they're on par / a little bit lower because our starting testing was indoors in an air-conditioned room because that's kind of where we were limited to. So I think most houses are about like 50-ish% humidity if you were like to put it in your basement. Usually that's like the biggest area where you have humidity issues. Usually that's like about 50-ish% humidity. I think ours was tested at about 35. So we were getting really low numbers, and I mean, the system is old, so I think we looked and compared it, and it's kind of running behind. I don't know if we have like an exact percentage difference, but then right now it's running at about on par with what you would get out of the standard dehumidifier. We tried to kind of open it up and like increase the airflow, but it didn't really seem to have much of an impact. Ideally, like we mentioned, it would be super cool and it would be much better to build a system let's say we're working with pressurized refrigerant. I'm pretty good at figuring out most things, but I'm not an HVAC specialist. So building in our own system would have also given us like customization options to where we could fit more and put larger, like a larger cooling coil system in and probably run it more efficiently. Whereas this system is designed to run off of a 120 volt wall outlet, we could have potentially run something a little more efficient off of our batteries. But I think we're about on par with what you would get out of a standard dehumidifier.
Give some quick calculation here. So it's about 33 liter, or it's about half, like you said. So it's, you guys are thinking it's about like less than 10% each. That's a rough number there.
Yeah.
Again, that number is not necessarily very important, but I guess that's the way you guys should be tackling this problem.
Yeah.
Because I mean, think about if you want to improve this machine, that would be how to increase the number.
Good afternoon. We are Group 7 Autonomous Algae Bioreactor. I'm Dylan Kuipers here with Brandon Gordon and Kevin Noller. We're advised by Dr. Carol Bedore, and this is our final presentation. Shown here is a picture of our project. It is a bioreactor, which is a device that holds a biologically active system. Our goal is to capture carbon in the form of algae by providing the optimal environment for algae to grow. Our motivation for this project stems from our passion to protect the environment from climate change. Shown here in this figure, you can see that the carbon emissions are growing at a drastic rate with little signs of slowing down. And it's for these reasons that drive our interest in technologies striving to combat climate change. On top of this, there are very few carbon capture technologies deployed throughout the world today, and it's for this reason we see an opportunity in this field. Some of the goals for our project, it's a proof of concept, so we want to prove that we can make an automated system and also prove that we are capturing carbon. We want to make advances in the current climate combating technology, so we want to show that the carbon we are capturing is enough to make a difference. And then we want to achieve these goals within our budget. We believe if we can achieve the goals within our budget, that we have a lot of room for improvement. Some of the goals for this semester were to create the physical build, wire all the components, complete the program, test all the components, and acquire data for our results. Some of the ASME Code of Ethics fundamental canons that we've been following throughout this project are numbers 1, 5, and 8.
So we've been on schedule all semester. Our main focus has been building the prototype, testing all components, gathering data, and acquiring results to show the outcome of this project. Our WBS has a few changes compared to last semester. On the mechanical side of things, we have designed an algae separator to replace the harvesting tray for the harvesting procedure. On the electrical side of things, we have an LED and photoresistor combination. This component will measure the algae density within the tank. We also have 2 water non-contact sensors that will be attached to the algae separator. This will control the ball valve and servo combination. So this is the block diagram that outlines our requirements. Nothing major has changed since last semester. The components I just mentioned in the WBS further optimize our harvesting procedure. So we have come under the $500 budget. We spent a total of $426.31. Our real world total is over $1,000, but with help from the senior project storage room, we were able to avoid expensive costs like the support structure and 2 batteries.
So the CAD model on the left shows the plant design as of last semester. This was a very good starting point for changes needed to be made along the way. The biggest change would be going from a harvesting tray, an open harvest tray, to the algae separator system. mentioned before, this is just a proof of concept to show that the technology works. So with that in mind, we did not focus as much on the aesthetics as we did the functionality. That is the reason that some of the wiring is not super clean and the electronic components are not in a protective housing.
So for our tank, we used a 5-gallon water jug, which we cut the top out to incorporate our 3D printed lid. We then drilled 3 holes into the side of the tank to incorporate our water pump, aerator pump, and temperature sensors. We added 2 check valves to the tank, one on the bottom to connect the tank to the aerator tube to ensure no water can get into the aerator, and one at the top to allow air to escape the tank without letting anything in. And then we also have a photoresistor and LED light to perform our density readings.
So here's a list of the 3D printed parts that we made for the device. These are printed on my personal printer as well as by Dr. Moo in the lab. The first one was, its only goal was to fill a void in the bottom of the tank where algae would build up and become hard to harvest. Number 2 was one of the systems that we struggled with the most. Number 3 wasn't completely necessary, but allowed easier control of the water into the algae separator. Number 4 was printed by Dr. Moo and provided an easily removable cover to the top of the tank. Number 5 was the largest of the bunch, taking roughly 55 hours to print. Unfortunately, we had to cut it into multiple pieces to fix some issues. It's kind of hurt on the inside, but it was definitely necessary. The process for determining the algae density is fairly simple. Every couple of hours, a photoresistor on top of the control plate will check the ambient light. If it is dark, the LED will turn on, and a second photoresistor will check the amount of light passing through the tank. If this photoresistor measures a high value, that means a lot of light is passing through, and the system knows that there's not a lot of algae in the tank. The 2 pictures that are shown are the 2 extremes of algae density. The clear water will reflect most of the light, while the dark, dense algae will block most of it.
So there's 2 major components to our harvesting procedure that are shown here. A 5-volt DC servo motor is attached via a 3D printed mount to our ball valve. This component allows the algae water to exit the tank and fill the algae separator. A 5-volt DC water pump is then attached to the bottom of the algae separator, and then that pumps the filtered water back into the tank.
Once the system determines it is time to harvest the algae based on the density we measured before, the ball valve will open up, allowing water into the separator. The 2 non-contact water level sensors are constantly checked to ensure that the water valve closes at the right time and does not overflow. The water will then seep through the filter, catching the algae as it travels into the center of the separator. The water pump will then be turned on and pump the filtered water back into the main tank to grow more algae. The arrows in the cross-section view of the separator shows the flow of water throughout the process. These steps are then repeated for a predetermined number of cycles.
So shown here is our touchscreen user interface. When the device is turned on, our ABB logo will load onto the screen. Once the device is pressed, we can go to the home page, which we can go then to the environments and controls pages. Our environments page shows the algae density as well as the water temperature. The circle next to the algae density will show blue for low densities, yellow for mid-ranges, and red for high densities. On the controls page, we can control the aerator, water pump, valve, and harvesting sequence. The aerator and water pump are just controlled by on-off switches. The valve is controlled by a 0 to 90 degrees slider, which will 0 degree being closed, 90 degrees being all the way open. If the harvesting command is selected, a confirmation will appear, asking us if we want to force the harvest. If the harvest is selected to continue, the harvesting screen will come up and the number of sequences that have run through the algae separator will show. If the cancel is selected, then the canceling screen will appear. The valve will close and all the water from the algae separator will be pumped back into the tank. Once either this or the harvest is completed, the complete screen will appear and the user can return back to the controls page.
So for the brains of the operation, we chose an Arduino Mega due to its many input and output ports. The one we received had some issues. The analog input pins would not read the values correctly. This was an issue because the touchscreen needed these pins in order to use the actual touch feature. We ended up just using our own.
simply attaching the servo via 3D printed mount to the valve. However, the valve did not budge. Our second attempt was to implement a gear system that theoretically should have increased the torque by 3, a gear ratio of 3 to 1. But again, however, the valve did not budge. So next, we simply just replaced the valve with a smaller one that required much less torque. And as you can see in the video, we have a successful component.
The program behind the AAB took a long time to develop throughout the semester. Designing the pages that Dylan just showed took just as long as it did to develop their functionality. The process for the harvesting sequence we took from our PLC class when modeling a classic tank problem. The program had to go through a lot of trial and error to get it to this point.
So when it came to determining the algae density within the tank, it went through one failure before a successful process was executed. We initially intended to use sunlight and a photoresistor installed at the bottom of the tank to measure the algae density. This proved to have its many complications, one being the most obvious is you can't control when the sun will be out or not. So after some thought and discussion with Dr. Zhu, we concluded that we needed controllable light and to only harvest at night. These corrections then made the harvesting process a success.
The touchscreen that we got is originally designed for Uno and not Omega. However, it is advertised as compatible with the Uno and Omega. It took a long time to figure out the issue, which was that the SD card did not function properly. This was because some of the pins on the two Arduinos look the same, however they function slightly different. Once this problem was determined and corrected by adding a few wires, they worked well.
So when it came to the algae separator, we had a series of complications and failures. One being that we failed to identify a key feature in the filter holder that is installed before each harvest. It prevented a tight seal at the bottom of the separator. So instead of reprinting the whole separator, we corrected some dimensions, cut the bottom off, 3D printed a new bottom, this black piece, and then attached it to the original piece with silicone. So this process actually saved us over a day of printing, because as Kevin mentioned, the whole separator took well over 2 days to print.
We started growing our algae with just a small kit shown here on the left, just on my windowsill. We then decided to order a larger algae culture, which we saw great results in just 2 weeks. We then split this into 4 separate containers, which were all used, it amounted to about 12 gallons, and we used that all for testing.
So 2 weeks worth of testing, harvesting testing is shown here. The last column of the table shows how much carbon was captured with each harvest. So although it is evident that we are capturing carbon with each harvest, these results are not what we intended nor expected, and it is clear that we are not filtering out the majority of the algae like we wanted to. So to put this into comparison, the average tree takes out about 800 grams of carbon every 2 weeks. Even adding up our results, we don't even compare. So, but there is some silver lining here. At the beginning of the semester, we purchased a large sheet of 1 micron filter paper. That ran us roughly $30. But upon further research and discussion with Dr. Terzaghi in the biology department, we actually required different filter paper for this application. For a large sheet of that filter paper, that would have ran us into the thousands of dollars. So we as a team still believe with more time and the right filter paper, we would this prototype would perform to its expectations. And then from there, scaling the unit size and the unit numbers, we believe we would be able to make the impact that we set out to do. And these are our references. And yeah, just can't thank everyone on this list enough. We wouldn't be at this point without them. So thank you.
Any questions?
So at the end, you mentioned that it wasn't capturing as much carbon as you hoped. Is the problem that it's passing back into the tank, like you mentioned with the paper?
So, yes.
A better paper would capture more carbon?
When we had our discussion with Dr. Algae, he showed us the circular filter paper that he suggested. And after we did our research, we realized, a 12-pack of those alone would cost us $130, $150 for a piece this size. And these pieces here are 10 by 10 and a half. So we would be spending a lot of money even for one piece of filter paper like that. And then another reason is we may have filtered too early in the growth process of the algae. In the table you can see the later harvests we're actually getting more. So there's a couple variables we thought could have contributed to that.
I have two comments. Very good job. I don't always see good things. I hope you guys understand. So, number one is you guys' attention to details, like how much you put into the software development. Some manager could say, "Oh, this is superficial. That's why we didn't do it." So, but that's tremendous amount of effort just to make that touch screen work. And also the automation part. You can say, "Oh, well, let me just close this valve." But you guys need to spend so much time to deal with that valve. So the attention to detail in this project is outstanding. That's my first comment. Second comment is that you really took a scientific approach to this problem. I really want to like. The presentation is also very good, almost flawless. From software power to eventually this slide is also super important. Good or bad, at least you should do it. So 5%, 10%, not a big deal. But at least that's an approach you should take. And for that, like those two things, that's impressed me most. Thank you.
Thank you. Any other questions?
Thank you. Dare I say, are we ahead of schedule? Hey, all right, so we got up to a quick 5-minute break. You're going to need to use the restroom or grab a drink. Come right back in 5 minutes.
Okay, right here. Do you see this? Yeah, okay. Yeah, you're good there. I love cats. This is for me.
What's this? Over here?
No.
No, it's got to be at least in front of that first computer.
Yeah, at least.
At least there.
Hang on, let me. Move it over a little bit more. Now you're good. Yep, you're good.
Dog, how's it going? Saving the best for something.
Okay, everybody, we're going to get started again.
Good afternoon, ladies and gentlemen. Thank you for coming out today. We are the CATS team, Construction Aid Traffic Systems. I am team leader Trey Harloff, and I am joined with you today with my good friends Trevor Fegley and Dustin Snyder. And today we're going to be showcasing the culmination of everything we've been working on, this whole scope of our project with our fully working prototype. Just a little project recap and inspiration so you guys, we all are on the same page here. What was our initial goal? What did we intend to do? Our main aim was working with construction sites, human flaggers in particular. Now our initial goal was to design, build, and test a construction aid traffic device in order to aid in the human flaggers that are working on the front lines, often exhausting their shifts, and be able to make these construction environments, number one, more safer for them. Number two, make the whole system more efficient as well as more effective. And number three, to be able to develop a system that can be more easily reconfigurable and therefore be able to adapt to many different scenarios.
So while we were working through the year, we had to take into account some ethical considerations, and we took these from the NSPE Code of Ethics. The first one was that we must hold paramount the safety, health, and welfare of the public, and also that as engineers, we are encouraged to participate in civic affairs and work for the advancement of the safety, health, and well-being of our community.
Right here you can see an overview of our fully operating system. In the front you see one of our smart speed bumps, and in the rear you can see our smart sign, which is in front of you here. We opted for approximately a 40-foot wide work zone. Ideally it would be around a quarter of a mile for a small operation, but this will be used for testing with wires.
And just here is that rendering that we made in CAD that shows all of our components all together. The two total smart signs, the 4 speed bumps, and then our control module here in the bottom right corner.
Just a little breakdown again for you guys, just to recap the revisions to our initial work breakdown structure from last semester transitioning into this semester. With the scope of our project, we did have a significant design change where we implemented now ultrasonic sensors provided by Dr. Zhu instead of initially utilizing infrared brake beam sensors to count the vehicles that are going in and out of our system, as shown in their snippet on the right here. And then on the left, we were able to implement two different traffic control methods. Instead of initially just having the time delay program, we are also able to implement and devise a code for a counting program that we'll go more into.
So as for our schedule, our scope of project did remain on time as we finished up within the last few weeks. However, also, we did decide not to weatherproof any of our components as the components we were going to weatherproof were readily available, provided by Dr. Zhu here on campus, rather than purchasing from an outside vendor, which would take up part of our school budget. This led us to not pursue any weatherproofing testing for our entire system.
Again, just another recap. This is our system control logic diagram, just to kind of get you guys on the same page with the basis of our system, how it works in a real-world application. So our CATS device is first placed, initiated, and set up in an instance where traffic needs to be controlled at several different road intersections in a site, with using our control center right here to power on the device. From there, the user, and in this case the human flagger, will be able to input the different modes to determine whether to use a time-based or counter-based setup. And from there, our ultrasonic sensors that are embedded within our speed bump will be either able to select the amount of time interval basis or the number of cars in and out of the work zone, fueled to the control center, and ultimately to the light matrix to display the traffic signal in alternate directions.
Here you can see an overall view of our entire circuit diagram. On the very bottom left, you can see our first matrix, which would be this one here, and you can see all four of the ultrasonic sensors. They're independently powered from the Arduino using the power sources on the different matrix 1 and 2. So matrix 1 is on your bottom left, and matrix 2 is on your top right. In between all of that is the user interface LEDs, so that's indicating where all the selections are being made. And on the very top, you can see the rotary encoders, which is what the user will use to select the different user interfaces. On the very top left, you can see the emergency stop button. Now this will be used if there's an emergency on the work zone, or if something happens with the system or inside of the work zone. The user can emergency stop the system. Both sides will change to stop so that no traffic should be moving through. The impedance can be cleared, and then the system can proceed once again. Now this is all being run off of an Arduino Mega, Arduino 2650, and this is because of all the requirements we needed throughout the system, and we'll get more into that in the future.
So here's our total Wilkes University budget that was provided to us. The only difference between this semester and last was that we added our PVC components, our hookup wires, and our rubber grommets, which only added about $100 to our previous budget, which left us with a grand total of just under $400, which means we were well under budget as we have a little more than $100 left to spend of the given $500 to us. And here's our total budget that we would take into the real world if we were to do this. Again, we only added the PVC, the GeSn ST connectors, and excess wire. However, we did also add waterproof ultrasonic sensors, which would be the sensors we would use if we were to take this out into the real world.
So getting into the programming of it, we used a variety of matrix that unfortunately there is no Arduino library for, so everything had to be done manually. On the very bottom picture there, you see me working in Excel. So we have an Excel spreadsheet that in all the cells you can select a number, and that number coincides with the color. And the Excel program will write a line of code so that that can be used with serial transmission in the Arduino profile to send the color profile to the matrix. We did some experimental power experiment with that to determine the power consumption of the matrix. With the two panels, so that what you see on this line right here, we came in just under 1.5 amps. So assuming an 8 to 10 hour workday, we decided that a 20,000 milliamp hour battery would be enough for one side. So there would be two different power banks, or if there are more modules, there would be a third, fourth, and so on. Just because what we had at the university, we used a 5,200 milliamp hour battery. In testing, that lasted us around 2 hours, so that would coincide with the 20,000 milliamp hour battery lasting 8 to 10 hours. Right here, you can see the two different color profiles, so the stop and the slow profile. And that was attached to this plexiglass panel right here, and rather than using the sign that we would buy from industry that you would see on a normal work zone, we used translucent orange paint as well as an opaque paint on the rear so that the sun would not shine through, so that while we're testing, we are able to clearly see the matrix and there wouldn't be any sun shining in the driver's backs.
So while we were putting together our control box, we had to 3D print our control panel, which we did on Dustin's personal 3D printer. And once that was done, we placed all the rotary dials and LEDs into their respective spots, and connected any wires or general connections to those direct components so they could be wired directly into their Arduino Mega, which would be housed underneath the control panel. And then just here on the right is our final model of our control module. It has all the components with the Arduino, the wired connections which would go directly to the components, and the battery that would be used, housed underneath the model. And in the middle we have our CAD rendering, and as you can see they are very similar, which is what we're aiming for.
Now this here is our speed bump prototype. We have one out for you today. We do have 4 total in our system, each of which has an ultrasonic sensor specially embedded within that. Now, these are just normal 6-foot high-density polyethylene speed bumps that we were able to purchase. Now, going a little bit more into the machining process, what we did, we went in the basement. We were able to work with Mitch Adams to mill out several holes to act as pockets on the underside of the speed bump, as you can see in the right picture here, to allow kind of different channels for our wiring and connections to be brought out through the entire system, bringing everything together where the ultrasonic sensor fits snugly under that pocket, which is actually right here, right in the center of the speed bump. So you can kind of see how the flush top surface of the speed bump is flush with the top of the ultrasonic sensor, which just allows for a smoother transition.
So when we were assembling our smart signs, we glued all of the components for the base except for the pole, as this would make it easier for transportation to and from the work site. We had to use custom C-spacers for the sign backing so that we have a flat surface to connect to on the pole, which we connected all together with nuts and bolts. And each matrix was adhered to the sign backing with 3M command strips to make it easier for any repair when we would have to take off the matrix to work on them.
Now this is kind of the developmental process. You can kind of see our 7-foot tall PVC pipe smart sign module here. This is one of 2. Now you can kind of see over the last 2 months how we optimized the design and ultimately used orange acrylic paint to help make our signs more visible in an outdoor environment that's dynamic changing in our construction zone. So you can kind of see this LED matrix is fully equipped. We have a battery pack on the back side for a power source, as well as our plexiglass backing, and 2 LED matrices apiece on each smart sign module. All of that is mounted on top of our PVC pipe hole.
So when we had to test the speed bump and the ultrasonic sensors, we used the 2 main programs, the counter program and the timing program. The counter program would count the number of cars that enter the work zone, and then also count the number of cars that exit the work zone. And when those 2 numbers matched up, the signs on the words on the respective signs would then switch. For the timing delay, once the car passed over the first speed bump, a timer would start, and once that timer ran out, the words on the signs would then switch also. And based on where these speed bumps would be on the work zone, these sensors would either count the number of cars that go in and out or initiate the timer to start counting down.
I'd love to get into depth in a lot of the code, but I think Dr. Bednarz would be a little bit upset to go over time. We have just over 1,000 unique lines of code, which is about 84 pages. But I'm just going to go into some of the limitations that we ran into. So for serial transmission to the matrix, we had to use one of the 4 unique pins on the Arduino Mega. There's only one of them on the Arduino Uno, so we were limited to the Mega for that. We also had to use the interrupt pin. So whenever you're coding your program to pick your selections, we had to use interrupts for the rotary encoder so that the program would be able to start over and make sure that it doesn't miss an indication on the rotary encoder. Also, we have our ultrasonic sensors. We did a little bit of testing to determine the exact height of part passing over it. Since they're not the best of ultrasonic sensors, there's a lot of variation between each one. So we had to uniquely test every single one of them to determine the exact height for a vehicle. And then finally, our emergency stop button. So using that, we were able to do a while statement for the entire program. So when the button is pressed, the entire system stops. It displays stop on both sides. And once you are done with your emergency, you can restart the system and it will start just as normal.
So as for full-scale testing, a few weeks ago we went out to the sub-parking lot over by Passant Hall, and we utilized our most desirable scenario of our system, which is 2-directional traffic flow, which utilized all of the components, the 4 speed bumps and the 2 smart signs.
So this video we are loading up for you actually shows our timer mode being implemented with two directional traffic with 2 different vehicles. So you will see one vehicle entrance over the speed bump, and I know the lighting's a little bit different here, but the light entrances do alternate between the stop and slow wording to direct the traffic. You'll have 2-point perspectives with the other vehicle coming around the other side of the work zone, entering the other end of the direction of traffic. Now this video is sped up just for purposes of the presentation, but you can kind of see how everything is set up based on our time interval that we the interval that we inputted to be about 40 seconds.
In the second video here, you can see a one-vehicle counter method. So we have a point of view and also an external view. As the car passes over the first speed bump, the sign switches to stop, the vehicle exits, the timer initiates, so the vehicle lines up here again, and once that time is over, the next direction of traffic begins, the sign switches to slow, it counts the vehicle in, it counts the vehicle out, and then the system cycles over again.
Did we meet our initial goal?
Now, as any testing goes, you always have to troubleshoot, and when we tested, we did have to debug any errors in our code as the overall program would stop running or just not work, so we had to go in and find each individual problem and fix it. And also, the durability of our quick connections was not very robust, as if a car would run over the wires, the connections would break and we'd have to go and fix each individual one. Also, our program does not really take into account the different types of vehicles on the work zone, most notably motorcycles, as the width of a motorcycle is much smaller than the width of a car. The probability of our sensor detecting a motorcycle is very low. However, we do believe that our system will still operate as normal if a motorcycle were to come through our work zone. All in all, our system did prove to be very easily reconfigurable, as that was the main goal, as the transportation to Stark Learning Center to the testing area was very manageable. All of the components did manage to fit in the back of a 2013 Chevrolet Cruze, so that area is much smaller than what our test area was, which is the back of a pickup truck, so it's very transportable. And all three modules of the system did combine to work very well together.
So all in all, again, going off what Trevor stated, really we wanted our system to be easily reconfigurable. We defined that to be a success. Not only were we able to meet all of our constraints and to give the requirements for the scope of our project, we were able to test, design, and build our successful fully working prototype that was not only under our budget but also within the scheduled timeline, which again we defined to be a success within the scope of our project. Again, with engineering, there are ways to innovate, there are ways to improve. We need to be mindful of that. So one of the big things we would consider for future students would be potentially having weatherproof components to be able to test those features, have a central power source located toward the control box. In addition to that, having more optimal connections between our components for further testing. Now, our acknowledgments, we would like to thank first and foremost Dr. Zhu for all of his help and support throughout the entire course and all of the capstone project. We couldn't have done it without his help. Some integral faculty members to associate, definitely Mrs. Lisa Kulavidi, as well as machinist Mitch Adams. Thank you for so much for making this possible. Big thank you to all our volunteers helping us test our prototype with their own vehicles. And finally, Dr. Edward Bednarz is to be thanked for all of his help and support throughout the entirety of the project.
Here are the references we used throughout the entire year. Any questions?
Great work, great presentation.
Thank you.
I have to congratulate for completing the project. I mean, it's not something that usually you probably get to do in a semester. I had a little doubt in the last semester, but I'm very happy to see the result now.
Thank you.
Just comment on the logic of that. You see there timer counter. The counter is the number of cars that can travel between the two stops until the other direction gets the slow or moving fast.
Correct.
So it is not a combination of them, right? It is either counter or timer.
Correct.
So what if you set the counter to 10 and there are only 5 cars passed and another car just waits there until, and there's no other car coming from the other side?
Right, so we have it set up so that the user of the system can determine based on the traffic of the roadway. So we have it set up from 1 vehicle all the way up to 20 vehicles. So if there isn't a lot of traffic coming from one direction, it is fully configurable in that sense.
So it needs kind of active monitoring from the person. Okay, it would be nice to have a combination, like for example,
definitely, yeah.
that if there is no traffic from the other side, it kind of
Have a comment?
Change that, adjust it, give more kind of cars allowed to pass on the restriction, just suggestion.
Yeah, definitely, sure. Thank you, Dr. Brazil?
Okay, so maybe Dustin, could you help me understand how interrupted works? This is not a fair question at all, but I just want to see how you think
It definitely is. So if the system is running, normally you wouldn't want to change something when the system is running if there are vehicles actively going through. However, if you wanted to, you could change the rotary encoders while the system is running. And so to have all four operating at the same time, it can't just continuously check one. So the interrupt, what it does is if you change one and another one, it'll read both changes rather than just going through a loop to read the one, locking that in, going through the loop to read the second one, locking that in. So you can change them all independently.
Thank you.
Thank you, Dr.
Yeah, great project, guys. I'm glad to see it come to fruition. Is it possible to light the sign now, or is it not so tough? I'm just curious how bright it is. That's my own concern, honestly, with the whole system. Are you able to see it with the sun glaring, with the LEDs?
It did work out pretty well, honestly. We did play around a lot with the illumination because that was a big general concern that we did have. So taking that into account, when we did take it out for testing, I mean, all of the people that helped made it possible to test, and they even like stated, you know, it was relatively easy to see the sign switch just based on like where it was relative to the speed bump and where everything was located. So it seemed to work pretty successfully.
Okay, yeah.
Definitely.
I mean, from the video, it looks like it's easy to see, but I couldn't tell, you know, the person.
Actual sunlight, sure, yeah, definitely.
You have enough 40 feet of wire to do that.
Right.
I mean, like you also mentioned, it's a proof of concept too. It could be scaled up to make it bigger.
Definitely.
And it really works with what it said it works on.
Sure. Anybody have any other questions?
Okay, great job, guys.
Thank you everyone for coming. We are Group 8. We did the Pneumatic Stair climbing hand truck, or if you want to know the acronym, which is conveniently the sound it makes when it activates. I'm team lead Zachary Moser, joined by my two amazing colleagues, Savannah and Gregory Hyde. So just a brief overview to kind of get on the same page again from last semester. We're going to go over the project overview, our up-to-date design, our requirements, our specifications, WBS. We're going to go over our schedule, our budget, which is updated again, and testing and future improvements. So project overview, again, just to update you guys. Our original statement was moving objects up and down stairs with a normal hand truck can be really dangerous. A lot of injuries occur. I'm sure everybody in here has helped somebody move or at least reorganize their house. So our solution to this was to use a pneumatic device on the frame of a normal hand truck to eliminate the need for an extra person helping and make it safer in general for people to move things up and down stairs. Our goal was to be able to lift up to 200 pounds safely, and I think we did a really well job.
So here's the isometric view of the two different original designs that we had. So the one on the left-hand side was the one from the fall semester. It has a couple of things still current on it. Some of them we did change. And then on the right-hand side is our new spring semester design that we created in SolidWorks. So a couple changes between the design and the prototype. We have some similarities as well. So we did keep the levers on both of the handles just for easy access to control the hand truck. Then we also kept the cylinder feet flat, flush against the bottom of the hand truck, just so it doesn't, it's flat, sits flat so it doesn't tip over. Some differences that we had to change because we encountered some issues with prototype testing. So we had to mount the pistons on the back of the hand truck. We originally planned to design them to integrate them into the frame of the hand truck, but because of the placement of the frame on the steps with the wheels, the pistons weren't able to reach the step accurately, so we decided to put them on the back. We also had to weld the two cylinder feet together. We'll go into that in further detail with some of our testing videos, but more or less they kind of worked, they were spinning around more or less, so we had to keep them connected. And then we also had to put a separate inlet and outlet valve on the back with the ball valve to connect it to the trigger levers.
So for the design, it's primarily just a hand truck frame and the wheels is what we ended up using out of the original hand truck that I was able to source. Then we welded up 2 more handles and we got rid of the original handle in the center. We then from there welded the cylinders to the frame using a plate and 2 plates on the bottom to keep them rigid, and bolted them on top so they are removable, it's serviceable. Then we have an air inlet and an air exit with 2 ball valves that are spring loaded, and these ball valves will return back to position when a lever is pulled, and then these levers are what actuates it. So they would actually rotate the levers, and that would increase or decrease the air pressure or just release and pull in air. So basically those would activate the cylinders, and then the cylinders will raise as long as you're holding the lever. If you don't press any levers, it will stop where it's at. If you say hold the exit and entrance of the air, it will move still because there's the same amount of air pressure leaving as entering. So here's some detailed pictures so that you guys could actually probably see it. So the ball valves are on the left, and one's an entrance and one's an exit for air. This made it basically simpler for a design than if we were to use a manifold. It was more price efficient, and we were able to get ball valves and springs on them, or well, springs corded on them so that they can move, and they'll also return back with whatever air pressure you have in it. We've tested it with 150 psi of air pressure. They still returned right away, and you were still able to pull them very nice and easily with the handles.
So here we have our requirements, and a couple things have changed since last semester. Our original goal was to lift 300 pounds, and though in conjunction, those 2 cylinders could lift that. They are rated to lift that. There is notable compression with the air in the system. So just for safety measure, we kind of bumped our goal down to 200 pounds. We wanted built-in safety mechanisms to ensure the load is consistently stable with no possibility of user injury. Obviously, every time you get in a car, there's a possibility for user injury. So you can't bring that all the way down to 0, but we did everything we could to minimize that risk. As far as our pneumatic system goes, we have the ball valves, which act as proportioning valves in conjunction with the throttle levers, which evenly distribute the compressed air to the cylinders. And we used single action airlift cylinders that can easily meet the 7.5-inch average rise on a stair. And for physical appearance, some of you who've seen previous iterations of this prototype know that we gave it a fresh coat of black paint, which looks much better now and much more professional. Specifications. As mentioned, we have twin activating single acting airlift cylinders with 170-pound capacity each, and that's rated for about 100 psi, and they have a total of 12-inch extension. For activation and control systems, we have 2 spring-loaded ball valves, as Greg mentioned, and those are connected to the throttle levers. So once you're done activating, they'll return on their own. And then we have throttle cables hidden in the frame of the design. And for the body composition, the throttle levers on the handles are there for easy control. You don't have to remove your hands to activate anything on the device, so you can maintain control the entire time you're using it. The pneumatic lift cylinders in the bottom of the frame, those are originally meant to be integrated into the frame, but we also had some diameter issues. They don't quite match up. You can see they're way bigger than the frame. And as mentioned, the throttle cables are concealed, and we also added high friction pads on the bottom of the feet so that we can prevent slipping.
I don't know how hard it is for anybody to see, but lifting it is light, but it's not me lifting it over my head light, I guess. All right, so for the work breakdown schedule, we have on the left there, we started with the mechanical side of it, and we looked into the steel hand truck, and then we developed from there into everything I discussed with the pressure control, the climb controls, and we moved to testing it. So we wanted to test the air cylinders first when we got them in, and then we tested with the pistons in conjunction, and we finally finished with the management requirements and specifications steps. And then here is the schedule breakdown of how this year was supposed to go, and we pretty much came close to our schedule. I mean, we ran a little close to the project presentation date build-wise, just because of a lot of our ideas kind of didn't come perfect, and so we ended up going with a lot of the good ideas, and we ended up with our prototype too, which is this.
So for our budget, great news, we did come in under budget. Our total was only $403.15. So most of our parts were donated thanks to Greg. He does have a shop at home, so that's where we source a lot of the materials. But for like the higher quality stuff, like the ball valves, the throttle levels, levers, and the pistons, we all got from MasterCard. And that's it. And then for the realistic version, so our original goal was to make it so it is more accessible for everybody. Of course, this price is higher because this is only budgeted for one hand truck. And of course, wholesale prices are going to be a lot lower than the prices that we purchase our materials at.
So we do have some videos of our previous iterations of this prototype that we'd like to play for you guys. So this is the original prototype we wound up with at the beginning of this semester. As you can see, there is no spring-loaded activation, and there is only one inlet that is also a shared outlet. So to use it, you have to disconnect that air inlet and reactivate that ball valve just to let the air back out. So obviously, this is just a proof of concept at this point. The whole thing put together does work. And then the next video is to show it maneuvering upstairs. And again, this is the first iteration. And you can see we had a failure here. So we collected this data and moved on. But you can see the failure was that these cylinder feet are not fixed, so they freely rotate and they scrape up against the stair, preventing proper elevation.
This is due to cylinder rotation inside the actual chamber itself, since they're spring-loaded and since they're not keyed. I imagine if you got keyed cylinders, they wouldn't have that issue, but our fix to that issue is just to weld the feet together.
And here we have the current iteration of our prototype, and we have some testing videos for you. So this was one of Greg's tool chests at his shop, and it weighs just about 200 pounds. There is still equipment in the drawers, but we just used two simple ratchet straps and secured it to the hand truck, and I'll show that one again. And you can see I was standing back quite a fair bit. You do have to make sure that you're keeping it pulled back kind of towards you when you activate it, but the activation went completely smoothly, and there was no issue with this test.
As well as we're taking into account that if the toolbox loaded, there's dynamic weight in it, so the tools did move around. Our first trial with that was the toolbox turned around, which ended up in the drawers coming forward, and it wanted to come off. So yeah, Zach had to move himself because of the center of gravity of that toolbox is also way out. So if we were to redo it, it would have been, everything would have been taken out. But it does prove that it can lift something that sizable and with a center of mass that's actually pretty far away from the pistons, pretty smoothly.
So for some further improvements, we would like to do a built-in strap system right on the frame of the hand truck, because like we did with our actual testing of this prototype, we did have to use ratchet straps to hold the bigger toolbox onto it. So we would like to have a built-in strap system. We also want to integrate a safety system for automatic air release from the pistons. So if you, with both hands let go, the pistons will automatically retract. This is more so if it was to fall down this flight of steps, the pistons would retract, so you don't have a possible impalement issue as well. We also want to do a level sensor, which would be an electronic. We would have to introduce like a coding with that as well. So if the hand truck would automatically sense itself not being level, it would automatically just kind of stop itself from extending or retracting the cylinders.
And in conclusion, we learned a lot of lessons doing this project over the last year. We started off with something we thought was going to be really fun and easy to do, which was kind of naive to start. But through working on this thing, we learned a couple of really important things. Like there is no such thing as on time. You are ahead of time or behind. And we also learned that it is really important to communicate with your team and be all on the same page. And that was something that thankfully by this semester we got really great at, and I'm really proud of us for doing that. But in summary, the pneumatic stair climbing hand truck is a cheaper alternative to existing models. We completed testing and it shows positive and successful results, successfully lifting around 200 pounds with no issue. Improvements could be made further, and we would love to keep working on this, and we're really excited how it turned out. Are there any questions?
How was it going upstairs with like from design?
So, because of the location we tested the weight with, there were no stairs within the area, so sadly we didn't get to test this semester doing that. That is something we actually really look forward to testing in the next couple of weeks. But yeah, there were no stairs in around Greg's shop. We did do a stair test once we fixed the feet together, and it went up the stairs beautifully as intended, but there was no weight on it again, so that is something we need to test.
I also want to point out that I stood on it and Zach was able to operate it easy. And, I mean, I'm not as much of the dynamic weight as possible, but it would 100% based off the two tests that we did. Climb a flight of stairs with something that maybe isn't necessarily a toolbox in size or dynamic weight, but I mean, I imagine Zach would have gone up the stairs himself without.
Yeah.
Zach, so you mentioned you thought it was going to be fun going into it. Was it fun at the end?
Well, it was fun in a different way than I thought it was going to be. You always think an idea is going to go perfectly, and then you start trying certain things, and all of a sudden that falls apart in your lap, and you have to kind of think on the fly. But I guess that's what we do.
Actually, my real question, I see that you acknowledged Jerry. Have you been talking with him regarding IP? Considering a patent?
So at the beginning of the semester, we did have a dialogue going, and that kind of died down as we started focusing more on just working on this thing and getting it to a good place. But we do plan on reconnecting with him and talking about IP and everything.
So I see that you are controlling the cylinder separately using the levers. Is there a reason for that?
No.
Yeah,
So
they're together. As in, if I tilt it down, you'll be able to see. So this was our way to hold the levers down without really making too much of a mount. I'm sorry if anybody's in the back. Both cylinders are tied together with the two airlines there, and they're roughly within like an eighth of an inch difference in airlines. So based on my theory, I didn't do any calculations on it, that they should be getting almost the exact same airflow. And when the pistons weren't tied together and we did testing, you were able to see that they ended up within like a half inch of each other. And being tied together, our thought was that they were going to have a problem with like leaning, but they seemed as though, from all of our testing, they didn't.
Yeah, our testing was completely successful. But just to be clear, this lever allows air to go into both of them, which is shared below at this connector. And then this lever allows all the air in the system to leave that out. Yeah, so one of them is up and one of them is down.
When you were doing the testing, what's the supply pressure?
The supply pressure was, I want to say 90 psi was what I was keeping it at regulated because of the fact that that's what most people keep things at. But we did crank it to 120, and I didn't want to break any of my air system, but it almost tried to lift 500 pounds.
So, in a home setting, how would you propose where does the supply pressure come from?
So, most homeowners would, some homeowners have a compressor. If not, you can also rent them, and you can buy them from Harbor Freight for like $100, $50. And you would basically run an airline into your house, like you could get a 50-foot airline. And so the noise would all be outside the house, everything would be outside the house, and this was so that we could keep it light, we could keep it, somebody can move something up a flight of stairs without ruining somebody else studying in a room next door, and you can also, detach it and then throw it all on the vehicle.
So it's kind of just like somebody goes home, give it back.
Yeah, it was also limiting the fact that, like, if you already have a compressor, good for you, you don't have to pay another $200 to have the unit.
So help me understand, how did you size those two pneumatics, and how do you decide the maximum I should use?
So we looked at their ratings they're rated for, I believe 95 PSI to lift 170 pounds. We figured you add that together and you get 340, but we figured 200, 250 pounds, it could easily lift that. So we just decided to go for it and test it, and it wound up giving amazing results.
Because based on that, this ballpark lever calculation would be helpful.
Yeah, this was in combination with the fact that we needed an exact length to get upstairs, and it's typical 7-inch dry is 11. So we used that as a basis, and then we basically looked at bore sizes and stuff to figure out something that we could get, like a compact air volume. I forget what the number is right off the top of our head. So that you could run it off a smaller compressor without it depleting, and yet still have that pressure load that was already calculated by us.
Final point, so there was exactly more operating. There is a benefit that usually keep operating. So you were trying to fully bring it back.
Yes.
So that's why I think it really needs some almost like a ratchet and hold, so that it can only move in one direction, not the other direction.
Right.
Otherwise, that could be very dangerous to operate.
Yeah.
That one direction, like that locking mechanism would be very essential.
Yeah, that's our plan moving forward, is a bunch of safety features like that level sensor, so that if it sends you getting off level, it would basically assume that you're starting to fall forward and you can't do anything. So the best option for it to do would be to automatically just depress itself down so that it can try to get to a stable point as fast as it can. And we were going to end up doing calculations on how to get the air pressure out of the piston as fast as you can to get it down. Because it stays stable, stationary, but it's only unstable in the air. And then that also we were going to combine with 2 levers that would sense your hands come off, say you trip backwards up the stairs, automatically.
Absolutely. Not everybody's as strong as that.
Yes, that's why he was testing it.
Okay.
Thank you very much.
shoveling snow. As far as the contents of this presentation goes, there will be a recap from the previous semester, especially for the newer audience. But we will maintain our focus in the testing and the results obtained from it to draw a conclusion.
So every year in the U.S., there are about 11,500 injuries that occur from shoveling snow. 100 of these are fatal. And so even like manual snow blowing, that helps, but it's still a lot of physical exertion to do that. Plus, manual snow blowers are still quite expensive. And even more expensive than these are automated snow blowers, which currently sell for about $2,000 to $3,000. So our goal for this project was to reduce the risk associated with snow removal in a much more cost-effective way. And so we set out to design an automated snow blowing system that would be both compact and lightweight enough to be easily transported and powerful enough to be effective at its work. And so the method that the user of the system would have to follow if you were to use the system, it's pretty straightforward. The first thing we recommend doing is just at the beginning of the winter, you set these 4 stakes out of the 4 corners of your driveway. These stakes have infrared sensors on them that form the boundaries of the area to be cleared. And from there, when it comes time to clear the snow, you're just going to have to place that robot directly into that area, turn it on, and then turn on each of the stakes. Once you leave that area, the robot will start moving and clearing the snow. And then when it's finished, you as the user will just have to go out and turn off the stakes, turn off the robot, and move away. So that's all there is for the method. On your left, you see a flow chart describing the logic of our system. Basically what this says is that the robot won't start moving until all the stakes are on and boundaries are established on all sides. When these conditions are met, it's going to start moving forward, blowing the snow directly ahead of it, and it's going to continue until it breaks one of those infrared beams. At that point, the wireless radio frequency signal will be sent from one of the stakes to the robot, telling it to turn around to stay within that boundary. And this process will repeat over and over again until the area is clear of snow, at which point the user will come out and turn off one of the stakes. So here is a brief overview of the work we've done over the past 2 semesters. One of the most important tasks in this project was defining the scope of work, which this project especially had the potential to really diverge into 1,000 different projects, each dealing with some part of the system that could have been improved. And so to deal with the time and budget constraints in the senior projects class, it was really important for us to define early on what we were going to work on and what we were not going to work on. So we decided to make a semi-autonomous robot that would move on a random path within a defined boundary and blow snow directly ahead of it. This included tasks such as the motor and battery sizing, the mechanical design of the robot and the stakes, things like implementing the infrared brake beam signals for the boundary, and also working with wireless communication between the stationary stakes and the moving robot. And finally, working with Arduino code for the control of the system. Some things that fell outside of our scope of work are the exact path that they would take within that boundary and also the direction to blow the snow. So once we had that defined and we had developed a design for the system, we began acquiring many of the components last semester and testing them individually, at which point we also created the CAD models, and then this semester we were able to assemble the mechanical system. And once we had written the code, we did some initial testing in the snow. And after this, we made some design modifications, updated our CAD models, the documentation, and then the final step was to test the system as a whole.
So the final design, as you can see here, is SolidWorks for both the transmitter and receiver stakes. Some highlights of improvements that we made from last semester to this semester include a modified plastic base that we used the milling machine to create. We replaced our initial alkaline 12-volt batteries with 2 9-volt batteries in series. As you can see from our brief bill of materials, we included a optional divider between the IR sensors, and that is because the transmitter signal would sometimes get interrupted and reach the adjacent IR sensor on our receiving stick, and that we obviously don't want to happen, so we include that little divider. Additionally, we changed our RF module, which Richard will talk about later. So you can clearly see the improvement from last semester's robot design to this semester's design. Some of the highlights include the aluminum housing that we now created, that we cut and bent with the help of Mitch. We included a hinge, plexiglass top for ease of access to the electrical components. We included aluminum side brackets on either side of our snow throwing auger system to secure it fastened to the base plate. Here's the bill of materials for our robot. As you can see, we also changed our once square base plate is now a H-shaped base plate, and that's to keep the wheels sort of tucked into the system and away from the snowpack itself. Additionally, we included passive IR sensors on the back of our robot as kind of a means of safety as it detects any beings in general proximity and shuts off the system temporarily. Here's a quick overall circuit schematic of our system. The main takeaway from this schematic is that we have IR sensors on our transmitter stakes, which send a signal to the receiver stakes. Now, once that signal is interrupted, a signal is sent via wireless communication to our robot, is read, and then rotates the motors and proceeds with the program. In this sense, the motor driver here is our central unit, whereas our Arduino is the buses.
So once we had the robot completely assembled, one of the key pieces of information we wanted to acquire was how much force it could push with. And so to find this, we just constructed a simple experiment using a spring, as you can see on the slide. From the compression of the spring, we found the maximum pushing force to be 6.7 pounds. And using that information, we were able to estimate the quantity and quality of snow that the robot could clear. I mentioned the quality of snow because as temperatures rise to the 30s and 40s, snow melts into slush, which becomes significantly denser and harder to clear. Which is why this system and also the $2,000 system that's currently on the market are both rated for light and fluffy snow only.
So to determine how much snow our system can push, we first had to look a little bit into snow hydrology. Now, density of snow is based off of a lot of things, but largely by the cohesion of water molecules. So as you can see there, dry snow has a different ratio of snow to rainwater. So 15 inches of snow equals around 1 inch of rain for dry snow. That's 10 to 1 for average and 5 to 1 for wet snow. That means that dry snow has an average density of approximately 7 pounds per cubic foot. That's 15 for average and 25 for wet. And as you can see through our best approximation of snow weight that is required to push, wet snow is much more difficult to move when compared to other qualities of snow. So a rough estimate based off of not only snow weight and compaction, but also our auger's clearing weight and pushing force of our robot, we can determine that it should be able to push approximately 6 inches of dry snow, 6 inches of average snow, and a little over 2.5 inches of wet snow when there is no slippage in the system.
So when we look at the battery life of the system, we originally designed it for a runtime of 45 minutes. And last semester, we did some calculations for the battery life of each component based on the rated power we consume. And this semester, we put those calculations to the test by turning on each circuit as it would be used in normal operation and measuring the voltage every 5 minutes, as you can see on the graph. The first component to fail was the motor that drives the auger, which lasted for 1 hour and 13 minutes. So even though the system could last for over an hour, we have to rate it for just 45 minutes to incorporate a factor of safety.
So as far as the final testing goes, we have categorized into 3 parts, the stakes, then the robot, and the overall system. So as far as the individual testing for the stakes goes, we used 1 transmitter and a receiver stake. And the results were definitely positive as the robot was able to rotate when the beam was broken. Also to notice is the green LED, when the beam breaks, it turns off, which simultaneously assigns a 0 value, and then it is sent to the robot via wireless communication, which makes it rotate. And when the beam is now broken, the robot continuously receives a 1. Now, the final testing for the robot goes, we used various types of snow. So our first ever testing was using 1 inch of heavy snow, and the results were also quite impressive since it was able to move easily in that thin layer of snow. Also to notice is that there was no added weights or chicken wire to improve the traction. After doing a little bit of more modifications, we tested our robot again in 5 to 6 inches of average snow, and also the results were quite impressive considering how small these motors are. And also to notice is that after the robot moves through a certain area, how clear the path is. That's also very interesting. And then after a little bit of more modifications and fully assembled, our most recent testing we conducted was using shaved ice, donated by the Wilkes penguins. Unfortunately, it didn't work out for us because the temperature during that day was at least 60 degrees, which made the shaved ice into slush and extremely compacted for the robot to clear. But the video does show how robust of our mechanical design is, that it is able to push the snow. So now, as of our overall testing, we had to conduct it indoors and without the snow due to time constraints. But again, it is to show our overall logic of this system. Now, one major change we had to make was the communication module. Our initial was the NRF module, but unexpectedly it showed inconsistency and just stopped working effectively. But we were prepared for such instances so that we had another type of module, the 433 megahertz. But after testing, we also find out that that was also unreliable as well. And we can see that because there's one instance in this video where the robot overshoots a little bit and it then rotates, which is caused by the delay in the wireless communication.
So here are some of the final specifications for both the robot and the stakes. Some of the most notable ones here are that, again, this is rated for light, fluffy snow only. The surface it's used on should be relatively flat and smooth. The power is by rechargeable batteries, so there's no gas or oil in the system, it's all electric. And finally, like I said before, it's rated for runtime of 45 minutes.
So to sum up our snowmobile project, as of the prototype we have right in front of us, it has accomplished almost all of the goals except reliability, and again, that's due to our wireless communication module. But that goal can also be met if we use a high-quality module. But looking at just the mechanical design and the strategy we have created, and if it were to go through numerous iterations, it could be made into a much more reliable and inexpensive system. So as of the cost of this product right now, we were just $5 under our overall budget of $500, and most of our cost was just the auger and the extra battery that we needed, and the other half was the modules and extra materials. But if this product were to mass produce in a factory, the manufacturing cost will significantly decline. But nonetheless, we were able to accomplish a nice, robust, and compact mechanical design, and also a very multi-applicable strategy. And as of our senior project experience, we definitely enjoyed working together, and it was a great hands-on experience as well. So thanks to everybody who has given us great guidance and helped out throughout this project. So thank you, everyone, and any questions?
How did you come up with that number? Did you just let it in the lab without? Yeah. Okay. So that's with no load on that.
That's kind of a no load.
No load 1 hour 13 minutes. And the auger, did you just buy it off the market?
Yes. So this is a commercially available snow joe system. This is a piece that's usually on the end of a long extension with the handle that you kind of do manually. So we took that off and we put it on.
whole class, we tried to challenge it all. We were like, okay, find more ways to do snow testing, but then you got the unfortunate timing that you're finishing up the product as there's no more snow. It's a very, good job to reach out then to the Wilkes first track penguins. Honestly, my own concern with the project, I think maybe I expressed it last year, was the random nature of the robot, that you may be just throwing the snow back over your city path, back and forth. So, if there's a way to code it so that you always know you're throwing the snow out of your way, that would be really nice.
Yeah, that's kind of why it's, that could be another whole project, is the direction of the snow, because, snowblowers have the chute that you change the angle of.
Also with this current prototype, like we could deattach this front auger and replace it with like a one with a chute, and then code it that way for it. So it's very flexible with this prototype.
So do you think that would be hard to code in, just to go down, turn, come back at an angle, more of a defined path?
We've had that program in it before too,
but since there's like slippage and things like that, and after some point it just wouldn't remain intact.
Unless you have a GPS signal that you're tracking at full time.
yeah, I think this video does it best because this program is just supposed to go forward and come back and then turn and then go forward again. But like it doesn't like reposition itself that well. There's slippage, so it kind of just goes right.
Just make a big comment. Over the past 5-6 years, we had many groups who worked on similar projects. Like we had mobile lawnmowers, the stuff at the top of the car to clean up the snow. This is by far the best one because they really put this whole thing, the power system, all of this in such a small package. Just that by itself was a great success. So they put lots of common sense in their design and so it's really, and they are very self-driven. That's the best thing. I work with them and they are really just on autopilot, basically speaking. So they put the requirements on themselves much higher than what I asked them to do. So it's very, very great team. Good job.
Okay. Thank you guys. Okay, everybody, so we're going to take a brief 3-minute break, just stretch, and then we'll come back and do the last 2 391 things. Please stick around for all students, please stick around for the last 2 teams.
Questions here? No questions? I've been here the whole time. I'm trying to get some ideas. Zavi? We have a good Monday here. Yes. Like this. I've been here, come on, you see?
Thank you everybody for sticking around. So we have two more teams left, our Senior Projects 1 teams, and they're going to be finishing up in the fall, so feel free to ask them lots of questions, give them good guidance going into the last semester.
So, hello everyone, my name is Corey Gals. I'm Zachary Mazer. I'm Mark Kozub. And I'm Brendan Lee. We're Senior Projects 1 Group 1. The name of our project is Hindsight Blind Spot Monitoring System. So the purpose of our project is to design an attachable blind spot monitoring system that aims to increase the awareness of skiers and snowboarders with the area. We plan to do that using sensors that monitor the blind spot of the user, and when those sensors detect on their skier or snowboarder, a non-visual vibrational signal will be provided to the user. So on the left, we have a preliminary design. You can see it's an attachment that goes on the back of the helmet. And on the right, we have a basic diagram of the operation of the device. So the black circle is the helmet or the user, and it's facing downhill. The light gray shape is Hindsight mounted to the back of the helmet. And we're going for a distance-based vibrational feedback. So these circles are other skiers or snowboarders, and the one on the right is closer, so it's going to cause a more intense vibration, versus the circle on the left, which is further away, so it causes a less intense vibration.
So skiing and snowboarding has become a very popular sport. And with that increased popularity, there's a greater increase for injury. And the primary cause of these injuries are collisions with other users on the slopes. And a way that we can prevent this is by using Hindsight's blind spot monitoring system to increase the spatial awareness of the user on the slope. So related items to this are the car blind spot and lane shift monitoring systems. This is present in a lot of newer cars today, where you get a vibration of steering wheel, a blinking light, or a noise to alert you of a car in your blind spot so you know not to merge into the lane. There's nothing we've seen commercially available that relates to skiing and snowboarding, but there was a Swiss university that created the smart ski helmet, which is pictured here on the screen, that they utilize sensors in the back of the helmet, but instead of vibrational non-visual cue to let you know if someone in the blind spot, they use LED lights in the peripheral vision of the rider. They did have a controlled study where they did see there was a greater increase in spatial awareness on the slopes, so keeping the rider safe.
So when we started planning for this project, we did have to outline a bunch of requirements. So first off, we do want to do a 3D printed housing. This will basically encompass and protect the internal electronic components from the external environment. So protecting these components from things like temperature and water. If these components are exposed to too cold temperatures or too hot temperatures or even water, it will stop functioning. Also, we want a universal design such that it can attach to any size, style, skiing and snowboarding helmet. Also, it must not compromise the internal structural integrity of a current helmet, which is specifically why we're going for an attachment. Also, we want a rechargeable battery that can last approximately 8 hours. On an average day on the slopes, you're probably going to be up there for about 8 hours. Most importantly, we need to make sure that the user is not uncomfortable. If we have too much weight on the back of the head, over time, it is going to get uncomfortable. So this design does need to be as lightweight as possible. So going to the electrical/software side, we need this system to be able to detect objects for up to 8 meters. Also, we need to orient these sensors such that we can get a 90-degree field range of measurement. And we're going to be going with a clear, concise, non-visual cue to alert the rider that there is other riders coming from behind them. So this would be for approximate distance and location. We're going to operate this system on a small microcontroller, and it will have an on and off system. And for convenience purposes, we want to implement a mute function. This will be used in certain situations where maybe you're going down the slope and you might stop to fix some of your equipment or just wait for a buddy who's dragging behind you. Also, it could possibly be used if you're waiting in line for the ski lift. If you don't want to turn it off, you can simply just mute it and you would have no unnecessary vibrations happening for you.
So in order to create a fully functioning prototype, here is a list of the hardware that we will be using. This includes a 6-volt battery along with a voltage regulator, 3 TF Luna LiDAR sensors, a mechanical rocker switch, an input button that has a muting function, 3 haptic motor drivers, and 3 DC vibrational motors, along with a TNC 4.0 development board. So the program that we wrote was using Arduino IDE, which was written in the C++ dialect, which uses a UART communication code to communicate with the sensors and an I2C communication protocol to speak to the motor drivers. Here we have a flow chart that shows the basic logic of our software. So as you can see, once the device is powered on, the system sits idly. And like we said, the user has an option to either mute or unmute the device. Once the device is unmuted, the sensors begin to scan. And once an object is detected, it will send a signal to the rider with a soft vibration, letting them know that there's someone in their blind spot.
So here we have our work breakdown structure, and these are essentially the 4 topics that encompass this project. So as for the mechanical aspect, we essentially just have the 3D printed housing. On the electrical side, we have the components. So which components are we using, and how are they arranged inside of the 3D printed housing? Also, the programming and code, which essentially just relates all of the components and how they work in the background. As for the testing, we have sensor testing. So how accurate are these sensors, and how do they have to be oriented to get basically achieve our goal? As for notification system testing, where are we going to place these vibration motors, and can you feel them where they're placed essentially? As for prototype testing, once we get this code all wrapped up and all the components together inside of the housing, does it function how we expect it to, and more importantly, how we need it to? As for management, we had to outline specifications, requirements, draw up a schedule, and a budget. These 4 things essentially kept this project on track throughout its duration and have put us in a pretty good position for where we are right now.
So this project is broken up into 3 phases. Phase 1 has been this past semester where we came up with our project idea, and then we started our preliminary testing, coming up with our design, and we stayed very close to on time for that process. Summer 2022 is considered phase 2 for us. We're lucky to have this greater amount of time to work on this, and this is very testing intensive to come up with a final prototype. And then phase 3 in the fall is testing that prototype, seeing where we need to potentially redesign and make our product better for December.
So here we have our budget overview. On the left side of your screen, you can see a table essentially summarizing some of the expenses we've had thus far. And on the right, we have a pie chart where you can kind of visualize all these expenses as compared to the entire budget. We have used less than half of our budget right now. This does put us in a very good spot financially to either switch out components if they don't work, or maybe add some other features on them in the future if we have extra time. Here's our detailed budget for Wilkes University. As you can see, we have all of the prices outlined for every component as well as what's donated. This project, like I said, is under budget right now by a lot. We have it coming out to $231.03. As for the real world, the only thing that changes in this budget is that we've added the pricing for all of the donated components. And we have added labor for the product development aspect of this project in the real world. So we have 4 engineers working 4 hours per week for 38 weeks. We priced this at approximately $150 an hour, and we got a total price of $91,683.63. Here we have our mechanical design overview. On the top left part of your screen, you can see the 3D printed housing. We're going to be printing this on PLA material, and you can also see the 3 slots where the sensors will be able to peer out of the housing. They're flush with the outer rim of the sensor lenses. That will give us that watertight fit so that none of the internal components get damaged. We do realize this is a very bulky design right now, but we do believe that there is tons of room for improvement in that range. That will go directly into the hardware assembly. So over the summer, we will be testing certain arrangements for these components, and by the end of the summer, we hopefully have optimized the space usage inside the housing, which will definitely bring down the size and make it more compact and aesthetically pleasing at the end of the day. So just to go over the hardware assembly, we have the 3 vibration motors denoted as A, the battery denoted as B, the microprocessor denoted as C, and the 3 LiDAR sensors denoted as D.
So on the electrical side of things, as Mark was saying earlier, we're going to be powering the devices using a 6-volt battery, but none of our components can actually use that 6 volts. So we have to step down the voltage to 5 volts and power the components in that way. On the communication side of things, we have our 3 sensors connected to 3 serial ports on the TNC port, and then our motor drivers and motors are going to be connected to the I2C ports.
The NSPE Code of Ethics states that engineers, in fulfillment of their professional duties, shall hold paramount the safety, health, and welfare of the public. And we took great pride in the fact that we're helping hearing impaired riders be able to go out and enjoy the mountain, and also decrease the number of collisions that are happening each year. Also in the same code, it states that engineers shall acknowledge their errors and shall not distort or alter their facts. We think it's very important moving into the summer phase, as we're testing our product, that we should present all our data, because it is a safety product, and we want to make sure that we make the best design as possible. And lastly, the ASME Code of Ethics states that engineers should be striving to increase the competence and prestige of their engineering profession. And we think the best way to do this is just to advance the technology that is in society today, and as you can see, all of us are doing that here.
So over the course of this semester, we decided to do some initial testing to get familiar with the components we were using. So this video on the left is going to be, Mark is going to be walking towards the TS luminous sensor, and it's going to be controlling the LEDs on the breadboard there. So as he gets closer, the green LED will light, then the yellow, and then the red LED as he crosses certain thresholds that we defined in the program. And then you'll see the opposite behavior as he backs away from the sensor until he gets outside of the range that we defined and all of the LEDs are on. To do some further testing, we wanted to also control motor speed, because that's effectively what we're going to be doing with the project. So here in this graph, that's the output of the data that we got from that program. The dotted line is distance, and distance here is defined as distance away from the sensor, and the solid line is motor speed. So as distance goes down, motor speed goes up, and we see that trend continue as we move closer to and away from the sensor. As Zach was saying earlier, we're going to be doing a lot of testing over the summer, and that's basically going to be on the component performance. So first we're going to be looking at sensor accuracy to characterize the sensors that we're going to be using and better understand what we're working with. And then past that, we're going to have to do some testing on sensor arrangement. Now what we're going to be looking at there is basically understanding the constraints of the system that we're constructing. As you're putting these sensors close together, at some point they're going to start to interfere with each other and you're going to be getting wrong readings. But you also have to see at what point when you start to move the sensors away from each other that you start to create a large blind spot in a blind spot monitoring system, which is not what we want. One thing that we potentially anticipate is that we might have to add more sensors to the system. Anyways, to continue, so what we're also going to be looking at is similar to the sensor arrangement, we're going to be looking at motor arrangement. So right now we're looking at putting the motors close to the helmet, inside the device still. But if we feel that we can't get the vibrational signal that we need out of that, we might have to move the motors closer to the user somehow.
So I know the next slide is called Moving Forward While Looking Back. In fall of 2022, we would like to research and potentially apply for a patent for this technology. In the future of hindsight, past the capstone project, we would like to see this product actually integrated in a real-world scenario on the slopes and see how it performs in keeping people safe. We also would like to we'd also like to use this product, specialize this technology into other sports. And the main one for that would be biking, which has a lot of different variables to consider in that. And then also create our own integrated helmet with the hindsight technology. So the purpose of this project is to create a product that creates a safe and enjoyable skiing snowboarding experience for everyone by utilizing the sensors on the back of the helmet and the vibrational motors to alert the user of someone in their blind spot. And our next steps, as we've been talking about, is testing and prototyping over the summer to come up with a finished product for December.
So here's our references. And our acknowledgements, we'd like to thank Dr. Wu for advising us during the semester. We'd like to thank Dr. Zhu with guidance with mode selection and circuit design. We'd like to thank Dr. Benrash for keeping us on track throughout the semester with assignments. And then we'd like to thank Lisa for ordering components and dealing with annoying customer service. Any questions?
So, since I work very closely with you guys on this, but I don't think you guys have too much grease. So this is I like so many things about what you guys are doing right now. Again, I don't always just say good things just because you guys are good. So it is because, especially as a 391, I want to be creative. So you know what I mean? But at the same time, like I said, how you the experimental results you give, that just tells you guys want to, especially that do that in the first semester. That says a lot about the basic approach you guys are taking towards this project. So that's great. Not only that, I see the speed control. That plot is also very informative. You know, like even better than some of the 392 results. So even that, again, that approach, I really want to compliment you guys for that. And they keep doing that. I'm really excited to see the results. I think it's going to be a great project.
Thank you. Thank you. Any more questions?
I think I asked this question in class, but I'll ask it again. How are you going to determine how many sensors the actual sensor weigh? You kind of mentioned it, Corey, that you don't want gaps, but you don't want too much overlap. So what's going to be your final metric to determine the final rating? What do you testing over the summer?
I think we're just going to kind of look at, right now we're looking at a 90-degree range, and if we can hit that with 3 sensors and then see if there's giant gaps in between those sensors, we'll try to add sensors in between. And I think adding those sensors in between will probably increase the range. But similar to what we were talking in class, things like trees and stuff like that, Zach had a funny comment earlier, you know, trees aren't going to be running at you from behind, and you're going to be passing stuff. So maybe we don't need, 180 degrees fully side to side, but maybe a little bit less.
I would just add a quick comment. I think it's not easy to use a motor to move the sensor around. So the natural motion of the head will create that scanning process. So that's very important for this application. If you make an artificial movement kind of combination of work and so many things. So that's why they have to really just rely on the natural motion of the head, because you don't keep your head at still. When you are doing, your head is naturally moving. So if you do 3 inserts, kind of it's going to naturally cover that range pretty well. So that I think that they are pretty safe on that in that regard.
Yeah, I mean, like a few inches, at the head, sweeps out many feet, 8 meters away. So, I mean, it's going to be able to cover a lot of areas at the end of the day.
Like a cone shape, if you think about your head is moving, then it's constantly scattering. So I think instead of moving, putting some motor inside, like constant scan, I don't think that's going to work very well.
I was just mentioning class that would make more sense because it's get more of a range, like you're saying, hey, we don't do it, let's say we get some.
Yes.
So just a comment about LiDAR. Two things that usually it isn't used while moving. Safety or not use their LiDAR guns while moving, so that might be something you have to implement into your code. And the second thing is LiDAR always takes the speed of the bigger object. So if you have 2 objects next to you, it's going to recognize one over the other. It's like a big box truck passing a normal car will take the speed of the box truck. So you might have to account for that.
That's fair. And hopefully there won't be, realistically, there's not usually tons of traffic on the slope. It's usually just a few people. So hopefully that won't be too big of a problem. But that's something that we will see in the future.
You guys will definitely have a lot of challenge later when you do the program and the integration. I can just the electronics side, so this is pretty heavy on this program. That will be pretty much your main focus for the next semester.
Yeah, getting one is
I think the issue is the communication. You just communicate, you want to get all those data in, process them in real time, and give you the very quick results because it has to be quick. So those communication and the programming circuits, those will be all very challenging.
Thank you, guys.
Our senior project is the active angle. Alright, so today in our presentation we're going to be talking about the overview of our project, a general background, our WBS, Gantt chart, budget, our requirements, specifications, ethical considerations, a detailed description, CAD drawings that we have done, as well as the future plans of active angle. So in short, our active angle is a propulsive active ankle prosthesis. And we're trying to make it to be used for amputees who have lost limbs below the knee, so a transtibial amputee. Propulsion comes from the calf muscles for those of us who do not have a leg amputation, and that is a very important motion. The calf muscles are one of the most important muscle groups in our body when it comes to walking. So we really wanted to make sure that we mimic that with our prosthesis model. We also designed it with the idea of making it rated for K2 use, meaning that it will be used for individuals that are moderately active and will occasionally be walking on uneven terrain. Some definitions that we just want to highlight that are going to be talked about throughout the presentation are inversion and eversion of the ankle, so that is the side-to-side rotation of the ankle, as well as dorsiflexion and plantar flexion, and that is the lifting and lowering of the toes respectively.
So, to provide you with some background information as to why we chose this project, basically, we're going to start here. 2 million people in the United States suffer from some form of lower limb loss. So basically, they have turned to present-day prosthesis in order to regain some walking control and support throughout their life. In order to replicate the ankle, it's a hard thing to do. The ankle joint is very complicated in its nature. So basically, there are various types of prostheses that can range from passive types to active types, and even custom types of prostheses. And as you can see, the price ranges range from either $1,000 all the way up to $80,000 plus in price. The one that's on the market is about 5 pounds, so that's basically a little bit heavier, considering that the average ankle or average foot weighs about 2 to 3 pounds. So our main goal would be providing amputees with a more affordable, lightweight, prosthetic option that provides a normal walking gait and, reduces stress on their joints, back, and anything else. Our starting point came from about 2014 when a previous senior project group began with their own prosthetic ankle. You can see that, it's very rigid in design. There's things sticking out of it. The electrical components are basically exposed, and, it's not very practical. With this, we began our journey into making this a better product.
For our work breakdown structure, we separated into 5 parts. We started with trying to find an idea for this project as well as the scope. We then moved into some research for past projects that may guide us towards a solution, as well as modern solutions that current companies have. Then we started looking at the different mechanisms that those companies use and what could be viable for us to use as well as sensors and materials that those companies use. Later on, we'll be ordering and manufacturing most of the parts, and then we'll be moving on to part testing, as well as individual and combined testing for those parts. Finally, we'll be doing the final assembly and testing for the entire foot. So this is our Gantt chart showing that we've completed all of our research as well as our project conception. Later on, over the summer, we'll be completing ordering and manufacturing parts with a December 2022 final testing. We were allotted $500 by Wilkes University. We plan on using $450 of that, keeping in reserve $50 for any extra expenses, such as any extra components that we might need or replace from testing, or any extra shipping costs.
So, for our mechanical and electrical requirements, we have various points that we want to hit for each part of our device. So, for the foot base, we want that to be able to support, the user and provide stability as they're standing. We also wanted to have a smooth rollover motion when the user is walking. And lastly, we wanted to mimic the inversion, eversion movement of, an ankle that would normally be like real life. Secondly, we have the ankle joint. We want that to be, secure to the foot base, as well as the cat housing that will be provided for the top. And then we wanted to mimic the dorsi and plantar motion of lifting the ankle up and down along with that foot base. For the electronics, we want that to be, sheltered in the calf housing from any weather conditions, such as, water and anything else like that, such as snow, and also, materials from the user, like clothes and any friction that may occur. Continuing, we want the calf housing to, like I said, provide any shelter from weather conditions. We want that to be a strong yet, lightweight material in order to provide support for, the co-joining pieces to work in tandem together. For the battery, we want that to fit in the calf housing as well, and another portion of it to be rechargeable for, the motor use. For the weight, like I said before, we want that to be under 5 pounds, and we want it to withstand, someone weighing 200 pounds, and then the force of them, running or jogging as they try to do that dynamic motion. For the specifications, like I said, for the foot base, it's going to be curved to provide that smooth rollover motion. It's going to have an arch in it in order to be able to fit into a shoe. And then it's going to have a split keel going down the middle in order to provide that inversion, eversion motion that we need, what we're looking for. For the ankle joint, it's going to be connected to the calf and the foot base via screws that are strategically placed in order to keep it in line. We don't want too much movement from it just being free floating. And we wanted to utilize motors and a screw rod in order to provide that dorsiflexion motion that I was talking about earlier. So the screw is basically going to move around in the nut and lift it up and lower it down when it comes time. For the materials, we want the foot base to be made out of carbon fiber materials, and the screw and ankle fixture would be made out of aluminum left up to our group. Basically, we got word from Professor Zhu that we could use 3D printed materials in order to provide that extra stability and that lightweight material that we're looking for. In continuum, we wanted to use a 9-volt battery to power the Arduino Uno microcontroller and a battery pack to power the motor. And lastly, we wanted the interface, like I said, to be an Arduino Uno microcontroller and a pressure sensor to be coupled with that. That's basically going to fit on the bottom of the base. The mechanical testing that we're going to get into will be stress analysis of the ankle joint, stability and durability of the pieces, such as the ankle joint and the motor that will be housed, and testing of the motor speed in order to see how much torque we may need in order for that foot to lift up and lower down.
Concerning the ethics of our project, we were looking at the NSP ethics concerning the welfare of the public and its interests, as well as the FDA guidelines and for prosthetics.
So next we have a more detailed description of the active ankle. The active ankle is made up of two main components, our foot base and our calf housing. For the foot base, there is a rubber sole that will be along the bottom, and that's going to protect our pressure sensor, which is in light blue here. The pressure sensor is the shape and size of our foot base. Attached to the foot base are these ears, which will hold a pivot pin, and then the pivot pin will allow this linkage mechanism to rotate. There is a pin nut within our linkage mechanism, which allows this screw to go down into it. And then we also have a resistance band that is connected to our foot base in the front here and linkage mechanism back here by custom clips that we will design. As Elijah mentioned earlier, in the calf housing, we want to make sure that everything's protected. So we have the motor up here, we have our battery, microcontroller, screws, and then any wiring that we have will be in there. All right, so now for the process of how active ankle will work as the user is walking with it. First, the toe sensor will be activated. They'll press down on the toe portion, and then that will activate our motor. The motor will turn our screw down into the nut, and then that will cause the resistance band to gain tension. It will also lift up the heel. So this motion will create the propulsion that we are looking for as the user is taking their step. At this point, they're in mid-step and they're ready to come down on their heel. They land on their heel, the pressure sensor is activated in that portion, and then that will trigger our motor to turn the screw back to a neutral position. Once it's in a neutral position, the user can then follow through with their rollover because we have a curved foot base. And then that completes the cycle of the step. Right, so for our CAD model, this is just our foot base here that we made on SolidWorks. And in the top view, you can see the split heel that we mentioned earlier. That allows for each side to have a little bit of motion for the eversion and inversion. In the side view here and over here, you can see the ears more clearly. That will hold our pivot pin in place. And then here's the CAD model that we have so far. It's open so that you can kind of see what it would look like inside. The linkage mechanism is more a slot, which is easily seen here, where the screw can go through and it won't hit any parts while the user's walking with it. And for our future plans, in the summer, we're going to complete more SolidWorks testing, force analysis. We'll be ordering and 3D printing parts as needed, and we'll start individual testing on those parts. We'll start building the prototype, but that leads more into the fall. We will finish our prototype, complete more testing, any troubleshooting that needs to happen, and then we'll complete our final testing before our presentation in December. Some improvements that we thought about including for next semester is a guide for our linkage mechanism, which we have a model here, and that would provide more support and stability for the user and for this system. We also want to look into a smaller microcontroller or any other smaller, more lightweight parts. So these are our references. And thank you everyone for listening today and staying so long. We'd like to thank our advisor, Professor Greiner, Dr. Bednox, and Dr. Zhu for advice. And if you have any questions, any comments, suggestions, we would really appreciate them. Scope of our project and the budget that we have, we will probably make it out of 3D printed plastic, probably polypropylene.
So for the, are you planning to use a motor to drive those through, or like what motor you're using?
It'll be a DC motor, and it will.
So that's okay. So there's something better. You should choose just a linear actuator.
Okay.
Because a linear actuator directly provides the motion you're looking for. So you have to save that with that part. So there's something that's integrated. You don't have to do that integration.
Okay.
And also, if it's commercial package, it works a little bit better. So look for a nice linear actuator so that provides that motion right you need. You don't need to do a motor because that assembly will not be as simple.
Right. Okay.
But that self-contained actuator will give you that linear motion as simple as that.
Okay.
Keep it simple. But you have to be really careful because we need torque, but at the same time it's not be too heavy. So what's your choice may not be too many. You just have to be careful because hopefully you can find the line that suits your application. But that will be really important.
Okay, thank you.
The second is that so how many deburr freedoms you're talking about? How many actively controlled deburr freedoms you're talking about? It sounds like you're trying to do two, right? One in this direction, one in this twisting direction,
yes.
Right?
Well, we are not controlling the inversion and eversion. That is passive with display.
Okay, so that was my point. I think that you might want to just use one. So one active, one passive, that might be better. Because the two active, I don't think it's not just later when you do control, you're going to find out that using a sensor to keep that command may not be necessary.
That's exactly what we have. We have one passive, one active.
So you should do the active one, then this one keep it passive.
It is.
Yeah,
It is having that type of motion anyway.
Those are all active. You've got these very, very interesting project. Looking forward to seeing the results.
Thank you. Anyone else?
Have you guys sourced your pressure sensor yet?
We actually found one on Amazon that's pretty cheap. I think it's like between $20 and $50.
Okay, yeah, I just know that we had a lot of difficulty finding one that fit what we did for our project, so definitely get on that fast.
Yeah, we did look into it. There's actually a picture on the budget slide where it literally looks like a foot, and then it has lots of little sensors throughout it, and then we can program each individual one to what we want to have. And like I said, it's relatively inexpensive, so I think it'll be perfect.
So it's just about having pressure present, it's not about value that pressure?
Yeah.
We'll have to look into that. It'd be awesome to have it be more detailed, but we'll have to just see next semester.
Very interesting project. I hope you know what you're getting yourself into. And following up on what you said, you probably need to reconsider the scope of your work. It can be quite complicated, and there's only so much that you can do over the next couple you are not designing a toy. So either adjust the corners of the project or be prepared to really deliver it. That's one. So aside from that, how are you going to test that?
Testing. I know some testing can be done where if you can create a piece that someone with both legs can put their knee in. I should do that in heels. But you can put your knee in it. You can try walking. So that's probably one way to test it.
Yeah, I told them, or I was explaining to them that I possibly have like a relative that would be willing to try it out because they have, need for amputee, need for a prosthetic. So if they're willing, hopefully, if not, we might have to find some other form.
Very careful, because anytime when you have human subject testing, there's a very lengthy process of getting approval, very complicated. I don't think you guys have to be just a guinea pig on this, so test on yourself. But using something else, third-party testing is very complicated. I don't think you guys want to go down that path. So don't even think about it because it's complicated. There's legal issues, complex legal issues. Even the university had to prove it by a committee to approve all those things. So
There's a lot of rules centers and issue. There's also ethical considerations, and so they are very fine line.
Just forget everything I just said.
With the 2014 model, there is an attachment for the leg that was used. It's for anyone, but you can definitely put your knee in it, even if you're not amputated. So we definitely have some idea of how to attach it to the leg. The scope of the project isn't specific to that.
So just two things when it comes to the 3D printed parts. One thing that's going to be important is your orientation when you print. Depending on how your forces apply, your layer lines can split in that. The second thing is when you're printing flexible film that's TPU or polyurethane, was one of the ones they said. Basically what happens is your infill density will change how much your plastically deforms. So either it's plastically deformed and completely break, or you can have small deformation, or you can go, so you're going to have to experiment with that.
Thank you.
Okay, guys, give me just a few minutes to give some concluding remarks on our day. Thank you so much to everybody. What a wonderful day this was. I have a whole list of people that I want to thank, so just please bear with me. First, I definitely want to thank Ms. Lisa Colavetti. I think she's in the back there. Not only has she... Not only has she helped every single team. You saw how they listed her in the acknowledgments of the ordering process and helping with the project, but she pretty much coordinated this whole banquet event single-handedly, so I appreciate all she's done with that. So, I also want to thank Mr. Mitch Adams and Mr. Jim Lennox for all their help physically with the students. I don't think they're here today, but every single student worked with them in the basement, in the machine shop. So, so much thank you for their help. Zebra Communications, again, thank you again to Chris and Maddie for staying here. All day here So, I also want to thank the dedicated faculty advisors working with each team every week. I know each team made sure to acknowledge them, but also faculty advisors that weren't the primary advisors, but just wanted to help out just for the sake of helping out. I know my colleague, Dr. Zhu, appeared almost on every single slide. He's the go-to robotics, Arduino, motor expert in every single team. So thank you to all the faculty advisors for all the help, truly with all this. Thank you to our guests. This is great to have our first kind of event in a few years where parents were invited and friends. So hopefully you enjoyed seeing your sons, daughters present something. Thank you for coming. And then finally, thank you to all the students. Great. I talked with my colleagues and other students, and they all pretty much said the same thing, that this is one of the best senior project cohorts we have ever seen. Truly, truly, truly. Every single team made sure to complete their prototype, test it, get a great conclusion at the end. And, you know, I will say that we just went through ABET review, and I don't know if I could say Dr. Badura and Dr. Capstone, but we were recognized by ABET for our work in senior projects. That was one of the exemplary features of our program and one of the hallmarks of our program. So this event today really showcases all the great work our students do, working all they've accomplished in just 2 semesters, really. So yeah, thank you to the 392 students, the 391 students. Thank you, everybody. Have a great day. We'll see you next time.
So that was
Do you have that case for
thank you so much.
Thanks for you. Thank you for being here. No problem, no problem.
Okay, did the case go back into
I don't know. I know I put. This is the one we didn't use.
So,
I just want to thank both of you again.
yeah, of course.
I think Dan said that you could leave all this in the zebra office.
I'll be taking it back.